Hello. Hi students, good afternoon. I hope my audio is clear and loud enough. If you can please acknowledge in the chat box, we'll get started with this live session. We got delayed a little bit. I apologize for that. Acknowledge. Okay, voice is clear. Thank you for that. So myself, Gautam, faculty for analog circuits, EDC, and also electric circuits at Home Institute. I've been teaching this subject for almost 10 years. Okay. So in this session, and by the way, this is not the only session I'm going to take with respect to analog circuits. I'm going to take a series of sessions. This is only the first one in that series. Okay. So first things first, this is the overview of analog circuits. Okay. So what are the major topics or chapters that are part of the syllabus? So as you can see, first you have ideal op-amp and its applications. This is by far the most important topic in all of analog circuits. Okay, whether it is electrical or EC or instrumentation, at least half the questions will be coming only from the topic of op-amp, and that is what we are going to do in this first session. Okay. So apart from ideal op-amp and its applications, we also have to learn or understand diode and also the different circuits that you can make using the diode, which are what? Clippers, clampers, peak detectors, voltage multipliers, rectifiers, voltage regulators, and also you can combine diode with op-amp and make some interesting circuits. So all of those circuits will be part of the second topic, which is diode and its applications. Okay. And then we have the first transistor, which is BJT. Again, BJT, there are two parts. First is DC analysis, which is all about analyzing any given BJT circuit. So there are two types of transistors, NPN, PNP. And along with the transistors, there will be other elements as well, a few resistors and a few voltage or current sources. So any given BJT circuit, how do you find the various voltage and currents? That is what is this BJT DC analysis. Okay. And also DC analysis includes the topic of current mirror, which is a circuit that can be used to make copies of a given current source and so on. Okay. And then using the same BJT or the transistor, you can also design a variety of amplifiers, and that is what is part of this AC analysis. All right. And in the first chapter, we'll always assume the op-amp is what? Ideal. Yes, ideal op-amp and its applications. Always the op-amp is assumed to be ideal. But if you take any real op-amp, anything real is never ideal. So in the same sense, even a real op-amp will not be ideal. So this real op-amp will not be ideal in a number of different ways. So all of that stuff we'll study in the fourth chapter, which is on real or non-ideal op-amp. Okay. So you must be familiar with things like finite gain, input offset voltage, input bias current, input offset current, slew rate, finite bandwidth, etc. So all of those aspects will be covered under the heading of real or non-ideal op-amp. And after that, we have a few small, miscellaneous topics in the name of oscillators and also feedback amplifiers. And towards the end, we have this topic which is about MOSFET. And again, you just like using BJT, you can make amplifiers. Using MOSFET also, you can make a variety of amplifiers like common source, common drain, common gate, cascade, cascode, differential amplifiers, so on and so forth. Okay, so that is like the quick overview of this subject. Again, MOSFET is also a part of EDC. Yes, so you can study there or you can study here, but the concepts will remain the same. So as I already told you in the beginning, that in this session, our focus will be only on ideal op-amp and its applications. So this session, strictly speaking, is not going to be a marathon, because usually marathon, I guess it is for like 8 to 10 hours. But this session will only try to cover the topic of ideal op-amp and its applications. Okay. So I don't think this session will last for more than 4 hours. So in that sense, this is more like a mini marathon rather than an actual marathon. But I have tried my best to include problems in such a way that every concept has been touched or covered. Okay. So we are going to revise this subject through problem solving. And all these problems are essentially what get PYQs, as evident from here. Okay. So again, under this heading of ideal op-amp and its applications, we again have like 4 or 5 subtopics. First is ideal op-amp and negative feedback. Again, you must be knowing majority of the op-amp circuits are based on what op-amp connected in negative feedback. Even in GATE exam, at least 90% of the questions related to op-amp are based on negative feedback. Okay, so ideal op-amp, when it is connected in negative feedback, you can have a variety of circuits. We look at all those circuits that are based on an ideal op-amp connected in negative feedback. Okay, and the same ideal op-amp can be used without any feedback. The same ideal op-amp can be used without any feedback, in which case we say the ideal op-amp behaves like a comparator. Okay, and the same ideal op-amp can be used in positive feedback, where also it behaves like what a comparator, but it is called a Schmitt trigger. Okay, so Schmitt trigger is also some sort of a comparator, but it has positive feedback. And based on, using the Schmitt trigger, we can come up with 2 waveform generating circuits, namely the relaxation oscillator and the triangular waveform generator. And finally, using the op-amp, you can also design what are called active filters. Of course, op-amp alone is what a filter, but ideal op-amp is not a filter. Okay, op-amp by itself is what a filter. In fact, it is what a low-pass filter, but in the non-ideal case. But here, the entire discussion is based on what the ideal op-amp. So ideal op-amp by itself is not a filter, but when you combine this ideal op-amp with resistors and capacitors, then you can make all sorts of filters like low-pass, high-pass, band-pass, band-stop, and also all-pass filters. Okay, so it is also an important topic under this heading. What heading? Ideal op-amp and its applications. Okay. So the plan for today's session is the following. So first, we'll quickly review what are all the important points that you need to know with respect to ideal op-amp in negative feedback. Then we will jump into what problem solving. So we're going to solve plenty of problems, and towards the end, you will gain enough confidence to score full marks in the upcoming GATE exam. So that is the motto. Okay. So before I dive into the actual subject, let me quickly draw your attention towards the offline course at our home institute in Hyderabad. So our very first batch for next year's GATE, that is GATE 27, is going to start on 26th Feb, which is roughly 10 days after the upcoming GATE exam. Okay. So for anyone who is ready to come to Hyderabad, this is a very, very good platform for your preparation and also learning a lot of things along the way and gaining confidence in all subjects and become an overall better personality. Okay. So it helps you not just for GATE. There are a ton of things on which you'll improve upon once you join this, offline course. And for college going students, especially the ones who are in second and third year, I'm sure most of you will be in some kind of dilemma, what sort of career option that you have to make. Okay. So one option that is always open for anyone is what the IT side. But IT side is not that stable and all of that. But I won't get into those things. But for anyone who is inclined towards exploring something in the core domain, whether it is electrical or ECE, a very good opportunity is to be a part of this offline summer crash course. Okay. And the first batch for summer crash course is going to start on May 13th. So the summer crash course will be during the summer semester break. Okay. So I'm sure by April end or May first weekend, your semester gets over. So after that, you can just come to Hyderabad. You can attend classes. You can just enjoy the city, and during the process, you can learn so many things. Okay, so it is going to be a huge learning experience. Okay, and you can then decide that getting into core sector is indeed the best decision that one can take. Okay, so you can decide with confidence. Okay, and there are a bunch of discount options for students from NITs, students from university colleges, and so on. Okay, you can visit our website www.homeinstitute.com for more details. Okay, also we have a live course again for GATE 27 and 28. This is also targeted mainly for college going students. Our very first live batch is going to start on 2nd February. I think hardly 1 week from now. Okay. So you can go to homeinstitute.live to find out more about this live course. So thank you for the attention. Now let's dive into the discussion. I hope everyone is ready. How many classes in series of analog? There will be at least 4 sessions. Okay, and each session will be for approximately 4 hours. So 4 times 4 is 16. So it's very much a crash course which will cover every important topic related to this subject. Okay. So if you participate in these sessions, there are two definite outcomes. Okay, one, you will become very good in problem solving. Number two, your conceptual clarity will will go to the next level. Okay, so these are the two guarantees from my side to anyone who is going to seriously participate in this series of sessions on analog circuits. And based on the response, I get for analog circuits, I'll plan for EDC and maybe networks. Okay. Also based on my own commitments, we'll take a call. So what is op amp? So very quickly, so op amp is what a differential amplifier. It has two input terminals that are marked plus and minus. At the two input terminals, you can apply two different voltages. Let's say I apply some voltage V1 at plus input terminal, you apply another voltage V2 at minus input terminal. And the op amp is what a voltage amplifier. It will have some voltage gain, which is some A. And then on the other side, you have the output terminal, where the output voltage is denoted by V0. So what will the op amp do? It will simply compute the difference between the voltages applied at its two input terminals. Okay, this potential difference, we call it VD. This VD, which is V1 minus V2, okay, gets multiplied with the gain of the op amp, and the product will appear at the output. That's all. This is the only thing you need to know about the op amp as far as this discussion is concerned, which is on ideal op amp and its applications. Okay, so V0 is equal to what? A times VD. So A times V1 minus V2. So this is what the op amp does. There will be two input voltages, and the op amp will compute the difference, and that difference will get multiplied with the gain of the op amp, and the product will appear at the output. Okay, fine. And for this ideal op amp, there are three important properties. Number one is what? The gain of the op amp is infinite. Okay, ideal op amp, has infinite gain. And also for the ideal op amp, which is nothing but what? Ideal voltage amplifier. Op amp is what? Voltage amplifier. So ideal op amp means what? Ideal voltage amplifier. And voltage amplifier means what? You will apply some input voltage. Output also would be what? A voltage which is proportional to what? The applied input voltage. Because the output voltage depends on the input voltage, voltage amplifier can be thought of as what? A voltage controlled voltage source, where the input voltage will control the output voltage. So look at this. Op amp is what? A voltage amplifier, and every voltage amplifier can be modeled or thought of as a voltage controlled voltage source. So combining these two, I can say ideal op amp is nothing but ideal voltage controlled voltage source. So ideal op amp is also what? An ideal VC Vs. And for any ideal voltage amplifier, the input resistance must be infinite. Okay, even for ideal op amp, which is also what? An ideal voltage amplifier, the input resistance is what? Infinite. What is that input resistance? When you look into the input port, what is the equivalent resistance you are going to see? That is nothing but the input resistance. Okay, so if I can just draw an amplifier, any amplifier will definitely have an input port, not just the op amp. So for the op amp, anyway, there are two input terminals. So the input port will be across what? The two input terminals. So when someone looks into this input port, whatever equivalent resistance that you are going to see is nothing but the input resistance. Okay, so R equivalent seen looking into the input port is what we call the input resistance. And if this op amp is ideal, then its input resistance is what? Infinite. Infinite resistance is what? An open circuit. That means what? For anyone looking into the input port of the op amp, he or she will only see what? An open circuit. So when you look into the input port, what do you see? Nothing. You'll see what? An open circuit. What is the current flowing through an open circuit? Zero. Open circuit, there's no path for current to flow. Current has to be zero. Okay. So the moment you come across the phrase ideal op amp, one of the first things that should come to your mind is what? That for that ideal op amp, at the two input terminals, the currents are 0. And that is because the input resistance is what? Infinite. Okay, fine. So number one, gain is what? Infinite. Number two, input resistance is also what? Infinite. As a consequence of which, the two input currents are 0. Remember, only at the two input terminals, the currents are 0. At the output terminal, any current can flow in any direction. Okay. There's also this output terminal, right? So at the output terminal, any current can flow in any direction. When I say any direction, what it means is positive current can flow into the op amp at the output terminal, or a positive current can flow out of the op amp as well at the output of the op amp. Of course, whatever current flows at the output terminal of the op amp, that current will be drawn from the power supply. Usually for the op amp, there will be two power supplies, a positive supply and a negative supply. Okay, so whatever current is going to flow at the output terminal, that current at the output terminal will be drawn from one of the two power supplies. Will be drawn from one of the two power supplies. And the next point is what? With regard to the output resistance, again, ideal op amp means what? Ideal voltage amplifier. Ideal voltage amplifier output resistance is what? 0. Now, R out, if it is 0, it actually means what? The output port, it behaves like ideal voltage controlled voltage source. So these are the only three properties of ideal op amp that you need to know for this particular discussion. There are other properties as well for ideal op amp. Okay, for example, ideal op amp, the slew rate is what? Infinite. Bandwidth is what? Infinite. Yes. And input bias current is what? 0. Input offset current is what? 0. Input offset voltage is what? 0. Power supply rejection ratio is what? Infinite. CMRR, common mode rejection ratio, is what? Infinite. So there are a bunch of other properties as well for the op amp, but those are not required as far as this discussion is concerned. Okay, I hope these three things are clear. I mean, these are very trivial points. Okay, anyone who has even the minimum degree of familiarity with the op amp will be knowing these three things. Okay. Yeah, if there is any problem, you just let me know in the chat box. I'll keep checking it from time to time. Okay. Every 15-20 minutes, I'll take a look at it. So that's the ideal op amp. And I told you what, most of the op amp circuits are based on negative feedback. Okay. You see this ideal op amp, it can be used in three configurations. Okay. The most commonly used configuration is what? Negative feedback. Okay. So what is that negative feedback? One thing you can say is what? The output of the op amp is connected to what? The negative input terminal. But that does not always guarantee negative feedback. The more fundamental way to say it is what? This op amp should be part of a loop, and for that loop, the loop gain has to be negative. Repeat, the op amp has to be part of a loop, and for that loop will have what? Loop gain, which is what? Gain around the loop. So that loop must have a gain that is negative. So any op amp that is part of a loop that has a negative loop gain, that op amp is also said to be in negative feedback. Now on that loop, there can be any number of op amps, not just one op amp. Okay, so you can have a loop that has, let's say, 3 op amps, and for that entire loop that has got 3 op amps, the loop gain is what? Negative. What it means is each and every individual op amp that is part of that loop that has a negative loop gain will also be in negative feedback. Okay, so ideal op amp in negative feedback, that is the most commonly or most widely used configuration for op amp. Okay, and some rare cases this ideal op-amp is also used without any feedback, in which case this ideal op-amp behaves like a comparator, okay? And in some cases, the same ideal op-amp is also used in positive feedback, and that circuit is called as Schmidt trigger, okay? So Schmidt trigger also is some kind of a comparator, but the only difference is what normal comparator, no feedback. Schmidt trigger, it has got positive feedback, okay? So this comparator and the Schmidt trigger and its applications, we are going to discuss in the next session, okay? So in this session, we'll only focus on the first configuration, which is negative feedback. We look at every possible circuit that you can have using an op-amp in negative feedback. And more importantly, how do you go about the analysis of any such circuit, okay? So to be frank, there is actually nothing, okay? It is not a very extensive topic as such. There's only one little thing that you need to know to get through this entire discussion, and that is what the concept of virtual short, okay? So whenever you have an ideal op-amp connected in negative feedback, it is all about the application of virtual short, okay? So this combination, okay, ideal op-amp connected in negative feedback will always result in something called virtual short. What is that virtual short? This op-amp has two input terminals, okay? So the two input terminals, it is as if they are shorted together. So generally, if any 2 points are shorted together, then those 2 points will be at same potential. Same here. For the op-amp also, there are two input terminals, right? So let's say the voltage at the plus input terminal is what? V plus. And the voltage at the minus input terminal is what? V minus. And if this op-amp is what? Ideal. And if it is connected in what? Negative feedback, then we have this concept of virtual short, which is true. And this virtual short, it only means what? Both the input terminals are at same potential. If this input terminal is at 1 volt, then due to virtual short, this will also be at 1 volt. If this is at 0, this will also be at 0. So it is simply the fact that both input terminals of the op-amp will be at same potential. That is what is meant by virtual short. And when will virtual short be valid? Under these two conditions. Number one, the op-amp has to be ideal. Number two, that ideal op-amp has to be connected in negative feedback, okay? And there is one exceptional case where this virtual short will kind of fail, okay? See, first of all, what is the definition of op-amp, okay? What is the definition of op-amp? Definition of op-amp, it means what? Output-input relation, okay? It is simply V naught equal to what? A times Vd, where Vd is what? V plus minus V minus, okay? So it's a classic linear relation between the output and the differential input voltage Vd. So if you plot V naught versus Vd, okay, which is also called the voltage transfer characteristic. So what is it? There is an op-amp, and the potential difference between the two input terminals is what? Vd, and the output voltage is what? V naught. And any op-amp will be connected to what? Generally, any op-amp will be connected to what? Two power supplies, two DC power supplies, plus Vsat and minus Vsat, okay? So these supply voltages, they limit the range of V naught. If not for the supply voltages, this value of V naught, the output voltage, can take any value from minus infinity all the way up to plus infinity. Okay. But because of the finite power supplies, which can be like 10 and minus 10, the range of V naught is limited to what? The two supply voltages. Okay, so this V naught always lies in the range minus Vsat to plus Vsat. So V naught cannot be more than plus Vsat. V naught also cannot be less than minus Vsat. So this V naught is limited to this range between the two supply rails, okay, negative supply rail and the positive supply rail. Now V naught equal to A times Vd, which is like y equal to mx, which is obviously a straight line passing through origin with a slope of m or a slope of a in this case. So this V naught equal to A times Vd. So as Vd becomes more and more positive, by the way, this slope is what? The gain of the op amp, which is A. Okay, so higher the gain of the op amp, higher the slope. Now when it comes to ideal op amp, A is what? Infinite. So this yellow color line is actually going to have infinite slope. In fact, it will coincide with the y-axis. Okay. So anyway, so let's take the more general case where the gain is what? Some finite value, which is usually quite large. Okay. So as Vd becomes more and more positive, V naught also becomes more and more positive because V naught is what? A times Vd. As V naught becomes more and more positive, at some point V naught can reach what? Plus Vsat. Now beyond this point, even if Vd increases, V naught will no longer increase. Output gets saturated. Okay. Similarly, if Vd is negative, and the more negative Vd is, the more negative V naught will be. So if Vd becomes more and more negative, V naught also becomes more and more negative. So at some point, V naught will reach what? Minus Vsat. Once V naught reaches minus Vsat, beyond that point, even if Vd becomes more negative, V naught will not change anymore. V naught remains constant at minus Vsat. Okay, so this is the typical voltage transfer characteristic of an op amp. Okay, so if you look at the plot as a whole, if you look at this plot as a whole, and if I ask you, is this element linear or non-linear, then your answer has to be non-linear. Okay, because for anything, for any system or for any circuit to be linear, yes, output must be linearly related to the input for any value of input. Okay, but here output is linearly proportional to input only in this range. Outside this range, output is no longer proportional to input. Yes, output becomes constant or saturated to plus Vsat. Even to the left of this, when Vd becomes more negative, there will be no change in V naught. So output is not really proportional to the input Vd. Okay, so output is proportional to the input Vd only in this range where it is what? The straight line passing through origin. So here output gets saturated. It is kind of independent of the input. Here also the output gets saturated. So if you look at the plot as a whole, and then if you try to decide whether the op amp is what? Linear or non-linear, definitely it is what? Non-linear. Okay, because for a system that is strictly linear, that voltage transfer characteristic or the plot has to be a single straight line passing through origin. Yes, it has to be one single straight line passing through origin, but here clearly that is not the case. Okay, fine. But as long as your Vd is such that, let's say there is some V1, there is some V2. So if the value of Vd lies in between V1 and V2, yes, then your op amp is operating on this middle segment where you can say the op amp is what? Linear. You understood, right? Yes. So in that sense, op amp is what? Linear. Now our op amp is what? Ideal. Our op amp is what? Ideal. Ideal op amp has infinite gain. So when you plot V0 versus Vd for ideal op amp, it will be something like this. Okay, same as the earlier plot, but in the middle, instead of finite slope, it is now going to have infinite slope. And that infinite slope is nothing but the infinite gain. Okay, so once again, on the positive side, it is plus Vsat. Negative side, it is what? Minus Vsat. Okay. Now for this segment, what is the value of Vd? It is 0. Virtual short also tells us what? V plus and V minus are equal. Yes or no? Virtual short tells us what? The two input terminals are going to be at same potential. When the two input terminals are at same potential, then what is the difference between the two input terminals? It is 0. Yes. So our ideal op amp, when connected in negative feedback, will operate on this middle segment. Now, if you look at this middle segment, what is the output? Output can be any value in between minus Vsat and plus Vsat. Yes or no? When the op amp is connected in negative feedback, of course the op amp is ideal. Then we have what is called virtual short, which forces V plus to be equal to what? V minus, which in turn results in Vd being equal to what? 0. So when Vd is 0, you are operating on this middle segment, which coincides with y-axis. Now, if you look at the middle segment, your output voltage can be any value. That is the point. Okay. So under virtual short condition, even though Vd is always 0, but the output voltage itself can be any value in between minus Vsat and plus Vsat. Okay. Now if the output gets saturated, which means it can operate anywhere on this segment or on this segment. Yes. In that case, let's say the output is what? Plus Vsat and is operating here. Then what is Vd? It is this much. Look at this value of Vd. It is not 0. Vd is some positive value, and then the output is what? Plus Vsat. Or let's say Vd is what? This much, and then the output is what? Like minus Vsat. Okay, so when Vd is 0, the output voltage can be any value in between minus Vsat and plus Vsat. Okay, so this is kind of the reason why virtual short is valid only as long as the output is not saturated. Okay, so once the output is saturated, which means your operating point is on this segment or on this segment, in both the cases, the value of Vd is not 0, which means V plus is not equal to V minus. Okay, so that is one exceptional case where even though the ideal op amp is connected in what? Negative feedback, still virtual short will not be valid. And that is when output gets saturated. Okay, so as we go along, we'll look at examples where the output gets saturated, and that will lead to what? The virtual short not being valid. Okay. Okay, fine. I think this is everything. I mean, this is the kind of background. What will if gain is less? No, if gain is less, then the slope will be smaller. Then you require a much larger value of Vd for the output to get saturated. Okay. But if the gain is finite, definitely virtual short will not be valid. Okay. Virtual short will be valid only when your op amp is not ideal and also connected in negative feedback. Okay. So if op amp is connected in Nagendra is asking if op amp is connected in positive feedback, then it is linear or non-linear? Non-linear. Definitely non-linear. Yes, op amp, if it is used in positive feedback or even in no feedback case, where it acts like a comparator, op amp, the overall circuit is not linear. Okay, linear means what? Output of the circuit must be linearly related to the input. Okay, but I told you what op amp in positive feedback will act as what? A Schmidt trigger. Okay, So I'll just do one thing. So just to answer his question, okay. So his question is, if there is an op amp and the op amp is connected in positive feedback, then the overall circuit, is it linear or non-linear? That is the question. Okay, we'll look at all the three cases. So let's say you have an op amp. So let me draw a simple circuit like an inverting amplifier. Okay. So all of you know this is what the inverting amplifier. And if the op amp is ideal, then the gain of the inverting amplifier is what? Minus R2 by R1. So what is the output in terms of input? V naught equal to what? Minus R2 by R1 times Vi. This is minus R2 by R1. Is it not a constant? Okay, it is a negative constant, but it is still what? A constant. Okay, I can call it some K. Then I can write V naught as what? Some K times Vi. Correct or not? I can write V naught equal to what? K times Vi. What is this V naught equal to K times Vi? Output is proportional to input. Any system or any circuit in which the output is directly proportional to the input is definitely what? A linear system. Okay, so here this inverting amplifier circuit, it is what? Linear, because the output is linearly related to the input. Okay, so if you plot, for example, V naught versus Vi of this inverting amplifier, it is a straight line passing through origin with a negative slope whose value is what? Minus R2 by R1. Okay. The same op amp, if it is connected in positive feedback, okay. Let's say some input is applied at the minus input terminal, and then you have R2 and R1. So through this resistive network, the output is connected to what? The plus input terminal. So clearly, the output of the op amp is connected to what? The plus input terminal, which means this op amp is connected in what? Positive feedback. I've said this a couple of times already, that any ideal op amp that is connected in positive feedback will act as what? A Schmidt trigger. ST means what? A Schmidt trigger. And you know, for any Schmidt trigger, we always try to plot V naught versus Vi. So what is that? V naught versus Vi plot for a Schmidt trigger. For this circuit, which is a standard Schmidt trigger, the V naught versus Vi plot will be like this. Understood? There is a kind of V naught versus Vi plot that you will have for any Schmidt trigger. For this particular circuit, this is the exact plot. Okay. And the two trip points, BV sat minus BV sat. The output is always either plus V sat or minus V sat. Whatever it is, just look at the V naught versus Vi plot. From the plot between V naught and Vi, we can directly tell it is what? Non-linear. For any system to be linear, when you plot output versus input, yes, it has to be a straight line passing through origin. It is not a single straight line at all. It has got many straight lines, and also none of the straight lines is passing through what? Origin. Yes or no? Previous case, inverting amplifier, V naught versus Vi plot, it is what? A proper straight line passing through origin. That is what you require for linearity. But here, it is not a straight line. It is also not passing through origin. So that means what? The Schmidt trigger as a circuit is what? Non-linear. Inverting amplifier, linear. Schmidt trigger, non-linear. So what are the two cases we have seen? Here, see, in both these circuits, this circuit and this circuit, the op amp is what? The same ideal op amp. But here, it is connected in what? Negative feedback. But here, it is connected in positive feedback. Yes. So when you connect an ideal op amp in negative feedback and the output is not saturated, then the op amp will actually operate somewhere on this middle segment. So as long as the op amp operates on this middle segment, the op amp circuit is always going to be linear. So the moment the operating point will jump onto either this line or this line, yes, then the overall circuit will become non-linear. Okay. But our scenario, we can say something like this. Ideal op amp connected in negative feedback, overall circuit is what? Linear. Ideal op amp connected in positive feedback, overall circuit is what? Non-linear. Yes. And what about ideal op amp without any feedback, which is what? The comparator. Even comparator is what? Non-linear. Okay. So comparator also is what? Non-linear. Okay. How to check for type of feedback for an op amp if resistors are connected across both input? Yeah. I mean, there is a very common case that we encounter, okay, where the output of the op amp is connected to both minus as well as plus input terminals. In such a case, how do you determine whether the op amp is in negative feedback or not? Okay. Since you brought it up, I'll quickly explain, but after that, we'll jump into problem solving. Okay. So this question is this. There is some, 1 second. Yeah. So there is some op amp. Let's say there is a plus input terminal, there is a minus input terminal. So it is not compulsory that the output of the op amp should be connected to only one input terminal. The output of the op amp can be connected to both input terminals at the same time. Okay. So let's say you have yeah, the answer is loop gain. Okay. You can always find the loop gain and decide whether the feedback is what? Negative or positive. Okay. So in this case, as you can see, the output of the op amp is connected to what? Plus input terminal. It is also connected to what? The negative input terminal. So in such a case, what is the type of feedback for the op amp? Or what is the net feedback for the op amp? It will have some positive feedback. It also has some negative feedback, but net feedback will be what? Either positive or negative. So it is a net feedback that is important when trying to decide whether virtual short will be valid or not. For virtual short to be valid, it is net feedback that has to be negative. Okay. So the way we do it is, let me just clear this off. we just break the loop at the output of the op amp. This is what we normally do. Okay. So I just take a pair of scissors and cut the wire here. When I cut the wire here, then the output of the op amp is not connected back to what? Any of its input terminals. Now the op amp does not have any feedback. Okay. So when I cut the wire and sort of break the loop, I'm going to get 2 points here. Yes or no? I have a wire initially in this place and then I cut the wire. Then I get 2 ends, right? These are the 2 ends. Okay, the broken wire will have 2 ends. So these are the 2 ends. Okay. Now at one of the points, I inject a signal into the loop. Okay. So at this point, I inject a signal into the loop. I'll call it VT. Now this VT will sort of go around the loop and come back at the other point. So whatever goes around in this VT, when it goes around the loop and comes back at this point, whatever comes back is called the return voltage. So you have a loop which is initially intact. Okay. Now you cut the loop and now the loop is what broken. So when you break the loop, you'll have 2 points or 2 ends. Okay. At one of the ends, you inject a signal into the loop. Yes, and that signal will go around the loop and come back at the other side. So what is being injected into the loop? VT. What is coming out at the other side? V return. So it is as if you have a loop for which the input is what? VT and the output is what? V return. Output by input is what? Loop gain or the gain of the loop. And it is the sign of the loop gain that will tell you whether feedback is what? Negative or positive. If the loop gain is negative, feedback is negative. If loop gain is positive, then feedback is also positive. And while finding loop gain or while determining type of feedback, all independent sources you have to make them 0. So as Vs1 you make it 0, Vs2 also you make it 0. When you make any voltage source 0, it becomes short. This also becomes short. So what is loop gain for us? Gain around the loop, which is V return divided by Vt. So when you apply Vt here, this entire thing is what? Same node. Here also it is what? Vt. Here also it is what? Vt. Assuming op amp is ideal and so on. Ideal op amp, both the input currents are 0. When this becomes short, this point is shorted to ground. This point will be at 0 potential. Even this point is shorted to ground. This will also be at 0 potential. Now because this current is 0, this current and this current both will be equal. In other words, R and R will be in series between Vt and ground are 0. So the voltage at this point from voltage division will be what? Vt by 2. Even at the bottom, because this input current is what? 0, this current and this current will be equal, which means 2R and R are also in series between Vt and 0. So again, from voltage division, the voltage at this point will be what? Vt into R by R plus 2R, which is Vt by 3. So what is this Vt by 2? It is actually what? Voltage at the plus input terminal. What is Vt by 3? It is the voltage at the minus input terminal. Okay. And whatever we return, we are trying to find is nothing but the output voltage of the op amp. Here, if you want, you can assume the gain of the op amp to be some A. Now, what is the definition of op amp? Output is equal to what? The gain times V plus minus V minus. Okay, so V return is what? A times V plus minus V minus. What is V plus? Vt by 2. What is V minus? It is Vt by 3. That's all. What is 1 by 2 minus 1 by 3? 1 by 6. So this V return, you can write it as AVT by 6. But what are we trying to find? We are trying to find the loop gain, which is V return by Vt, which is A by 6. So look at the loop gain. It is clearly positive. Yes or no? A by 6. It is positive. If loop gain is positive, yeah. Yes, if loop gain is positive, it implies the feedback is also positive. Okay. In fact, if your objective is only to find whether the feedback is negative or positive, you don't even have to find the value of the loop gain. Here itself, you can simply compare V plus and V minus. Okay. So what is V plus? It is Vt by 2. What is V minus? It is Vt by 3. Clear or not? Yes. Now, which is bigger? Vt by 2 is definitely greater than Vt by 3. That means V plus is more than V minus. That way also you can directly tell that the op amp is in positive feedback. Okay, no need to find the exact value of the loop gain. So what is this method essentially? So just imagine, you don't even have to break the loop. Just imagine at the output of the op amp, you have applied some voltage Vt, and then you make all the other independent sources 0. Now you try to find the voltages at the two input terminals, that is what V plus and V minus, in terms of whatever Vt you have applied at the output. Once you find V plus and V minus in terms of Vt, like Vt by 2 and Vt by 3, then you simply compare V plus and V minus. Whichever is bigger, that is the type of feedback. Like in this case, V plus is more than V minus. That means op amp is in positive feedback. If V minus turns out to be greater than V plus, that means op amp will be in negative feedback. So here, what if voltages have same potential while finding loop gain? No feedback. If V plus and V minus are equal, yes, during this analysis where you are trying to determine the type of feedback, if V plus and V minus turn out to be equal, that means there is no feedback at all. Loop gain is 0. This on loop gain 0, no feedback. Okay. So no feedback, it means what? Op amp behaves like comparator. Okay. Positive feedback, the overall circuit will act like some kind of Schmidt trigger. Okay. So anyway, that is the how do sources get grounded to 0? Because see, we are finding loop gain. Loop. See, you have a loop. You are only finding the gain of that loop. Okay. Gain means what? Output divided by whatever is the input applied. What is the input applied in this analysis? Vt. So every independent source will act as what? Input. Yes or no? Every independent source will act as what? An input. So while finding loop gain, the only input that must be present is what? Vt, which you apply after breaking the loop. So all other independent sources, you should make them 0. Every independent source is like some kind of an input. Okay. So the only input is what Vt, and the output is what V return, and the ratio of V return to Vt is what we call loop gain. Okay, Banu is asking, Banu only, right? How to solve questions in positive feedback if virtual short concept is not valid? There is a separate discussion in the next session, not this one. The next session, we will look at Schmidt trigger. Yes. So once you know how to analyze Schmidt trigger, that will answer your question. Okay. So this much. So one more point, since I discussed up to this point, always the loop gain will be of the form plus or minus AB. Loop gain will be of the form plus or minus AB. Okay. So this loop gain also you can compare it with A times B. So what is the actual loop gain? A by 6. But what is this general form of the loop gain? A times B. So when you compare A by 6 with AB, clearly it means B is what? 1 by 6. And you know this B is what we call the feedback factor. Yes. So what is B here? 1 by 6. It means what? On the whole, 1/6 of the output is going to be fed back to the input. That is the meaning of the feedback factor being 1 by 6. Okay. Yeah, definitely. So this much review is enough. Let's start solving problems. I hope you are able to see the question. I mean, the font size is big enough, I hope. So, given figure shows a non-inverting op-amp summer with V1 equal to 2 volts. So, there is one input 2 volts, V2 equal to minus 1 volt. Okay, this is the other input minus 1. The output voltage V0 is. Okay, in all these circuits that we are going to encounter, even if it is not given, please understand op-amp is what ideal. Okay. So, and whenever you come across ideal op-amp in negative feedback, we just use the concept of virtual short. That is what we will be doing throughout this session. Okay. So, output of the op-amp through 2 are connected to what? Negative input terminal, op-amp in negative feedback. So, virtual short is valid. So, what is that virtual short? V minus and V plus both are equal. Okay. Also for ideal op amp, this input current and this input current both are 0. If you have V0 here, here also it is what V0. Because this current is 0, this current and this current both are equal. That means 2R and R both are in series between V0 and ground. So what is the voltage at this point in terms of V0? V0 into R by R plus 2R, which is V0 by 3. Now because of virtual short, if V minus is V0 by 3, then V plus will also be V0 by 3. Okay, that's all. All you have to do now is to write KCL at this node. Okay, we'll just change the color. What is this current? I mean, you can take any direction for the current. What is this current? 2 minus this V0 by 3 upon R. What is this current? Minus 1 minus same V0 by 3 upon R. What is this current? V0 by 3 minus 0 by R. Okay. So at this node or at this point, from the left, two currents are entering. At the bottom, one current is leaving. So sum of these two currents will be equal to what? This current. I'm just writing KCL at this point. Okay. So 2 minus V0 by 3 upon R plus minus 1 minus, sorry. Minus 1 minus V0 by 3 divided by R is equal to V0 by 3 minus 0 by R. So V0 by 3 minus 0 by R. So R is common throughout. R will get cancelled out. Minus V0 by 3 minus V0 by 3 will go to the other side. 3 times V0 by 3 is what? 3 V0 by 3, which is V0. 2 minus 1, I am getting V0 equal to 1 volt. Good, very good. Let's move on to the next question. In the given circuit, this circuit, if the voltage input V minus, okay, so V minus is one input voltage and V plus, this is the other input voltage, are to be amplified by the same amplification factor. Okay, the value of R should be how much? Okay, fine. See, first of all, op amp is what? Ideal. Okay, and once again, output through 22K is connected to what? The negative input terminal. Ideal op amp connected in negative feedback. Once again, it is just about the application of virtual short. So how many inputs are applied to this circuit? Two inputs, V minus and V plus. Op amp in negative feedback is what? A linear circuit. So the output will definitely be a linear combination of the two inputs. Okay. So V0 will be what? Some K1 times V minus and some other constant K2 times V plus. Okay. Say from V minus to the output, the gain will be negative. Why? Okay. From V minus to the output, the gain will be negative. but from V plus to the output, the gain will be positive. So from V plus to the output, the gain will be positive. So this is negative gain, this is positive gain. So what it means is K1 times V minus, right? So this K1 will be what? Some negative value. K2 times V plus, but this K2 will be what? A positive value. So what is the amplification factor for input V minus? It is K1. What is the amplification factor for the other input V plus? It is K2. According to the question, the two inputs should get amplified by the same factor. What it means is, see, K1 and K2 cannot be equal because one is negative, the other one is what? Positive. The only sense in which both can be equal is in terms of magnitude. Okay, so what is implied by the question is what? That mod K1 and mod K2, I mean K2 is already positive, so mod K2, I mean K2 itself is positive. Okay, so mod K1 and mod K2 both are equal. That is the thing. Okay, we'll just use superposition. I mean, you can also do it without superposition. Okay, so in the first case, V plus, I'll make it 0. Okay, I'll keep V minus active. When I make V plus 0, what is this current? It is 0. Now this is 0, this is 0. Now 15K and R both are in series between 0 and 0. Between 0 and 0, what is the current? 0. So what is this current? 0. What is this current? 0. 0 current means 0 drop. This is 0, drop 0. So what is the voltage here? 0. Now V plus is 0 due to virtual short. V minus is also at 0. Again, for ideal op-amp, this input current is also at 0. Again, you can write KCL at this point. So what is this current? V minus 0 by 10K. What is this current? 0 minus V naught by 22K. Again, this is what? An inverting amplifier whose gain will be what? Minus 22K by 10K. Okay. So V naught will be minus 22K by 10K is what? Minus 22 by 10, which is minus 2.2 V minus. Okay. So that is the output when only V minus is present. Let us find the output when only V plus is present. Okay. So in this case, V minus will make it 0, but V plus will just let it remain. Again, what is this current? It is 0, because of which this 15K and this unknown resistance R will both be in series between V plus and ground. So I can use voltage division to write down the voltage at this point, which will be V plus into R upon R plus 15K. So V plus times R upon R plus 15K. Okay. In fact, the remaining circuit is actually what? The non-inverting amplifier. This you can imagine this ground. Okay. So if you look at this circuit, yes, there is the output, there is like R2, there is like R1, and this voltage at the plus input terminal is like the input voltage to the non-inverting amplifier. Non-inverting amplifier, what is the gain? 1 plus R2 by R1. Otherwise, this voltage will also appear here, and then you can write KCL here. That is also one way to do it. Okay. Anyway, since we already identified this to be what? Non-inverting amplifier, I'll just use the result. So V naught in terms of this will be what? This times the gain of the non-inverting amplifier, which is 1 plus R2 by R1. Again, R2 by R1 is what? 22 by 10, 2.2. 1 plus 2.2 is what? 3.2. So V naught will be what? 3.2 R upon R plus 15K times V plus. So what is the amplification factor for this input V plus? This multiplying factor for V plus, which is 3.2 R upon R plus 15K. What is the amplification factor for V minus? It is minus 2.2, but magnitude is what? 2.2. Now our requirement is what? Both the inputs should get amplified by the same factor, which means just equate this to what? 2.2. Okay. I'll just do it here. 3.2 R upon R plus 15K is equal to 2.2. Because I already told you, you can only equate the magnitudes because this gain is what? Positive. This gain is what? Negative. Okay, so only in terms of magnitude they can be equal. That's all. Now the only unknown is what? R. You can solve for R. Okay, so 3.2 minus 2.2. What is 3.2 minus 2.2? 1. This is the expression for R. Okay, 2.2 times 15k. What is 2.2 into 15? I guess 33. 33, right? Yeah. So what is the answer? This value of R must be what? 33 kilo ohms. Okay, so R must be 33k. In that case, what will the output be? In that case, what will the output be? What will the output be? Output will be 2.2 times V plus minus V minus. This is one way to do it. But if you know the difference amplifier, if you know difference amplifier, isn't this circuit a difference amplifier? Yes or no? V plus and V minus are like the two inputs. Yes. If you recall difference amplifier, this is R2, this is R1, this you can call it R4, this you can call it R3. What is the condition for difference amplifier to be ideal? R2 by R1 must be equal to what? R4 by R3. Yes, and only in such a case, V0 can be written as what? Something times this minus this. And the difference amplifier is said to be ideal. Okay, so if I use that condition for difference amplifier to be ideal, I don't have to go through all this analysis. I hope it is clear. Okay, so what is the condition for difference amplifier to be ideal? You know, R2 by R1 equal to what? R4 by R3. Already R2 by R1 is what? 22k by 10k, which is 2.2. And R4 is what? This unknown resistance R. R3 is what? 15k. This way also directly will get, in one step, directly I'll get R as what? 15k times 2.2, which again is what? 33k. I hope both the approaches are clear. Okay. Okay, look at the next question. The differential input resistance of the circuit shown in figure. So this, is what? Some kind of a difference amplifier for which the two inputs are what? V1 and V2. So there are two different inputs that are applied to this circuit in the form of V1 and V2. Okay. So where is the input port for this overall circuit? This is the input port. This is the input port. Yeah. This is the input port. So when you look into this input port, whatever equivalent resistance you see, that is nothing but the input resistance. And I can also call it the differential input resistance because the circuit has got two input terminals, and this amplifier will try to compute and amplify the difference between V1 and V2. Yes, the input resistance, I can call it the differential input resistance. That is what we actually need to find, okay, which is quite simple. So if you have any amplifier, how do you find the input resistance? Across the input port, you just have to connect a test voltage source and find VT by IT over. So here we have identified the input port. After identifying, after identifying the input port, now across the input port, you connect some voltage source. We call that voltage source as what? Some VT. and let the current flowing out of the plus terminal be some IT, and whatever input resistance we need to find is simply the ratio of VT to IT. Again, op-amp is what? Ideal, it is connected in what? Negative feedback, because the output through RF is connected to what? The negative input terminal. Okay. Negative feedback will lead to what? Virtual short. What is that virtual short? This point and this point will be at same potential. If both are at same potential, what is the potential difference between the two input terminals? You can say it is what? Zero. Okay. Now what is this current? If this current is IT, then this current is also what? IT. Now if you look at this R1, what is the current through this R1? IT from left to right. That will result in a drop of IT times R1 with this polarity. Look at this R1, through this R1 also the current is what? IT, but it is flowing from right to left, and the resulting voltage is what? IT times R1, and its polarity will be what? Plus minus. Correct or not? Now if you look at this, please observe, are we not having some kind of a loop here? This one on the left side we have a loop. For any loop you can always write KVL. So if you write KVL around this loop, let's say I start at this point. If I write KVL around this loop starting from this point, minus VT, and then plus, what is the drop? IT times R1. And then because of virtual short, this potential difference or this voltage drop is what? Zero. I won't write zero term. And again you have what? Plus IT times R1. Now you are back to the starting point. Equate this sum to what? Zero. That's all. This is the only thing you need to do. So from this, can't we see that VT is equal to what? 2 IT R1. So what is VT by IT? IT comes to this side. 2 R1 will remain on the other side. That is what is the answer. That is the differential input resistance. Or even without writing KVL, you can, you should be able to see that you have some kind of a loop here. And for this loop, the loop current is what? IT. And in this loop, the only voltage source that is present is what? VT. And in this loop, you got two resistors in series, R1 and R1. So what is the loop current? The net voltage in the loop divided by net resistance in the loop. Now for this loop, the only voltage source is what? VT. Divided by net resistance in the loop is what? R1 plus R1. So directly we can write the loop current IT as being equal to what? VT divided by 2R1. So if you write IT, which is what? Some kind of loop current, which is equal to VT by 2R1, directly you'll get VT by IT as what? The same 2R1. Either way, the differential input resistance is what? 2R1, which is option C. Moving on to the next question. So again, you have this op-amp, which is definitely ideal. And if you observe, the output of the op-amp is directly connected toward the negative input terminal, and that is it. Okay, output is not connected to plus input terminal, output only connected toward negative input terminal. So definitely op-amp is in negative feedback. E0 is what? The voltage at the output, E1 is what? This potential difference, I is what? The current through R1. You have to choose what is the correct relation among these quantities. Okay, again this is quite simple. Because output is shorted to this point, the voltage at this point is also what? E0. So because of virtual short, if V minus is E0, then V plus is also what? E0. Again, here you actually have what? An open circuit. Even if you don't have an open circuit, the input current will be what? Zero, which means this current and this current both are equal. That means R1 and R2 both are in series between E0 and ground. So using voltage division, we can write the voltage at this point as what? E0 R2 by R1 plus R2. Now this E1 is what? Potential difference between this point and this point. So E1 is equal to E naught minus E naught R2 by R1 plus R2. That's all. So if you take LCM and so on, what do you get? E naught times R1 plus R2 minus R2 is what? R1. R1 divided by R1 plus R2. I hope this is correct. But my answer is not among the options. Did I make a mistake? Or maybe I think maybe this is correct. See, what is I? What is I? I is actually what? I mean, this I is also what? The current through R2, right? So I is what? E naught minus 0 by, remember, R1 and R2 are in series. So I can be written as E naught divided by R1 plus R2. Now if you go back to the previous relation, E naught divided by R1 plus R2, R1 will come to this side. I can write it as E1 by R1. I think this is correct. So I is what? E1 by R1, which is option D. There is the next question. Yeah. Thank you. So moving on to the next question, again a simple op-amp circuit is given, but this time if you observe, the output of the op-amp is connected to what? Plus input terminal. So this op-amp is connected in positive feedback, not negative feedback. So virtual short will not be valid this time, okay? And you must be knowing that for any ideal op-amp that is connected in positive feedback, always the output of the op-amp will be either plus VSAT or minus VSAT. So positive feedback output will always be either plus VSAT or minus VSAT, okay? So if you really want to pick an option straight away, blindly you can take option D, because that is the only thing which is plus VSAT, which is what the supply voltage. All other values minus 1, 1, 2, these are values in between minus VSAT and plus VSAT. When will the output be some value in between minus VSAT and plus VSAT? When the op amp is in negative feedback. Of course, the output should not be saturated. But here the op amp is not in negative feedback, positive feedback. So directly output will be either plus VSAT or minus VSAT. Okay. But what if among the options you also have minus 15? Okay. Let's say this is not 2 volts. This is minus 15. Now which option is correct? And let us say it is MSQ. I give the same question, but I modify one of the options and I turn the question into what? MSQ. Now what is the answer? Is it still only D, or it could be B or D? You can just check, okay? Remember the output is, the op amp is in positive feedback, which means the output can be anything, either plus 15 or minus 15, okay? Let's say the output is what? Plus 15. Output is plus 15. What is V minus? It is 0. It is always 0 because the minus input term is connected to what? Ground. What is this current? Always 0. Because this current is always 0, these two currents are always going to be equal. So the voltage at this point can be directly written in terms of this voltage and this voltage, okay? We always do this. So if the output is plus 15, what is the voltage here? 15 into R plus 1 into R, which is 16 times R, divided by R plus R, which is 16 by 2, which is 8, okay? You see, if V0 is plus 15, I am getting the value of V plus to be what? 8. V minus, anyway, it is always 0. Does this make sense or not? V plus 8, V minus 0, which is bigger? V plus is more than V minus. V plus more than V minus for ideal op amp, always the output will be what? Plus V sat. So this is definitely possible. Okay, so output can be plus 15. But will the output be only 15, or it could be minus 15 as well? That is what we'll check now. Okay. If the output is what? Minus 15. Now also this current and this current both are equal. So what is the voltage at this point? Minus 15 into R plus 1 into R, which is minus 14 R divided by R plus R. Minus 14 by 2 is what? Minus 7. Okay, so I'm getting V plus to be minus 7. So when V0 is minus 15, I get V plus as what? Minus 7. V minus is what? 0. Again, please look at the values of V plus and V minus. V plus is what? Minus 7. V minus is what? 0, which is bigger. 0 is more than minus 7. That means V minus is more than V plus. If V minus is more than V plus, definitely V0 will be what? Minus V sat or minus 15. This also makes sense. You understood? So if at all, this is the question, then the correct options are both B as well as D. Okay? But again, output cannot be both plus 15 and minus 15 at the same time. You should know this. If this is the input, if this 1 volt is what the input voltage, how exactly that input voltage is changing. Is it increasing or is it decreasing? That will decide whether the output is exactly plus 15 or minus 15. But for whatever is given, if you have to decide what is the output, you can say it will be either plus 15 or minus 15. Okay, that is fine. Moving on to the next question. An integrator circuit. Okay, this is what an integrator. Input RC, output plus terminal connected to ground. Definitely it is what an integrator. The op amp is of type 741, fine, and has an input offset current minus IOS. Minus IOS. What is that input offset current? The difference between the two actual input currents. Yes, ideal op amp, no input currents at all. Okay, but real op amp, there will be some non-zero input currents at the two input terminals, and because of something called mismatch, the two input currents need not be equal. So whatever is the little difference between the two input currents, that is what we call input offset current. Okay. So they are saying that for the op amp, there is this input offset current minus IOS. In fact, the IOS direction is given. Okay, and there is not a proper way of conveying the information. There is not IOS direction. There is not IOS direction. Okay. So okay, C value is given 1 microfarad. R value is also given 1 megohm. If the input Vi, okay, the input Vi is what 1 kilohertz square wave of 1 volt peak to peak. The output V naught under steady state condition will be. You see, the circuit is what an integrator. Integrator will do what? Integrate the input. That is why it is called integrator. Okay. And what is the input? It is a square wave. When you integrate a square wave, you should expect what a triangular waveform at the output. So ideally, output will be a triangular waveform, but that is only in the ideal case. Here, what is the problem for the op amp? It has got some input offset current. So the moment you know that it has input offset current, it also means what? The two input currents are not zero. Okay, in fact, wait. So if you take an op amp, for any real op amp, at the two input terminals, there will be some current flowing. Okay, not the same current, but each input terminal will have its own current. Okay, because inside the op amp, what do you have? Transistors, and this input terminal can be connected to what? Base of some transistor that is inside the op amp, and at the base of that transistor, some current can flow. That current will become what? This input current. That is what is the actual input current. Okay, but the same op amp is made using MOSFET. Yes, then luckily for MOSFET at the gate, no current will flow. In such a case, the input currents are so small that you can say they are what? Zero. Okay. So anyway, at the plus input terminal, the input current is what? IB1. At the minus input terminal, the input current is indicated by IB2. Okay. And whatever input offset current they are talking about is what? The difference between IB1 and IB2. Okay. So IOS, you all know, is actually IB1 minus IB2. Okay. So whatever it is, the output voltage V naught under steady state condition. Okay, fine. You say if not for the input offset current, or if not for the input bias currents, the output would have been triangular. Okay, no doubt about it. And also this input is what? A square wave. Okay, that is some kind of AC thing. It will have several components or frequency components, but it is not DC. Input is not DC. Okay, input has a lot of frequency components. Okay, but this IB1 and IB2, they are constant values. So you can treat IB1 and IB2 as what? DC quantity. Input is not DC. Yes, input is not DC. It is not pure AC as well, but it has got several frequency components. Okay. Now you can think of this as a linear circuit driven by multiple inputs at different frequencies. Okay. One of those inputs is what? Your bias currents IB1 and IB2. Okay, which are like DC. Okay. So if you analyze this circuit for the input bias currents, if you analyze this circuit for the input bias currents, which are both DC, okay, in which case this input you can make it 0. That means it is as if this is shorted to ground. Okay, and assuming the op amp has very large gain, okay, and this is actually IB2. Okay, this is actually IB2. What happens is this. If you assume the op amp has very large gain, and of course the op amp is connected in what? Negative feedback. So if you apply virtual short, V plus is 0. So due to virtual short, V minus is also what? 0. Please understand this. This is 0. Why? Due to virtual short. Okay. This is the input current. This is the actual input current for the op amp at the negative input terminal, which is what? IB2. Now we are finding the output only due to what? IB2, okay, or due to the two input currents IB1 and IB2. IB1 doesn't matter, okay. Now input we made it 0. This is 0 due to virtual short. This is 0 because input is made 0. Now R is between 0 and 0. So what is this current? 0. Now forget about this resistance R. Now this IB2, whatever current IB2 we have here, will it not flow through C2? So if you have a constant current flowing through a capacitor, continuously the cap will get charged. So continuously a voltage gets built up across the capacitor with this polarity. So what is V0 now? This is 0, you go from minus to plus. V0 is what? VC. VC is what? Voltage across the cap. And VC is not constant. VC keeps on increasing because continuously IB2 is flowing through what? Capacitor. A constant current is flowing through the cap. The voltage will linearly increase with time. So as VC keeps on increasing, V0 also keeps on increasing. If V0 keeps on increasing, at some point V0 will reach what? The positive supply voltage, which is plus VCC or plus VSAT. Once the output reaches plus VSAT, output will get saturated to plus VSAT. Okay, output gets saturated to plus VSAT. Once output gets saturated, then no longer this negative feedback and all of this will be applicable. The op amp itself will lose its relevance. Okay, output simply remains at plus VSAT. In fact, this is a very standard, piece of information that due to the input bias currents in an integrator, the output will get saturated. Yes. So to prevent the output from getting saturated, maybe you have to include some resistor at the plus input terminal, and also you connect some resistor across the capacitor and so on. Okay. But at least in the given circuit, due to the non-zero input bias current, output definitely gets saturated. But as I already told you in the question, this IOS is not mentioned properly. But if we have to strictly go by what is given here, okay, again let's make input 0, okay, and the voltage here is also 0 due to what? Virtual short, because V plus is 0, V minus also 0. So they are saying minus IOS, they have indicated the direction as well, okay. This direction they have shown IOS. Minus IOS is 1 microamp. It means IOS is what? Minus 1 microamp. So in this direction minus 1, it means in this direction plus 1. And this current will flow through capacitor like this. Correct, right? In this direction minus 1. So in this direction 1. In this direction also 1. So we have a positive current flowing through the cap from right to left. So right side plus, left side minus. This is VC. And V0 will be what? 0. You are going from minus to plus. So V0 is what? VC. As VC keeps on increasing, because the cap will continuously get charged because of this 1 microamp current that is indicated, V0 also keeps on increasing. Output gets saturated to what? Plus VCC. So positive supply voltage plus VCC. So after a long time, this won't happen immediately, because output gets saturated only when the capacitor voltage reaches a sufficiently large value such that the output gets saturated. Okay, that is why under steady state, output gets saturated and the circuit will lose its integration functionality. Okay. In the circuit shown in the given figure, the input voltage Vin, okay, there is some circuit. So I mean, if you observe carefully, the output is connected only to what? The negative input terminal. So this op amp is in negative feedback. And at the plus input terminal, some input voltage source is connected, whose value is 2 sine 100 pi t. So it is what? A sinusoidal voltage. So what is the voltage here? Vin. V plus Vin, due to virtual short, V minus is also what? Vin. Okay. And then for RL, the load resistance in the range 0.5 kilo ohms to 1.5 kilo ohms, the current through RL. Okay, there is some load resistance RL connected this way, and the current through RL is what? IL. In fact, this current is what? 0. Input current 0. That means this current is also what? IL. So IL is actually what? Same as the current through 1K in the downward direction. Vn minus 0 by 1K. So IL is what Vn by 1k, and this is independent of RL. In fact, RL need not just be in this range. RL can be any value. Yes, whatever be the value of RL, whether it is 1 ohm or 1 giga ohm, the current through RL is always what Vn by 1k. Okay. So Vn by 1k, 2 sine 100 pi t milliamps. That's all. So with respect to RL, the remaining circuit behaves like ideal current source because the current through RL is independent of RL. Okay. Why Vn taken 0? Because see, in the previous integrator question, I was just trying to find the output due to that non-zero input bias current or the input offset current. Yes, output will have different components. One output component is due to what? The applied input Vi, which we know is going to be what? A triangular waveform, because square when integrated becomes what? Triangular. In addition to that triangular thing, you'll also get an output due to what? The non-zero input bias currents. That is what I found. So to find the output only due to input bias current, I can make all other things 0. That is why I made input source 0. All right, moving on to the next question. When light falls on the photodiode, so there is what a photodiode, and light is falling on the photodiode, as shown in the figure, the reverse saturation current of the photodiode changes from 100 microamps to 200 microamps. So due to light falling on the photodiode, the reverse saturation current, it is changing from 100 micro to 200 micro. Actually, this is not correct. Okay, so when light falls on a diode, reverse saturation current does not uh, change. You'll actually get some extra reverse current. Yes, you'll get some extra reverse current. Okay, strictly speaking, this statement is incorrect, but it's okay. Okay, assuming the op amp to be ideal, the output voltage V0 will be. Okay. You see, what do you know about photodiode? If you go back to, if you shift to EDC, so we studied in EDC that, if you have a diode across which the voltage drop is what? VD, through which the current is what? ID. How are ID and VD related to each other? Through the diode current equation, IS times e power VD by VT minus 1. This is something everybody knows. But what if light is incident on the diode, and let's say that light gets absorbed and will create some useful EHPs which will contribute towards some extra reverse current which is called IL. So due to light, there will be some extra reverse current. That extra reverse current is what? IL. So what is the net current in the forward direction? This is the existing current. With or without light is always going to be there. With light, you get this additional reverse current. So the net current in the forward direction will be what? The existing forward current minus the additional reverse current. Okay, quite simple. Now if you look at our circuit, okay, what is the voltage here? Because of negative feedback and the resulting virtual short circuit, if V plus is 0, then V minus is also at 0. Now if you look at the diode P side, this is P side, this is N side. What is the P side connected to ground? N side is also at 0 potential. P side 0, N side 0. Does it not mean the voltage across the diode is what? 0. If you put VD equal to 0, if you put VD equal to 0, E power 0 is what? 1. 1 minus 1, 0. So this thing for this diode becomes what? 0. Then what is ID? The first term, it becomes 0 because VD is 0. Then ID is simply equal to what? Minus IL. ID is what? Current flowing from P to N. Current flowing from P to N is what? Minus IL. Then the current flowing from N to P will be what? Plus IL. So N to P, it means what? In the downward direction. Okay. So in the downward direction, what current will flow? IL will flow. So maybe they are referring this current as what? The reverse saturation current. That is how you need to understand to proceed forward. Of course, if you don't know all this, then you can directly go. Okay. So if this current is what? IL in the reverse direction, remember this current is always 0. This IL will definitely flow through what? 10K. Due to which there will be some drop here. This is 0, you go from minus to plus, just add the drop. So V naught equal to what? Whatever is that photo current IL times 10 kilo ohm. Okay. Now this in the question it is given that the reverse saturation current, which you can take it as what? This IL, it changes from 100 microamps to 200 microamps. Okay. Then the output changes from what to what. Okay. So if IL is 100 microamps, okay, 100 microamps into 10K is how much? 100 100 into 10K is what? 10 power 6. I think there is 1 volt. So for 100 microamps, the output voltage is what? 1 volt. So obviously for 200 microamps, the output will change from 1 to 2 volts. Okay. So changes from 2 to 1? No. Changes from 1 to 2, that is correct. Okay. So option B is correct. Moving on to the next question. The circuit shown in figure below is, okay, this is an op-amp circuit. They're asking you to identify what type of filter is this circuit. Actually, filters will discuss extensively in the next session. Since anyway this question has come, we'll just identify what filter is this circuit. Okay. First of all, there's only one capacitor. It is what? A first order circuit. So first order circuit cannot be band pass. It also cannot be band stop. It will be either low pass or high pass. So how do you decide whether it is low pass or high pass? Just by what? Finding what is the gain at low frequency and what is the gain at high frequency. Okay. So if you analyze this circuit at low frequency, by the way, the output through this R is always connected to what? The negative input terminal. So this op-amp will always be in negative feedback. So virtual short is something that is always going to be true, okay, at any frequency. At low frequency, you know, this capacitor will become what? An open circuit. When cap becomes open, the current through cap becomes 0. This current is always 0. This current both are 0. And this current also 0. Current 0, drop 0. Drop 0, it means the voltage at this point also 0. If V plus is 0, then V minus is also 0. And then this current, anyway, it is always 0. You can find this current VI minus 0 by R. Yes or no? So what is this current? It is VI by R. Then the same current will also flow through this resistor, resulting in a drop of VI by R into R, which is VI. This is 0, you go from plus to minus, subtract the drop. So V naught is what? Minus VI. So at low frequency, what is the output? It is minus VI. So what is the gain? Minus 1. What is the gain magnitude? It is 1. Okay, so there is the gain of the circuit at low frequency. Okay, 1. Let us find the gain at high frequency. High frequency, the same capacitor will act as a short circuit. So this VI is now shorted toward this point. So what is the voltage here? VI. Now due to virtual short, if V plus is VI, then V minus is also what? VI. Now if you look at this R, it is between VI and VI, drop 0, current 0, this current always 0. If these two currents is 0, then this current 0, this current 0, this drop 0, this VI drop 0, this VI will appear here. So what is V naught? It is VI. So what is the gain? It is 1. What is the gain? It is 1. Okay, so look at the gain values at low and high frequencies. They are identical. It is not that it is maximum at low and minimum at high. Neither it is maximum at high and minimum at low. So at all frequencies, the gain is what? 1 only. It is what? All pass filter. it is what? All pass filter. Okay. So it is not band pass, it is not band stop because it is not second order. Okay. It could have been low pass and high pass, but it is also not low pass and high pass from the analysis. It is not low pass, it is not high pass, it is not band pass, it is not band stop. At all frequencies, the gain is what? 1. If you plot the gain magnitude versus frequency, at all frequencies, the gain will be what? 1. This is what? An all pass filter. Okay. I mean, it's a first order circuit, no doubt. It will have one pole, but it will also have one zero. And that zero and this single pole will occur at same frequency, leading to what is called pole zero cancellation. Yes, that is why the gain neither increases nor it decreases. Okay. Answer is what? All pass filter. In the ideal op-amp circuit given in the adjoining figure, this figure, the value of RF is what? The resistance connecting the output to the negative input terminal is varied from 1K to 100K. Then the gain, V naught by Vi. I think this is missing. So you have to choose the correct option. So does the gain remain constant, or does the gain vary, and so on? Okay, here it is given. Sorry. Here it is given. Gain will, I mean, whatever be the value of RF, output is connected to what? The negative input terminal. Okay. So definitely op-amp will always be in negative feedback, irrespective of the value of RF. Okay. Negative feedback will result in what? Virtual short. What is this current? 0. What is this current? 0. This current through 10K is 0, then the drop across 10K is 0. Current 0, drop 0. Drop 0, it means what? If this side is what? Vi, this side also the voltage will be what? Vi. Now virtual short, if V plus is Vi, then V minus is also what? Vi. Now if you look at this 10K, it is between Vi and Vi. Between Vi and Vi, drop 0, so current is also what? 0. This current both are 0, then this current will always be 0. And this drop is always 0. If this drop is 0, that means this point and this point both are at same potential. So V naught equal to what? Vi. So the answer is option A. Gain remains constant at +1. Moving on to the next question. Assuming the op-amp to be ideal, the voltage gain of the amplifier shown below is, Here also the output of the op-amp is connected to what? Only the negative input terminal, which means the op-amp is in negative feedback. So virtual short, everything will be valid. Okay. So this circuit is actually what? The inverting amplifier. Okay. So if this is the input Vi. So if you look at this circuit carefully, input R1, R2, and this is what the output. This V naught will also appear at this point. Okay, so I'll again say it. Input R1, R2, and then the output plus terminal connected to ground. This is what the classic inverting amplifier. So that you can think of this R3 as what? The load. Why load? Because R3 is connected between what? Output and ground. You can actually think of it as what? The load. Yes. So in this way, directly you can tell V naught by Vi is what? Minus R2 by R1, which is option A. Otherwise, you can use do the usual analysis. V plus is 0. Due to virtual short, V minus is also 0. Ideal op-amp, this input current is what? 0. Voltage at this point is what? Vi. So what is this current? Vi minus 0 by R1. What is this current? 0 minus V naught by R2. At this point, we can just write KCL. Vi minus 0 by R1 is equal to Vi minus 0 by R1 is equal to 0 minus V naught by R2. This way also you'll end up getting the same answer. V naught by Vi equal to what? Minus R2 by R1. Okay. Alright guys, look at the next question. Once again, in the circuit shown below, what is the output voltage if a silicon transistor, okay? Okay, there is this NPN, there is NPN transistor, arrow mark away from the device. So it is what, an NPN transistor. Along with the transistor, there is this ideal op amp. See, whenever you have an ideal op amp in combination with diodes and transistors, we'll always assume initially diodes and transistors are off. I repeat, whenever you have ideal op amp in combination with, okay, op amp in combination with diodes and transistors. There can be any number of diodes, there can be any number of transistors, okay. In such a case, we'll always assume that initially all semiconductor devices are going to be off. Meaning what? Initially we'll assume all diodes are off, we'll assume all transistors are off, and so on. Okay. Here, if you do the same, initially if you assume transistor to be off, how does the transistor behave when it is off? Open circuit. Diode also, when it is off, will behave like what? An open circuit. So imagine transistor is acting like an open circuit. If this is open, then the output of the op amp, if this is open, will not be connected to any input terminal. Output not connected to any input terminal, it means what? Op amp does not have any feedback. Ideal op amp without feedback will act as what? Comparator. Yes, an ideal op amp without feedback will act as what? Comparator. Comparator will simply compare V plus and V minus. Accordingly, the output of the comparator will be what? Either plus Vsat or minus Vsat. Okay. So initially, if you assume this to be off, no current flows in this branch or in this feedback path. This current always 0. If this current is also 0, then this current is also 0. Then this 5 will directly appear at this point. So what is V minus? It is 5. Plus terminal connected to ground. So V plus is what? 0. So what is the output of comparator? What is the output of comparator? It will compare V plus with V minus. Definitely V minus is more than V plus. So output of comparator will be what? Minus Vsat, which is minus 15. Okay. So initial, all of this is initially. So if this is minus 15, now you look at the transistor. Now if you look at the transistor, what is the base connected to? Ground, 0. What is the emitter connected to? The output of the comparator, which is minus 15. So what is base? 0. What is emitter? Minus 15. What is base minus emitter? 0 what is base minus emitter? Meaning what? What is the value of VBE? 0 minus minus 15 is what? Plus 15, which is well more than VBE on, which is usually what? 0.7. So transistor will be on. So this implies now the transistor is going to be on. Now the transistor is going to be on. Only initially the transistor will act like an open circuit. So once you know that transistor is on, once you know that the transistor is going to be on, immediately between base and emitter, you should write down that VBE on, which is how much? 0.7. Okay. That's all. So here itself, base is what? 0, you go from plus to minus. So V out is what? 0 minus 0.7. So V out is what? Minus 0.7. Okay. And even the op amp will now go into what? Negative feedback. Why? Because see, the transistor will act as what? Say when you try to find loop gain. For negative feedback, I told you clearly the loop gain has to be negative. Yes or no? Loop gain has to be negative. Let's try going around the loop. If you try to go around the loop, you can start anywhere. Okay, let's say you start here. Okay. What is the gain from here to here? So if you are going from here to here, means what? You are applying input here, you are taking output here. You are applying, with respect to transistor, you are applying input at the emitter. You are taking output at the collector. Input emitter, output collector is what? The common base amplifier. Always common base amplifier has a positive gain. So what is the gain of this path? It is positive. And then from this point, you can directly reach this point, because all you have is what? A short circuit. Gain of short circuit is what? Always 1 plus 1. Then from this point, you can come back to the starting point. How do you go from this point to the starting point? Through the op amp, from negative input terminal to the output. So when you go from minus input to output, the gain of this path is always what? Negative. That's all. Did we not just go around the loop? So what is the gain from here to here? Positive. Then again positive, then negative. So what is the overall gain around the loop? Positive into 1 into negative. The product is what? Negative. Positive into 1 into negative. The loop gain is what? Negative. Loop gain negative. Now you can say, yes, the op amp is now in negative feedback. Now we can apply what? Virtual short and so on. V plus is 0. So due to virtual short, V minus will also be 0 and so on. But our question is what? Simply to find V out, and that is what? Minus 0.7, which is option B. Okay. All right, moving on to the next question. VB is given 0.7, right? I mean, even though it is not given, you can take 0.7. See, this drop is 0.7. Base is 0. Okay, so emitter has to be minus 0.7. Only then the drop between base and emitter will be what? 0.7. Okay. So V out is minus 0.7. Okay. Base is 0, emitter minus 0.7. Then drop between base and emitter would be plus 0.7. Okay. An operational amplifier circuit, op amp circuit is shown. Okay. Again, we can assume both op amps are ideal. So this op amp, this op amp is actually in positive feedback, correct? Because the output through R2 is connected to what? Plus input. So the first op amp is actually in positive feedback. For any op amp in positive feedback, the output will be what? Either plus VSAT or minus VSAT. So what is the output voltage of the first op amp? Either plus VSAT or minus VSAT. And then this output of the first op amp will act as input for the remaining circuit. What is the remaining circuit? The remaining circuit output through R is connected to what? Negative input. That means the second op amp is in negative feedback. Okay, in fact, the input applied at plus terminal, and this is like R2, this is like R1. This is actually what? The non-inverting amplifier. Okay. Non-inverting amplifier with a gain of 1 plus R2 by R1. 1 plus R by R, which is what? 2. So the output V0 will be 2 times whatever is the input applied to this non-inverting amplifier, which is plus or minus VSAT, which is the output of the previous circuit or the earlier stage, which is what? Op amp in positive feedback. So directly we said output will be what? Either this plus VSAT or minus VSAT. So what is the output voltage V0 going to be? It will be either plus 2 VSAT or it will be minus 2 VSAT. But for this op amp also the two supply voltages are what? Plus VSAT and minus VSAT. So if the output tries to be plus 2 VSAT, the actual output will be what? Plus VSAT. Output gets limited to what? Plus VSAT. And if the output tries to be minus 2 VSAT, which is below minus VSAT, then also the output will get limited or saturated to what? Minus Vsat. So what are the actual values of V naught? Either plus Vsat or minus Vsat, which is option D. Moving on to the next question, the operational amplifier circuit, the op-amp circuit. I mean, the op-amp in this circuit is what? Ideal. The input voltage Vi is what? Some 2 sine 2 pi times 2000 T. The amplitude of the output voltage V naught. Okay, fine. This is actually what? A first order low pass filter. Okay. This is a very basic active filter. This is what? A first order low pass filter. And for this, filter or whatever circuit is there, the input is what? A sinusoid. And they're asking what is the amplitude of the output. What is the amplitude of the input? 2. Yes or no? 2 is what? Amplitude. Frequency omega is what? 2000. Sorry. F is what? 2000. 2 pi ft. F is 2000. So omega is what? 2 pi times 2000, which is, which is 4000 pi. I mean, the only way to find the output is to find the transfer function, okay? And to find the transfer function, you have to do analysis in the S domain where you treat every element as what? Impedance. This 1 kilo ohm alone, you treat it as one impedance Z1, and this parallel combination, you treat it as another impedance Z2. Now, if you look at the overall circuit, also this small vi, in the S domain, it becomes capital Vi of S and so on, okay? So now if you look at the circuit, what is it like? Input Z1, Z2, and then the output plus terminal connected to ground. Clearly it is what? The inverting amplifier, okay? Inverting amplifier with a gain of minus Z2 by Z1. So what is V0 by Vi? It is minus Z2 by Z1. Z1 is what? 1 kilo ohm itself, but Z2 is what? Parallel combination of R and C, okay? So Z1 is what? 1K. Z2 is what? R parallel 1 by SC, which is R into 1 by SC upon R plus 1 by SC. Directly I'll write it as R upon 1 plus SC R, okay? Even this Z1 will write it as R, okay? That's all. Now if you try to compute the transfer function minus Z2 by Z1, if you divide Z2 by Z1, R and R will get cancelled out. Actually you'll get minus 1 by 1 plus SCR, okay, which is minus 1 by 1 plus S is what? J omega, and your omega is what? 4000 pi, okay, 4000 pi. RC, what is RC? R is 1 kilo ohm, which is 10 to the 3. C is 0.1 microfarad, which is 10 to the minus 7. When you multiply these two, I think you'll get 10 to the minus 4. That is the value of RC. So in place of CR, I'll just write 10 to the minus 4. Now what? 4000 into 10 power minus 4 is what? 0.4. So your transfer function is what? Minus 1 upon 1 plus 1 plus J 0.4 pi. This is V0 by Vi. Now you have to compute magnitudes on both the sides, because magnitude of the transfer function is nothing but the gain of the circuit. And the gain of the circuit is what? Gain means what? Ratio of output amplitude to the input amplitude. Already input amplitude we know. It is what? 2. Yes or no? So if you can find the magnitude of this and that magnitude of the transfer function, which is nothing but the gain multiplied with the input amplitude, which is 2, will give us the answer, which is the output amplitude. Okay. So I won't do the calculation. If you can do the calculation and tell the answer in the chat box, I will just go with that answer. Okay. So output amplitude will be the input amplitude, which is 2, times the magnitude of this transfer function. Okay. 1 upon 1 plus j 0.4 pi. Now this input amplitude is what? 2. Okay, so 2 divided by square root of 1 plus 0.4 square pi square. That would be the answer. Okay, Sai Vikas tells it is 1.245. Okay, good. So this way you get 1.245. Look at the next question. In the circuit shown, again an op-amp circuit, V0 equal to VOA, okay, for switch SW. So you have this double throw switch. When this switch is connected to this point A, then the output is what? V0 A. And when the same switch is connected to what? B, then the output is what? V0 B. Assuming that the op-amp is ideal, what is the ratio of V0 B to V0 A? Value of V0 B by V0 A. It is quite simple. You just have to find the output when switch is connected to A, call it V0 A. Also find the output when switch is connected to B, call that V0 B. Find the ratio of the two values, that is the answer. Okay. So here we have the two circuits. Let's say switch is connected to A. Okay. Like this, switch is connected to what? A. That means this point B is what? Left floating. So what is this current? It is 0. You can just remove this 1 kilo ohm resistor. Okay. And what is the voltage at this point going to be? Now this 1 volt will appear here. Okay. This current is always going to be 0. This 1K and this 1K will both be in series between 1 and ground. So what is the voltage here? Due to voltage division, it will be 0.5. Okay. Now here also, due to virtual short, if V plus is 0.5, V minus will also be 0.5. What is this current? It is 0. What is this current? 5 minus 0.5 by 1K, which is how much? 5 minus 0.5 by 1K is what? 4.5 milliamps. Now because this current is what? 0, this current will entirely flow through what? 1K. So what is this current? It will be 4.5 milliamps. That results in a drop of 4.5 volts. Now this 0.5 go from plus to minus, subtract the drop. 0.5 minus 4.5 is what? Like minus 4. So what is the output when switch is connected to A? It is minus 4. So V0 A, I'm getting it as minus 4. Sir, Vi varies from minus 2 to plus 2. Which question are you talking about? Let it be. We are only talking about amplitude. Amplitude of input means what? 2 only. Okay, peak value is what? 2. Now let's find the output when the switch is connected to position B, like this. In this case, this current is 0. When nothing is connected to this point, this 1K is left floating. this current 0. If these two currents are 0, then this current 0. Current 0, drop 0, so the voltage at this point 0. Due to virtual short, the voltage at this point is also 0. Okay, now it is actually what a weighted summer. Okay, 5 volt is one input, 1 volt is what another input. Directly you can write the output. If not, you can write KCL as well. What is this current 0? What is this current 5 minus 0 by 1K, which is 5 milliamps? What is this current 1? Remember the voltage at this point now is what 1. 1 minus 0 by 1K is what 1 milliamps. At this point 5 and 1 both are entering, so this current will be what 6. And this drop is also what 6. This 6 you go from plus to minus. So the output voltage in the other case is what minus 6. So what is VOB? It is minus 6. VOB is what minus 6. VOA, I'm getting it as minus 4. VOB by VOA is what minus 6 by minus 4. Correct, right? Minus 6 by minus 4, which is 1.5. So what is the answer to this question? It is 1.5. Good. Let's move on to the next question. The op amp shown in the figure is ideal. The input impedance, okay, this is the input source, which will look in this direction. So when this input source looks into the remaining circuit is what this. Okay, what is the equivalent impedance or resistance impedance seen by this input source? That is what we need to find. I mean, already it is given that input impedance is what V in by IN. Just have to do the analysis and find V in by IN. In fact, those of you who already know this circuit, you should be able to identify that there is what a negative resistance simulator. Okay, so using this circuit, you can get an equivalent resistance or impedance which is negative. Okay. So let's just do the analysis. So this op amp will definitely be in negative feedback. Okay. You don't have to worry about feedback. Okay, if you want to find the type of feedback, what do? At the output, you sort of break the loop and then apply VT. And then you try to find V plus and V minus in terms of VT. And while doing so, I told you what? All other independent sources, you have to make them 0. So this V in source, you have to make it 0. When you make it 0, it becomes short. Then this 0 ground will be shorted to this point. Then the voltage here will be what? 0. Okay. And at the other side, this R1 and this R2 will both be in series between VT and ground. So the voltage at this point will be what? VT into R2 divided by R1 plus R2. So what is V plus? It is 0. What is V minus? It is some non-zero value, VT R2 by R1 plus R2. So clearly V minus is bigger than V plus, which means the op amp is in negative feedback. Once you know that op amp is in negative feedback, then we can use what? The concept of virtual short. So just clear off this thing. Yeah. So I prefer VT and IT over VN and IN. I'll call this VT. I'll call this IT. So whether we are finding VN by IN or VT by IT, both are one and the same. This ground, you go from minus. So what is the voltage at this point? It is VT. So between this point and ground, you have a voltage source VT or VN. So the voltage at this point will be what? VT or VN. Fine. This current is always 0. Ideal op amp input current 0. So this IT cannot flow into the op amp, so it will flow around the op amp. So what is this current? It is IT. So what is this? Drop the current times the impedance, which is IT times Z. Okay. Now negative feedback results in what? Virtual short. Virtual short, it means what? This point and this point both are at same potential. Yes or no? V plus is equal to V minus. Now this, if you look at this point is connected to both R1 as well as Z. Okay, so this entire thing is what? One single node. These 2 points are 2 different points, but because of virtual short, these 2 points will be at same potential. Okay, so that means this drop and this drop both will be equal. Okay, this point is same, I mean common to both Z and R1, but these 2 points are equal, are at same potential due to what? Virtual short. So this drop and this drop both are equal. Since we already know the drop across Z as what? ITZ, this drop is also what? ITZ. Okay, and what is this voltage? It is VT, correct? V plus VT, V minus also VT. Now what is this current? Ohm's law, 0 minus VT by R2, minus VT by R2. What is this current? Current through R1 across which the drop is ITZ. Ohm's law, drop divided by resistance, ITZ divided by R1. Now if you look at this point, minus VT by R2 is what? Entering. This current is what? Leaving. Just write KCL at this point where you equate these two currents. Minus VT by R2 is equal to ITZ by R1. ITZ by R1. So whatever input impedance we are trying to find is simply the ratio of VT to IT. So what is VT by IT? Minus Z times R2 by R1. As you can see, if Z is positive, then the overall impedance will be what? Negative. So using op amp, you can realize an impedance value which is negative, because op amp is what? Dependent source. So when you combine resistors with dependent sources, it is possible to have a negative equivalent resistance or impedance. Okay, there is one such example. I think option B is correct. Minus Z times R2 by R1. But VT can be negative or positive. Then feedback can be negative. No, that is not. See, please understand what is our method of finding feedback. You are applying VT here. You are applying VT, it means what? The voltage at the output of the op amp is what? VT. Okay. Then you are trying to find what is V plus and what is V minus. Because the output is connected to what? Both plus as well as minus input terminals, some part of the output will go to what? Plus input terminal. At the same time, some part of the output will also go to what? Minus input terminal. Now we are just comparing the voltages at the two input terminals. Okay, let us say 50% of the output goes back to plus input terminal. 50%. Okay. At the same time, 30% of the output goes back to what? Negative input terminal. Okay, so there is this output. Okay, let it be anything. But the feedback arrangement is such that 50% of the output is going to what? Plus input terminal. 30% of the output is going to what? Negative input terminal. So which input terminal you are getting a higher portion or higher fraction of the output? Plus input terminal is getting 50%. Minus input terminal is getting only 30%. So plus input terminal, you are feeding back more output. That is positive feedback. Yes, that is the essence of this approach. Sir, where will we get notes for this session? I don't know. Is it required to share the notes? Well, if you really need it, we can just put it up in our Telegram group. Okay. So in our official Telegram group, we'll upload this PPT or whatever. Okay. All right, guys. Let's move on to the next question. So assume ideal op amps. There are two op amps. Okay, this op amp and this op amp. The output voltage V1. You have to find this output voltage. Okay. I think these two are not printed properly. So in fact, both op amps are in negative feedback. Okay, 1 second. Look at each op amp. This op amp output is connected to what? Negative input. So from here to here, the gain will be what? Positive. From here to here, the gain will be negative. Positive, negative, loop gain is what? Negative. So negative feedback. Even for this op amp, output through this resistor is connected to what? Negative input. From this negative input, you can go back to the output, positive, negative. So both the op amps are in negative feedback. So no doubt virtual short will apply for both the op amps. Okay. Now let's find the output, which I think is simple. What is the voltage here? It is 3 volts. Between this point and ground, you have a 3 volt source. So if V plus is 3, then due to virtual short, V minus is also at 3. So what is the voltage at this point? It is 3. If you look at this op amp, what is voltage at the plus input terminal? It is 2 volts. Now due to virtual short, V minus will also be 2 volts. This on V plus 2, V minus also 2. If I ask you what is this current, what is the voltage at this point? This point is shorted to ground. This is 0 potential. 3 minus 0 by 1K is what? 3 milliamps. This entire thing is what? Same node. So what is the voltage at this point? Also 3. So what is the current in this direction? 3 minus 2 by 1K, which is 1 milliamp. So what is this current? It is 1 milliamp. Okay. This current is always 0. And what is this current? I think this is 3. This is V1. This V1 will also appear here. So 3 minus V1 by 1K. Now this entire thing is what? Like a node. So at this node, how many currents are flowing? 1, 2, 3. This is leaving, this is leaving, this is also leaving. This current is 0. Don't count it. So all 3 currents are leaving this particular node. So sum of these 3 currents is what? 0. So 3 plus 1 plus this current. So 3 milliamps plus 1 milliamp is equal to 3 minus V1 by 1K. 3 minus V1 by 1K. I think 3 plus 1 is what? 4 milliamps into 1K is what? 4 volts is equal to 3 minus 1. V1 is 3 minus 4, which is minus 1. Is that correct? Did I make a mistake? This is 3 milliamps. This is 2 milliamps. Oh, sorry. Okay, I'll just change the current direction. I made a mistake. I'll take the current direction like this, which is entering the node. Then I can write this equation. But the value of the current will now be V1 minus 3. Okay. V1 minus 3. V1 is 7. V1 is 7. Okay. In the circuit shown below, this circuit, all the components are ideal if Vi is what, 2 volts. Okay. So the voltage at this point is what, 2 volts. The current I0 sourced by the op amp. Where is this I0 flowing? At the output of the op amp. The current is what, I0. That is what you need to find. Again, output of the op amp through 1K connected to what? Negative input. So definitely op amp negative feedback, which means virtual short will be valid. V plus is 2, V minus also 2. So what is this current? 2 minus 0 by 1K, which is 2 milliamps. So this current is always 0. So this 2 milliamps will flow through this 1K. That results in a drop of 2 times 1, 2 volts. 2 volts. Okay, just as it. Now this is 2, you go from minus to plus, so the voltage at this point is what, 4 volts. So the voltage here is also 4. Now the current through 1K in the downward direction will be what, 4 minus 0 by 1K, which is 4 milliamps. So what is this current? It is 2 milliamps. Now at this point, if you write KCL, I0 entering 2, 4 leaving. So directly I can tell I0 is what, 6 milliamps. So at the output, the current that flows is what, 6 milliamps. I already told you, only at the input terminals, the currents will be 0 for ideal op amp. At the output, any current can flow in any direction. Okay. So this current is flowing away from the op amp, right? So this current will come from the positive supply. Yes, if a positive current flows into the op amp, that current will come from negative supply. That is the thing. Okay. Anyway, for this question, that is not required. Moving on, what is this question? A circuit with an ideal op amp. Okay, this op amp is ideal. A pulse V in. Okay, so this input is what, a pulse. Okay, fine. What is the height of the pulse? 5 volts. What is the width of the pulse? It is 20 milliseconds. A pulse V in of 20 millisecond duration is applied to the input. The capacitors are initially uncharged. Okay, the question is here. The output voltage V out of this circuit at t equal to 0 plus, okay, is dash volts. Okay. I mean, this circuit is actually what, a differentiator. I mean, these two capacitors are in parallel. You can club them into what, a single capacitor. Then if you look at the circuit input, capacitor, resistor, output, plus terminal connected to ground, it is what, differentiator. So you have a differentiator circuit and the input is what, a pulse. Okay. And also for the op amp, the two supply voltages are given, plus 12 and minus 12. Ideally, what will the output be? Ideally, when you differentiate a pulse, you will get what, 2 impulses, right? Yes. If this is t equal to 0, this is t equal to 20 milliseconds. Okay. This is 0 volts and this is 5 volts. This is the input. This is the input. Yes. And you know, for differentiator, the output is given by minus RC times dVi by dt. dVi by dt means what? The slope of the input waveform. Okay. Up to t equal to 0, the input is always 0, slope is 0, output 0. At t equal to 0, the input jumps from 0 to 5. Input jumps from 0 to 5, which means the input has infinite slope. It's like a step change, sudden change. Yes, slope will be what? Infinite. Slope is positive infinity. So dVi by dt at t equal to 0 is what? Positive infinity. I hope you are following. Okay, at t equal to 0, input jumps from 0 to 5. What is the slope? Infinite. Minus RC times infinity is what? Minus infinity. Yes. So the output will tend to what? Minus infinity. Because of the minus sign, output will tend to what? Minus infinity. Immediately after that, the input again becomes constant. If the input is flat or constant, what is its slope? 0. So in this interval between 0 and 20 milliseconds, the slope of the input is what? 0. Okay. And after that, again at t equal to 20 milliseconds, you have this negative edge. So this you can call it positive edge, where the input makes a transition from 0 to 5. At t equal to 20 milliseconds, the input makes a transition from 5 to 0. Here also the transition is what? Sudden. It takes place in 0 time. So what is the slope of the input at t equal to 20 milliseconds? Sudden jump, but in the negative direction. So slope is what? Negative infinity. Minus RC times the slope, which is negative infinity. Minus into negative infinity is what? Plus infinity. So at t equal to 20 milliseconds, the output tries to be plus infinite. Thereafter, again, the input is constant, slope is 0, output is also 0. So everywhere the output is what? 0. But only at t equal to 0 as well as at t equal to 20 milliseconds, the output is not 0. In fact, output tries to be infinite. Output tries to be minus infinity here, because slope is plus infinity, output tries to be minus infinity. Here the slope is minus infinity, output tries to be infinity. Is it not like two impulses? So ideally your output will be what? Should be what? This. If this is t equal to 0, this is t equal to 20 milliseconds, and if you are plotting V0 versus t up to t equal to 0, input is constant, slope is 0, output is 0. Okay. And then, sorry. You'll get this negative impulse. After that, again, output is 0. Here, you'll get a positive impulse. Elsewhere, the output is what? 0. In fact, I don't have to draw this, because for impulse, it is understood that so this is the ideal expected output. This is the ideal expected output. Okay. But will you really get this output in our circuit? See, had the supply voltage not been given, here explicitly the supply voltages are given 12 and minus 12. If the supply voltages are not given, ESC exam, what happened? Yeah. If the supply voltage is not given, then you can assume the supply voltages are what? Plus infinity and minus infinity. Then it is possible to have these impulses. Okay. Now the supply voltages are what? Finite. So the output cannot really go to what? Minus infinity. That means output at t equal to 0 will try to be minus infinity, but it can only be what? Minus 12. So clearly we have a case where output gets saturated. We have a case where output gets saturated. Whenever output gets saturated, op amp is not operating in that middle segment. Yes, which means virtual short will not be valid. Virtual short will not be valid. Okay. So this you won't get, at least for our circuit. I give you the same circuit, supply voltages are not mentioned, then the answer will be what? V out at t equal to 0 plus. Answer will be 0. If the supply voltages are not given, then V out, you should say it is what, 0. Okay, but here supply voltage are given, which means output will get saturated, which means virtual short will not be valid. Okay, so we need to do the analysis. At t equal to 0, what does the input do? Input does this. It goes from 0 to 5. Input jumps from 0 to 5. Okay. And by the way, these two capacitors can be combined. Okay, can be combined into what? A single 2 microfarad capacitor. Okay. This is like C and this is like R. So usually virtual short will be valid. Usually. Okay. Why? Because the output of the op-amp is connected to the negative input terminal through the resistor. Usually virtual short will be valid, but not here. Because at t equal to 0, number one, the input is changing suddenly. Input is changing suddenly. Okay. Voltage across the cap cannot change suddenly. Yes or no? Voltage across the cap cannot change suddenly. At t equal to 0, what is the momentary frequency of operation? Another way to look at this is what? Sudden change. If you have step change at t equal to 0, what is the momentary change of momentary frequency of operation? You can say omega tends to infinity. We have done this in class. Capacitor problems. Yes, at t equal to 0, when input voltage jumps from one level to another level, I tell you what, at that instant, we can assume circuit operates at infinite frequency, and then at infinite frequency, capacitor will tend to have 0 impedance, 1 by j omega c. So if you have a resistor across that capacitor, it is as if that resistor is connected across what? 0 impedance. We neglect resistors. Yes or no? You have to apply a similar thought process here. Okay, at t equal to 0, what is the momentary frequency of operation? Omega tends to infinity. Omega tends to infinity, this capacitor will tend to have 0 impedance. 0 impedance is what? Like a short circuit, which means this 5 volts will directly appear here. Okay, this 5 volts at the input will directly appear here. When 5 volts appears here, now V minus is what? 5. V plus is what? 0. So clearly V minus is more than V plus. Your output will become what? Minus V sat, which is minus 12. Yes. And virtual short, valid or not valid? Not valid. Yes, as you can see, V minus and V plus are not equal. Also, the output is what? Saturated. Okay. So whenever virtual short is not valid, then you do the analysis this way, right? This voltage will be pinned at minus 12. Okay. This current is always going to be 0 anyway. Okay. The op-amp becomes irrelevant. When virtual short is not valid, the op-amp becomes irrelevant. Why? Because it is not operating in that high slope region. It is operating in the saturation region. Okay, it is operating in the saturation region. When the op-amp becomes irrelevant, the circuit can be drawn like this. So on one side you have the input, then you have the capacitor, then you have the resistor, and then you have the output, which is saturated and pinned to what? Minus 12 volts. Okay. What is the input value? It is 5. Let us call the voltage at this point as what? Vx. And this Vx is same as what? V minus. Vx is same as what? V minus. Okay. So this is what a simple RC circuit, first order circuit driven by DC sources. Because during the duration of the pulse, we are analyzing the circuit during the interval of the pulse between 0 and 20 milliseconds. The input is what? Constant. It is like DC. That side is what? Minus 12. Okay. So as long as your V minus is greater than V plus, output continues to be at minus 12, okay, some sort of comparator. Now, what is Vx of 0 plus? Because at the time of this jump, the capacitor acts like a short circuit. This 5 volts will appear here. So Vx of 0 plus is what? 5. If this RC circuit tries to reach steady state, what steady state? Because that is constant, DC is also constant DC, it will try to reach what? DC steady state. At DC steady state, cap becomes open, then no current flows in this branch, no current through R, drop across R0, this minus 12 will try to appear here. So what is Vx of infinity? It is minus 12. So for Vx, which is the voltage at this node, and also what? The voltage at the negative input terminal, the initial value is what? 5. Final value or the steady state value is what? Minus 12. So what will Vx try to do during this duration of the pulse? Vx will try to go from 5 to minus 12. From 5 to minus 12 is what? Exponential decay. Okay. So this is initial. This is final. Okay. So Vx of t. So if you want to write down how the voltage at this negative input terminal varies with time, you can use that final initial formula. Final plus initial minus final times e power minus t by tau. In place of final, you write minus 12. In place of initial, you write 5. Okay. So if you try to plot Vx versus t, Vx starts from 5 volts, it will try to go towards what? Minus 12. As it tries to go towards minus 12, at some point, will it not touch the x-axis? So at this point, what will happen? Vx becomes 0. At this point, Vx becomes 0. While going from 5 to minus 12, in between definitely will go through what? The x-axis, or it will go through what? 0 value. When Vx becomes 0, look at V plus. V plus is always 0. If Vx also becomes 0, then what is your value of Vd? V plus is 0, V minus is 0, then Vd also becomes 0. So if Vx becomes 0, then your Vd also becomes 0. Vd equal to 0, where is your operating point? Now you are in the middle segment. Yes or no? So if you try to plot, V0 versus Vd, if you try to plot V0 versus Vd, plus Vsat minus Vsat in the middle. So initially what is Vd? Initially what is Vd? Initially V plus is what? 0. This is 5. Vd is what? 0 minus 5, which is minus 5. Okay. And then as Vx decreases, okay, as Vx decreases, Vd will go from minus 5 towards 0. Okay. See, Vx is trying to go from 5 towards minus 12. Vd is what? V plus minus V minus. 0 minus this thing. So minus 5 towards 0 minus minus 12 is what? Plus 12. So if Vd is minus 5, then it is somewhere here. So it is moving along this line. At some point, it will latch on to the middle segment. Once Vd becomes 0, what happens? Now V plus equal to V minus, which means now virtual short will be valid. Okay. and the output will become what? 0. Output will become 0. Okay. And the voltage across the cap simply remains at 5 volts. Okay. See. This side is 5. There is the capacitor, there is a resistor. This side is what? Minus 12. We are calling the voltage at this node as what? Some Vx. Okay. So let us write down what is the expression for Vx of t. What is Vx of t? Final plus initial. Final is what? Minus 12. Initial is what? 5. 5 minus minus 12, I can write it as 5 plus 12 e power minus t by Rc. Tau is what? Rc. Minus 12 plus 17 e power minus t by Rc. What are we trying to find? I am trying to find the instant at which Vx will drop to what? 0. Because once Vx reaches 0, then immediately Vd becomes 0, then your operating point will be on this middle segment. Okay. So just equate this to what? 0. Just equate this to 0. Then you'll get the time at which your Vd becomes 0. Okay. So when you equate this to 0, what do you get? 17 e power minus t by Rc is equal to 12. Or you can write e power t by Rc is equal to 17 by 12. So t is equal to what? Rc ln 17 by 12. R value is what? 10 kilo ohm, 10 power 4. C is what? 2 microfarad. 10 power 4 into 2 microfarad is what? 10 to the 4 into 2 into 10 power minus 6, which is 2 into 10 power minus 2, which is same as, I think, 0.2, correct, right? 0.2, 2 into 10 power minus 2. (20 milliseconds). 2 into 10 power minus 2 is what? 20 into 10 power minus 3 or 20 milliseconds. So Rc is what? The time constant is what? 20 milliseconds. So 20 milliseconds times ln of 17 by 12. ln of 17 by 12. So let me find the value of this. ln 17 by 12 into 20. Okay, 0.6966. $6.966. Just 7 milliseconds. So at t equal to 7 milliseconds, your Vx will come down to what? 0. Vx will come down to 0. Once Vx comes down to 0, your Vd becomes what? 0. So from here onwards, the output won't be saturated anymore. Okay, I think you can also argue that if Vx tries to, continues to go downwards, let's say it becomes slightly less than 0. Okay, if Vx becomes slightly less than 0 or slightly negative, then V plus becomes greater than V minus. Okay, then your output should jump to what? Plus 12. Okay, and if the output becomes plus 12, then okay, this is some small negative value. Now the current will start flowing like this. Then what is the final value of Vx? Then it will be plus 12. Then your Vx will try to increase. So from small negative, it will try to become small positive. So Vx will keep wiggling about 0, but that will not happen, because once Vd becomes 0, it is operating on this middle segment. It is no longer unstable sort of thing. So V0 will become 0. Okay. So if the voltage at this point is what? Some Vx. So if you try to plot Vx versus T, Vx starts from what? 5 volts. It will only drop to what? 0. Okay, it will drop to 0. After that, Vx remains at 0. Okay, and this happens at 7 milliseconds. So if you have to draw the output waveform, this is 0. So up to t equal to 0, nothing will happen. This 0 will simply appear here. Okay, because no current flows through cap, no current flows through resistor, no drop. The 0 appears at the output. So V out is what? 0. 1 second. At t equal to 0, when your input jumps from 0 to 5, that 5 will directly appear here, and V minus is greater than V plus, your output will jump to what? Minus 12. This is minus V sat, which is minus 12. And then you have this interval between 0 and 7 milliseconds where your Vx will drop from 5 to 0. Now throughout this interval, Vx is what? Greater than 0. Vx greater than 0, it means what? V minus greater than V plus, output continues to be at minus V sat. So during this interval, output will be what? Minus 12. In fact, they could have asked you for how long the output remains at minus 12 before it comes back to 0. The answer is what? That 6.9 or 7 milliseconds. Okay. So it is at t equal to 7 milliseconds that the output will come back to what? 0. And then output remains at 0. But again, you also have one more edge at t equal to 20 milliseconds. At t equal to 20 milliseconds. Okay, so at t equal to 20 milliseconds, let's say this is 20 milliseconds. Again, the input has what? A step change or a sudden change. So at t equal to 20 milliseconds, also the momentary frequency of operation will tend to what? Infinity, in which case the capacitor acts like what? A short circuit. Yes. And then if the input drops by 5 volts, then this also drops by 5 volts. This will go to what? Minus 5. Yes, because after this, during this interval, the voltage across the cap remains fixed at 5 volts. Yes or no? Because this is 0, this will remain at 5. 5 minus 0, voltage across the cap remains at 5. Okay. Now at t equal to 0, your Vn jumps from 5 to 0. That means Vn is suddenly decreasing by 5. The other side also should suddenly decrease by 5, so that the voltage across the cap does not change instantaneously. Okay. So this is initial at 0. From 0, if it decreases by minus 5, it will go to what? Minus 5. Now if you compare V plus and V minus, V plus 0, V minus minus 5, 0 is more than minus 5, output will become plus V sat. So now at t equal to 20 milliseconds, your output will jump from 0 to plus Vsat, which is plus 12 volts. Again, virtual short will not be valid after t equal to 20 milliseconds. Again, you have to draw this RC circuit separately, okay? Because the op amp will now operate here. Now the op amp will operate here after or just after t equal to 20 milliseconds. And then slowly this operating point will move towards the left. And then at some instant, VD will become what, 0. Then again virtual short will come into play and the output becomes 0. You understood? This is the output waveform that you should expect for the given circuit. So what is our question? Output voltage at t equal to 0 plus, that is just after t equal to 0. So clearly it is what, minus 12. Just after t equal to 0, what is the output? It is minus 12, okay? Let's move on to the next question. The output V naught of the ideal op amp used in the circuit shown below is what, 5 volts. So they themselves are telling that the voltage at this point is what, 5 volts. Then the value of the resistor RL. So they are asking what is the value of this RL resistance in kilo ohms. Okay. All right, let's do it. So this op amp will definitely be in negative feedback. Okay. I mean, this thing we have done in class, but still, you some of you might think the output. Oh, sorry. Some of you might think. Oh, yeah. The output is connected to what, negative as well as positive, which is true. But if you apply some VT here and make this 1 volt source 0 and try finding V minus and V plus in terms of VT, always V minus will be greater than V plus irrespective of the value of RL. If you can do that, you'll get that. Okay. If V minus is more than V plus, it means what? Op amp is in negative feedback. That's all. So once you know that op amp is in negative feedback, we can go ahead and use the concept of virtual short. Okay. So just erase this, also this. Yeah. You say, okay, output voltage 5. So there is also 5. What is this current? 0. What is this current? 0. If this current is 0, then this current and this current both are equal. So that means 10K and 10K both are in series between 5 and ground. So what is the voltage at this point? 5 into 10 divided by 10 plus 10, which is 2.5 volts. Voltage division. Okay, these two are in series between 5 and ground. Now due to negative feedback, we always have what? Virtual short. If V minus is 2.5, then V plus is also what? 2.5 volts. And the voltage at this point will obviously be 1 volt. Okay. And what is this drop? 5 minus 2.5. It is what? 2.5 volts. Now, due to virtual short, these 2 points will be at same potential. Okay. So what is this drop as well? 2.5 only. 5 minus 2.5. That way also you can say it is what? 2.5. I think we're almost there. What is this current? 2.5 minus 1, 1.5 divided by 10K. 1.5 by 10K is what? 0.15 milliamps. Similarly, what is this current? 2.5 drop divided by 10K, which is 0.25 milliamps. Okay. Now, if you apply KCL at this point, if you observe, 0.25 is entering, 0.15 is leaving. What is the remaining current? 0.25 minus 0.15, which I think is what? 0.1. So what is this current, it is 0.1 milliamps. Also, what is the drop across RL? 2.5 minus 0 by RL. 2.5 minus 0 is what? 2.5 volts. Now, RL load resistance is what? Drop divided by current. 2.5 by 0.1 is 25 kilo ohms. Yes. Drop is 2.5 volts. Current is what? 0.1 milliamps. So it is what? 25 kilo ohms, which is option A. I hope it is clear. Okay. So we have plenty of problems left to be discussed. It's been almost 3 hours, so we'll take a short 10-minute break. We'll take a 10-minute break. Now it is 6 o'clock, 6:10. We will continue this discussion. Okay, 6:10. All right, guys, welcome back. Let's continue our discussion. So we have been solving problems related to what ideal op-amp connected in negative feedback. Okay, so let's complete the remaining problems. So the circuit, I don't know if the diagram is clear or not, but it is what an integrator, the steady state. One second. Yeah. Ah. The steady state output voltage of the circuit shown below will be. See, first of all, the op amp is what ideal, so it will have infinite gain. Also, for ideal op amp, the two input currents are zero. So this current through this resistor R2 will be zero, which means the drop is also zero. So what is the voltage at the plus input terminal? It will be zero. This is zero, drop zero. So it is a standard integrator circuit. So you can think of this 0.1 volts as the input. So input R, C, output plus terminal at zero potential. It is what the integrator. So you know for integrator, the output expression is what? Minus 1 by RC times integration of the input from 0 to T. Now this input is actually what? A positive DC voltage. Yes. So in place of VI, you can just write 0.1. Okay. When you write 0.1 in place of VI, 0.1 being a constant will come out of the integration. Then you will get minus 0.1 by RC times integration of d tau is what? Tau from 0 to t is what? T minus 0, which is t. So look at this, the output expression, which is what? Negative ramp. Output is proportional to time. Output varies linearly with time, but the slope is what? Negative. So it is what? Negative ramp. So what will the output try to do? Output will start from 0, okay? Because this is 0. There is nothing mentioned about the initial voltage across the cap. So initial voltage across the cap, you can assume it is 0. This is 0, initial voltage across the cap 0. So initial value of V0 is also at 0. So V0 starts from 0. So V0 starts from 0. Thereafter, V0 will linearly reduce with time. Okay. So as V0 continuously decreases and becomes more and more negative, at some point, V0 will reach what? This negative supply voltage, which is minus VW. Okay. So once V0 reaches minus VW, thereafter V0 will remain constant at minus VW. So at steady state, the question is what? Steady state output. Steady state means what? After a long time. After a long time, clearly the output reaches what? Minus VW. Okay. And then it remains at minus VW. Output gets saturated to what? Minus VW. This is one way to do it. The same question can also be solved directly. Because I said the input is what? DC. Because the input is what? DC. You have a circuit driven by a DC input. You have a circuit for which the input is what? DC. Now that circuit will eventually reach what? DC steady state. Yes or no? So after a long time, the circuit will be at DC steady state. At DC steady state, the cap becomes open. When the cap becomes open, then the output of the op amp is not connected to any of its input terminals, which means the op amp will now act as comparator. So at DC steady state, the op amp behaves like what? A comparator. Comparator will compare what? V plus and V minus. Now, if the cap becomes open at DC steady state, no current through the cap, this current 0, then this current also is 0. Then your 0.1, the voltage at this point is what? 0.1. Because the current through R1 is 0, this drop is 0, this 0.1 will actually appear at this point. So then V plus is 0, V minus is what? 0.1. V minus 0.1, V plus 0, 0.1 greater than 0, V minus greater than V plus. Output will go to what? Minus V sat. That way also directly we can tell that the output gets saturated to what? Minus VW. Okay. So either way, the correct option is what? Option B. All right. Assuming ideal op amps, there are two op amps, assuming both are ideal, the circuit represents what? This overall circuit for which input is applied here and output is taken here will act as a summing amplifier, logarithmic amplifier, difference amplifier, or a buffer. See, summing amplifier should have multiple inputs, but here there's only one input, and this is quite simple. Is the feedback positive or, I mean, you must be familiar with this block. This is actually what the voltage buffer. Yes or no, output of the op amp shorted to the negative input terminal, it is what a voltage buffer. So what is the gain of voltage buffer? 1. Okay. So what is the gain from here to here? It is 1. What is the gain from here to here? It is negative. Don't say 1. From here to here, the gain is what? Negative. From here to here, the gain is 1 because this block is what? A voltage buffer. Now, did we not go around the loop? What is the gain around the loop? 1 into some negative value is also what? Negative. So, loop gain is what? Negative. Loop gain negative, it means what? The overall feedback is also what? Negative. Okay. Anyway, by this argument, we can say that both op amps are in negative feedback. Once you know that both op amps are in negative feedback, you can use virtual short for both the op amps. So this is V0, fine. Because of virtual short, this V0 will appear here because this point is shorted to this point. This point is also at V0. Now for this op amp, if you apply virtual short, this Vin will appear here. So at the same point, you have both V0 and Vin. That means V0 equal to what? Vin. If V0 equal to Vin, then what is the gain? Gain is what? 1. Correct or not? Gain is 1. For which amplifier the gain will be 1? Ideally, for a voltage buffer, the gain has to be 1. Okay. Say for a voltage buffer, not only the gain has to be 1, even the input resistance should be very large, output resistance should be very small. What is the input resistance? What is the current drawn at the input terminal? It is 0. Current at the input terminal 0, that itself means the input resistance is what? Infinite. Okay. Also, if at all you try to connect a load resistance, if you try to connect a load resistance between output and ground, if you try to connect a load resistance between output and ground, whatever be the value of the load resistance, the output voltage or the voltage across the load resistance will be equal to what? Vin. So the voltage across the load is independent of the load resistance. That means what? It is as if the load is connected across an ideal voltage source. With respect to RL, the remaining circuit will behave like ideal voltage source. Ideal voltage source, directly we can tell R out is what? 0. So these three values are the ideal values for a voltage buffer, and for our circuit also we have the exact same three ideal values as we have for a voltage buffer. So the answer is what? A voltage buffer. Okay. Look at the next question. For the ideal op amp based circuit shown in figure, the ratio V to I. So you have to find this ratio. I mean, it's quite simple. Output is connected to what? The negative input terminal. So op amp will be in negative feedback. So virtual short, everything applies. So what is the voltage at this point? It is V. Because this current is 0, these two will be in series. So what is the voltage at this point? From voltage division, it is what? V times R4 by R3 plus R4. Okay. Now, this value is what? V plus. Then V minus is also what? The same value. Okay. So if I call this some Vx, and this is also what? Vx. Okay. And then you can call this current as some I1. You can call this current as I2. Okay. Now at this point, you can write KCL. I is equal to what? I1 plus I2. So I is equal to what? I1 plus I2. I1 is what? V minus Vx by R2. V minus Vx by R2. I2 is what? Simply the current in this branch, V minus 0 by, R3 plus R4, or V by R3 plus R4. That's all. Now in place of that Vx, you write V times R4 by R3 plus R4. Then your V is common. When you take LCM, I think you'll get uh, R3 plus R4 minus R4, which is R3 itself. So V times R3 by R2 times R3 plus R4 plus V divided by R3 plus R4. So what is the LCM? It is R2 times R3 plus R4. If you take out V, then you'll have R3 plus R2. That's all. This side you have I. So what is the question? It is to find V divided by I, send I to the other side, and this entire factor will come to this side. I think you'll get R2 times R3 plus R4 divided by R3 plus R2, which is not among the options. Maybe I made a mistake. But this is V. This is V R4 by R3 plus R4. V R4 is correct. This is Vx. Same Vx here. I is equal to I1 plus I2. V minus Vx by R2. Fine. Now that V minus Vx will be what? R3 plus R4 minus R4. R3 by 3 plus R4 is also correct. V R3 by R2 plus V by R3 plus R4. So when I take LCM, it is R2 plus R3 plus R4. It's correct. I think whatever we got is correct. Okay. So my answer, hope you are also getting the same thing. My answer for V by I is this thing. R2 times R3 plus R4 upon R3 plus R2. Okay. Okay, fine. So maybe there is a mistake in the options. Okay, but this answer is correct. It's a simple question. For the ideal op-amp based circuit shown in the figure, what is the ratio V to I? Oh my God. The same question, right? Yeah. Okay. The circuits mentioned in the following options are realized using ideal op-amp. Among these, the circuits performing nonlinear operation on the input signal are. So 4 different circuits are given. They are asking you to identify. They are asking you to identify which circuits are non-linear. Okay, so instrumentation amplifier, is it linear or non-linear? Similarly, Schmidt trigger also linear or non-linear. Logarithmic amplifier, precision rectifier. Instrumentation amplifier is what? A differential amplifier. Differential amplifier, instrumentation amplifier is what? Difference amplifier, for which you apply 2 inputs and the output is proportional to what? Difference between the 2 inputs. Output proportional to difference between the 2 inputs. Okay. So I'm sure you would have seen an instrumentation amplifier before. It will have 3 op amps. This is a typical instrumentation amplifier circuit. Okay. So let's say one input is what, some V1, another input is what, let's say V2. Now your output, when you do the analysis, it will be some gain times some number K times V1 minus V2, which can also be written as KV1 minus KV2. So how is the output related to the two inputs? Linearly. Yes or no? V1 getting multiplied by some number K, V2 also getting multiplied by a number like minus K. Yes. So it is what, linear. So output is linearly related to the two inputs. But our question is what, to identify the circuits where the output is non-linearly related to the input. So instrumentation amplifier is not one of them. Schmidt trigger, I think in the very beginning I explained, if you plot V0 versus Vi, that V0 versus Vi plot has to be what, a straight line passing through origin. Okay, but for Schmidt trigger, you have that hysteresis loop and so on, which is not a straight line at all. Okay, so Schmidt trigger output is linearly related to input. True. Logarithmic amplifier. The name itself tells that. Why is it called logarithmic amplifier? Because the output is related to the logarithm of the input. Yes, output is proportional to what? The natural logarithm of the input. That is why it is called logarithmic amplifier. Log function, is it linear or non-linear? Non-linear. It's on log function. It is what? Non-linear. So there is also a correct option. Precision rectifier. What is that precision rectifier? How do you make this logarithmic amplifier? You can just use a diode. If you have a diode, if you have an op amp, and then you combine it with a diode like this. This side you apply some input voltage. This is what a simple logarithmic amplifier. Okay. First of all, for input, when input is positive, then only the diode will be on. For negative values of input, diode will be off. Okay. So we are assuming that the input is what, positive. Okay. And if this resistance is what, R, what is this current? When input is positive, diode is on. So output through the diode will be connected to what? The negative input terminal. So negative feedback will result in what? Virtual short. So what is the voltage at this point? 0. So what is the current through R? Vn by R. This current is 0 anyway. Now the current through diode, we can call it ID, and that will be same as what, the current through the resistor, which is Vn by R. And the voltage across the diode, we can call it Vd, and the output voltage, we can call it V0. So what is Vd? So if you observe, Vd is what, potential difference between P side and N side. P side is what, 0, N side is what, V0. 0 minus V0, Vd is what, minus V0. Okay. Now if you try to write the diode current equation, Is times e power Vd by Vt minus 1. Correct. Also, when diode is on, the value of the exponential term will be much bigger than 1. You can neglect 1. You can just write it as Is times e power Vd by Vt. But what is Vd in terms of V0? Minus V0. So e power minus V0 by Vt. Now what, you take logarithm, natural logarithm on both sides, ln on both the sides. Before that, Is will come to this side. I think you'll get ln of Vn divided by ISR is equal to minus V0 by Vt. Okay, that's all. So V0 is equal to what? Minus Vt times ln Vn by ISR. The point to note is this: output voltage is related. How is output related to input? Output is related to the natural logarithm of the input. That is why it is called logarithmic amplifier, and log function is what? Non-linear. So logarithmic amplifier is also what? Non-linear. And then you have the next circuit, which is what? A precision rectifier. Rectifier. Yes, rectifier means what? What is a precision rectifier? If you plot V0 versus Vi, yes, for a precision rectifier, Let's say it is a precision half-wave rectifier. Okay, precision half-wave rectifier. It can be full-wave rectifier also. Okay. If it is precision half-wave rectifier for positive input, whatever be the input when it is positive, let it be any small positive input. As long as input is positive, your output will be same as input. Okay, like this. And for negative values of input, output will be 0. This is the V0 versus Vi plot of a precision half-wave rectifier. Okay, which can be easily made by combining one op amp with a diode. Okay, so diode need not be ideal, but op amp has to be ideal. Okay, so look at those circuits in a later session, not now. Okay, so if you look at this V0 versus Vi plot, definitely it is not a single straight line passing through origin. Okay, it is having two segments. Okay, this is one segment, there is another segment. So it is what, nonlinear. Or if you think of precision full wave rectifier, okay, precision full wave rectifier, precision full wave rectifier, that V0 versus Vi plot will be what, having that V shape. So when input is positive, output is same as input. When input is negative, output is negative of input. This is the V0 versus Vi plot of a precision full wave rectifier. Okay. Again, there is also not a single straight line passing to origin. So only instrumentation amplifier is what, linear. The other three are what, non-linear. So if you go back to the original question, you have to select the circuits which are non-linear, and they are what, B, C as well as D. Okay. Moving on to the next question, assume that the op amp in the figure is what, ideal. The current I, okay, you have to find the current, which is quite simple. Output is connected to what, negative input, so negative feedback, so virtual short will be valid. What is this current? 0. What is this current? It is 2 milliamps. What is the voltage at this point? V plus 0. So due to virtual short, V minus also 0. Now this 2 milliamps will flow like this, resulting in a drop of 4 volts. This is 0, I go from plus to minus, subtract the drop, this will be minus 4. This will also be minus 4. So what is the current through 2K in the upward direction? 0 minus minus 4 plus 4 by 2K, which is 2 milliamps. So what is this current? It is 2 milliamps. Now if you look at this point, 2 both are entering, I is also entering. So I think I is minus 4 milliamps. Okay, so 2 plus I plus 2 equal to 0. So I is what? Minus 4 milliamps. Okay. Sir, please solve PYQ EC 2025 differential amplifier question. I think you can go to our GATE solutions video. So on the day of GATE exam, we have done a live session where we solved the entire paper. Okay. So you can easily find that video. In that session, you will find the answer to whatever question you are asking for. Okay. So this amplifier, the circuit of figure uses an ideal op amp. Okay. This op amp is what, ideal for small positive values of Vin. Okay, when Vin is small positive, the circuit works as. Okay, I told you what earlier, whenever you have op amp in combination with diodes or transistors, etc., you should always assume that initially the diode or the transistor is off. So here also, if you assume that initially the diode is off, it behaves like an open circuit. Now this current 0 because initially diode is what, off. Okay, and then this current will always be 0. This is 0, this is 0, and this current is also 0. This Vn will appear here. now V plus is always 0. If Vin is positive, then V minus will be greater than V plus, then your output will be what? Minus V sat. Now for the diode, if the N side is connected to what? Minus V sat, then only the diode will be on. That is why they said for small positive values of Vn. Only when Vn is positive, whether it is small or large, as long as Vn is positive, then only the diode will be on. Only when diode is on, you can say the output is connected to what? The negative input terminal. Only then the op amp will be in negative feedback. Only then you can use what? Virtual short. So for in the same circuit, when input is negative, diode will be off. No negative feedback. Okay. That's all. So for positive values of input, diode will be on, and then virtual short will be applicable. Then the current through R will be odd. I think this circuit we have just discussed. Okay, exact same circuit. We found output to be what related to the input in a logarithmic way. So it is what a logarithmic amplifier. You just have to identify the circuit. It is what logarithmic amplifier. Okay, fine. The output voltage V0 of the circuit shown in the figure. Okay. See, please look at the screen. Here, some op-amp circuit is given and you have to find the output voltage. But the first thing that we can observe is this, that the output is connected to what? Negative as well as plus input terminals. Okay. In such a case, first you need to ascertain or decide the type of feedback. Is it negative or positive? If you find that it is negative, then only you can use the concept of virtual short. Okay. So how do you find the type of feedback? I said just imagine that at the output of the op amp you have applied some voltage Vt, and then you try to find what are V minus and V plus in terms of Vt, whichever is bigger, that will be the type of feedback. Okay. And while finding type of feedback, all other sources you have to make it 0. So 2-volt source, when you make it 0, it becomes short circuit. This current will always be 0. So this current and this current both are equal. So what is the voltage at this point? It is going to be what? Vt into 10k upon 10k plus 100k. Vt into 10k by 110k, just 10 V1 by 11. Okay. Similarly, when you apply Vt here also it will be Vt. Again, this current 0. So these two currents will be what? Equal. Voltage at this point 0. So 10k and 5k in series between Vt and ground. Vt into 5k upon 5k plus 10k, which is Vt by 3. So I'm getting the following values for V minus and V plus. V minus, we are getting Vt by 3. V plus, we are getting 10 V1 by, 10 Vt, not V1, 10 Vt by 11. No, I think I made a mistake. This is this will be Vt into 10k by 110. 10 by 110 Vt. 10 by 110 is not 10 by 11, it is 1 by 11. 1 by 11 Vt. That is a mistake. 1 by 11 Vt is same as what? Vt by 11. Now you compare V minus and V plus. V minus is what? Vt by 3. V plus is what? Vt by 11. Clearly Vt by 3 will be what? Greater than Vt by 11. V minus greater than V plus. And this means the op amp will be in negative feedback. Now that you know op amp is in negative feedback, now we can use the concept of virtual short and find the output. Okay, which is quite simple. What is this current? 0, because of which these two currents will be equal. What is the voltage at this point? V0 into 10, okay, which is V0 by 11. The voltage at this point is what? 2. Here it will be V0. What is this current? 0. Because of which these two will be in series. Now 5K and 10K both are in series between 2 and V0. So directly we can write the voltage at this point in terms of 2 and V0. Multiply 2 with 10K, multiply V0 with 5K. So 2 times 10, 20 plus V0 times 5 V0 upon 5 plus 10, which is 15. So what is V plus V0 by 11? What is V minus this? When you equate V plus and V minus, what is V plus V0 by 11? V minus is what? 20 plus 5 V0 by 15. From here we can find the value of V0. When you cross multiply, 15 V0 is equal to 220 plus 55 V0. 55 minus 15 is what? 40. 40 V0 is equal to 220. So V0 is what? 220 by 40 or 22 by 4. What is 22 by 4? I think 5.5. That's correct. Very good. V0 is 5.5. Okay. Look at the next question. Again, an op-amp circuit is given. This is the input. This is the output. The question is what to find the voltage gain V out by V in. Okay. Of course, the op-amp is ideal and it is in negative feedback. So let's do the analysis. What is the voltage here? 0 because of virtual short. What is this current? 0. Ohm's law, what is this current? V in minus 0 by 1K, which is V in by 1K. Can this current flow like this? No, because ideal op-amp input current is 0. So how will this current flow? It will flow like this. So what is this current? V in by 1K, same as this current. What is the resulting drop across 10K current multiplied with resistance? It is 10 V in. Remember, the voltage at this point is same as this point, which is 0. This is 0. You go from plus to minus, subtract the drop. The voltage at this point will be what? Minus 10 V in. So what is this current in the upward direction? 0 minus minus 10 V in, which is plus 10 V in by 1K. 10 V in by 1K. Okay. See, if you look at this point, V in by 1K entering. From the bottom also 10 V in by 1K entering. So at this point, this current and this current will get added. What is this current then? V in by 1K plus 10 V in by 1K, which is 11 V in by 1K. What is the resulting drop across 10K? Multiply the current with resistance. 11 V in by 1K times 10K. Kilo and kilo will get cancelled. I think you'll get 110 V in. Now, this point, the voltage is what? Minus 10 V in. You go from plus to minus, subtract the drop. Minus 10 V in minus 110 V in is what? Minus 120 V in. So that is V out in terms of V in, minus 120 V in. Question is what? V out by V in. So the answer is what? Minus 120. Alright, moving on to the next question. The wiper of a 20 kilo ohm potentiometer. So this thing is what? A variable resistance whose value is 20 kilo ohms. Okay. So the maximum resistance that you can have from this part is what? 20 kilo ohm. Okay. That is the meaning. In the figure, the wiper. Okay. This is the wiper. Okay. This is the wiper. Is positioned halfway. Halfway means what? In the center, in the middle, exactly at the center. Okay. Then the voltage V0. Okay, this voltage you have to find. Please understand the meaning of this. This 20 kilo ohm thing there is a long resistor. From this end to this end, the resistance is what? 20 kilo ohms. Okay. And then a wiper is connected exactly at the center. Exactly at the center. Okay. So what is this? What is this resistance? It will be 10K. What is the resistance of the lower half? Another 10K, because this is a 20 kilo ohm part. End to end, the resistance is what? 20K. From this end to the center, 10K. From the center to the other end, again 10K. Okay. So what you should understand is this. It's like having two resistors. Okay, 10K, 10K, and the point, I mean, the node in between those two is connected to what? This 10K. Okay, that is the circuit, and you have to find what the output. See, so this potentiometer thing, 20K, I'll write like this: 10K, 10K, and this 10K is what? This one. And then you have the rest of the op-amp circuit. This is 2 volts. Yes or no? This entire thing is what? Ground. This is 2 volts. $15K. What is the voltage at this point? 0, because of virtual short. V plus 0, V minus also 0. Okay. And then what? I mean, you can do in number of ways. If you assume the voltage at this node to be some Vx, you can write KCL at this point. Okay. What is this current? Vx minus 2 by 10K. What is this current? Vx minus 0 by 10K. What is this current? Also Vx minus 0 by 10K. At this point, if you write KCL, you'll get Vx minus 2 by 10K plus Vx by 10K plus Vx by 10K equal to 0, since all three currents are leaving this node. Now 10K will get cancelled out because that is LCM, it gets multiplied with 0. I think 3Vx is equal to 2. You will get Vx is equal to 2 by 3 volts. Vx is equal to what? 2 by 3. Once you get this Vx, this circuit, it is like the inverting amplifier. Vx is like the input to that inverting amplifier. Input R1, R2, output plus terminal connect to ground. What is the gain of the inverting amplifier? Minus R2 by R1, minus 15K by 10K, which is minus 3 by 2. So V0 is what? Minus 3 by 2 Vx, but Vx is what? 2 by 3. So minus 3 by 2 into 2 by 3. Everything gets cancelled out. You'll get minus 1 volt. So my answer is minus 1 volt. Okay, that is option B. Karthik is asking up to what time this live will run. Until I complete all the problems. Okay. So we are going to discuss all problems that are related to ideal op-amp in negative feedback. Once we complete all problems, then only the session will end. Okay. Look at the next question. The value of V0. The value of V0 in the circuit shown in figure. Okay. So some circuit is given, you have to find V0. Again, first thing to note is what? The output is connected to negative as well as positive input terminal. So you might be wondering whether the feedback will be positive or negative, but let me tell you, the feedback is negative. Okay. Why? You can do the same usual analysis where you apply some voltage Vt at the output of the op amp, and then all other sources you make it 0. So current source, it becomes 0, it becomes open. This current always is what, 0. This is 0, this is 0, and this is also 0. Then this drop 0. So drop 0, it means this point and this point both are at same potential. So what is V minus? It will be Vt. When you apply Vt here also it is what, Vt. This current 0, so these two currents will be equal. Voltage division, the voltage at this point will be Vt into 20 by 20 plus 30, 2 by 5, which is 0.4 Vt. So what is V plus? It is 0.4 Vt, which is bigger. Vt is greater than 0.4 Vt, or V minus is greater than V plus. That means this op amp is also in negative feedback. Once you know that op amp is in negative feedback, we can use the concept of virtual short. Okay. Let us now do the analysis and find the value of V naught. Okay. Virtual short, it means this point both are at same potential. Now if you take this point is common to both 10K and 30K. This point is common to 10K and 30K. Even though these two are two different points, but still these are at same potential. What it means is, because these two are at same potential because of virtual short, this drop and this drop both will be equal. Okay. This current anyway is always 0. So this 0.3 milliamps will flow through this as well, resulting in a drop of 0.3 times 10, which is 3 volts. Okay. Just now I told you this drop and this drop both are equal. So even this thing will also be 3 volts. So 3 volts across 30K, the current through 30K will be 3 divided by 30, which is 0.1 milliamps. Once again, this current is 0, so this current is also 0.1 milliamps. So 0.1 milliamps through 20K, the drop will be 2 volts. Now you start from this point, which is ground, 0 potential, go from plus to minus. This will be minus 2. Again, you go from plus to minus. This would also be, this will be minus 5. So what is the answer? V naught equal to what? Minus 5. Very good. Good. All right. Look at the next question. There's a circuit that has two op amps. Okay. You have to find this output voltage V naught divided by the input voltage Vi. There are two op amps. If you look at each op amp, this op amp, the output through 3R is connected to what? Negative input, negative feedback. If you look at this thing, even for this op amp, output through 4R is connected to what? Negative input. So there is also a negative feedback. So both op amps are in negative feedback. So we can use virtual short for both the op amps. That point has to be clear. And this is the input voltage Vi. So what is the voltage here? It is Vi. In fact, this part of the circuit is what? A non-inverting amplifier. This Vi is what? The input applied at the plus input terminal. And then this 3R is like R2 and this R is like R1. And the voltage at this point is what? The output of the non-inverting amplifier. What is the output of the non-inverting amplifier? Tell me. Vi times 1 plus R2 by R1. 1 plus 3R by R, which is 4 Vi. So what is the voltage at this point? 4 Vi. Now if you look at this part of the circuit, input, this is like R1, this is like R2. Input R1, R2, output plus terminal connected to ground. So this is what? The inverting amplifier, whose output will be at this point. So what is the output here? Input times minus R2 by R1, which is minus 4 Vi. Now whatever V naught we need to find is what? The potential difference between this point and this point. 4 Vi minus half minus 4 Vi, directly we can tell V0 is what? 8 Vi. So what is V0 by Vi? It is 8, which is option B. Okay. Moving on to the next question. Okay, same question. Here again, there are two op amps. You have to find the output V0 in terms of this V is some kind of input voltage. Okay. So you have to find output in terms of the input voltage V. Look at each op amp. This op amp output is connected to what? Negative input. So this is a negative feedback. Good. This op amp also the output is connected only to what? Negative input. So both op amps are in negative feedback. So we can use virtual short for both the op amps. Let us use virtual short and find the output in terms of the input V. Look at this op amp, already the plus input terminal is connected to ground. So what is the voltage here? V plus equal to what? 0. What is this current? It is 0. You can find this current, right? Ohm's law, V minus 0 by R1, which will be V by R1. Yes or no? V minus 0 by R1. Because this current is 0, even this current will be what? V by R1. Okay. Now, due to this V by R1 current through this resistor, you'll have some drop across this. Okay, you'll have some drop across this, and that drop we'll call it some Vx or Va. Okay, so what is Va? V by R1, which is the current times the resistance. So VR by R1 times, oh sorry, 1 plus delta, that is Va. So this is 0, you have a drop of Va, so the voltage at this point will be what? Minus Va, correct? What is the voltage at this point? Again, this op amp V plus 0, V minus also 0. Okay. Now this entire thing is like a node. This entire thing is what? One single node. What is this current? It is 0. So what is this current? 0 minus minus Va, which is plus Va divided by R. So this is Va by R. What is this current? V minus 0 by R1, which is V by R1. What is this current? 0 minus V0 by R2, which is minus V0 by R2. Now, if you look at this node, three currents are flowing at the node. One current is entering, another current is leaving, third current is also what? Leaving. So this current is equal to what? Sum of these two currents. So I'm just writing KCL for this node. So V by R1 is equal to VA by R plus minus V0 by R2. Okay. Or I can say V0 by R2 is equal to VA by R. What is VA? VA is here. Okay. So in place of VA, I'll write VR divided by R1 times 1 plus delta. This is VA, and then your VA gets divided by R plus minus V0 by R2. Okay, minus V0 by R2 has come to this side, and V by R1 will go to the other side. Okay, so minus V by R1. So here, this R and this R will get cancelled, and LCM is what? R1. Right hand side LCM is what? R1. So when you take LCM, V times 1 plus delta minus V, I think you'll get V times delta. So finally, your output voltage will be what? V times delta times R2 by R1. Okay. V times delta times R2 by R1. I hope it is there in the options. It is option B, V delta R2 by R1. In the op-amp circuit given in figure, the load current, okay, I have to find the load current. Again, this is also quite a popular circuit. This is actually what this entire circuit with respect to RL will behave like what? Voltage controlled current source, okay. Here also, first of all, the output is definitely connected to what? Negative as well as plus input terminals. So in which case, if you try to check the type of feedback, if you try to check the type of feedback, okay, just a second. Okay. If you try to check the type of feedback, how do you do that? By applying some voltage Vt at the output, making this input Vs 0, and then by finding V minus and V plus, you'll always find that, you'll always get V minus to be greater than V plus. That indicates what? Op amp is in negative feedback, okay? So once you know op amp is in negative feedback, we can simply use virtual short, okay? What is that virtual short? This point and this point both will be at same potential. What is this drop? The load current times the load resistance, right? So this will be ILRL. This is ground, you go from minus to plus. What is the voltage at this point? It will be ILRL, okay? Now your V plus is what? ILRL. Now because of virtual short, V minus is also what? ILRL. What is this current? It is 0. What is this current? Ohm's law. Vs minus, let me write it, Vs minus ISRL by R1. What is this current? Same as this current, which is Vs minus IS, RL by R1. Multiply the current with resistance, then you will get the drop. When you multiply the current with R1, R1 will get cancelled. Directly I can write the drop across this R1 as what? Vs minus ISRL. What is the drop across this R1? Now because of virtual short, see this point is common to both this R1 and this R2. And because of virtual short, this point and this point both will be at same potential. This entire thing is common to both R1 and R2. These two are at same potential. What it means is this drop and this drop both will be equal. So already we know this drop, the same drop, we can write it down across R2. So Vs minus ISRL, okay? That's all. Now the only thing that we can do is to write KCL at this node. Okay, so what is this current? ISRL minus 0 by R2. What is this current? It is already there, IL. Now due to this drop, you can compute the current drop divided by resistance. This current, input current, always 0. So at this point or at this node, leaving, no current is entering. Sum of the three currents is equal to what? 0. Starting with this current, it is ILRL by R2 plus IL plus this current, which is Vs minus, oh, I'm sorry, this is not Is, this is IL. Because this current is what IL and this drop is what ILRL. The voltage at this point is also what ILRL. I think everywhere I need to change. IL is also IL. Here also it is IL. Okay. Vs minus ILRL by R2 equal to 0. Now, if you observe, the first and last terms will simply get cancelled out. Okay, ILRL by R2 minus ILRL by R2 will get cancelled out. So finally, we'll get IL equal to minus Vs by R2. This is a standard circuit, but that is the answer. Okay, minus Vs by R2, which is option A. So this load current, which is the current through RL, is independent of the load resistance. So whatever be the value of RL, the load current will always be what? Minus Vs by R2. So it is as if the load RL is connected across what? Ideal current source. That is why in the very beginning I told you this circuit with respect to RL will behave like ideal current source. Okay. Consider the inverting amplifier. Okay, this is what an inverting amplifier. Input R1, R2, output, plus terminal connected to ground. Using an ideal op-amp shown in the figure, the designer wishes to realize the input resistance seen by the small signal source. There's the small signal source. Okay. What is the input resistance? It is R1. Okay, so if you replace Vin with Vt and find Vt by It, you will get Rin to be what? R1. And we want the input resistance to be as large as possible. So R1 or Rn should be as large as possible. Okay, while keeping the voltage gain. Voltage gain means what? Gain of any inverting amplifier is what? Minus Rf by R1 in the range minus 10 to minus 25. So the gain should be in the range minus 10 to minus 25. Okay. You can say minus 25 to minus 10, whatever it is. So what it means is the value of Rf by R1, this ratio Rf by R1 should lie in between 10 and 25. Okay. So 10 less than Rf by R1 less than 25. This is the range of Rf by R1. So given that this is the range of Rf by R1, and also requirement is what? The Rn should be as large as possible, for which R1 also should be what? As large as possible. The upper limit on Rf is 1 mega ohm. That means Rf cannot be more than 1 mega ohm. Rf less than or equal to what? 1 mega ohm. Rf less than or equal to 1 mega ohm. Then the value of R1 should be how much? That is the question. Okay. And this is quite simple. So Rf by R1 should be in between 10 and 25. So if you have to do it systematically, this is how you can do it. If you just invert all ratios in this inequality, if you just invert all the ratios, you'll get 1 by 10 greater than R1 by Rf greater than 1 by 25. Now you multiply throughout with Rf, then you'll get Rf by 10 greater than R1 greater than Rf by 25. Okay. Now remember, we want R1 to be as large as possible. Yes or no? Because we want input resistance to be maximum, for which R1 should be as large as possible. What is Rf by 10 greater than R1 greater than this. Okay, fine. Please look at this part. R1 less than Rf by 10. Now we want, so what is this Rf by 10? Is it not like the maximum value of R1? Yes or no? R1 less than something, that something is what? Maximum. Okay. So R1 max will occur when Rf is also what? Max. So R1 max RF max is what? 1 mega ohm. Okay. 1 mega ohm by 10, which is 100 kilo ohm, which is 100 kilo ohm. That is the answer. So if you choose R1 to be 100 kilo ohm, then the input resistance will be what? Maximum. Okay. In fact, the input resistance is what? R1 itself. Okay. So R1 100K and then RF is what? 1 mega ohm. Then the gain will be what? Minus 10. So gain will be what? Minus 10. All right, look at this question. In the instrumentation amplifier shown in figure, okay, there is the instrumentation amplifier. Previously also we have drawn a similar circuit like this. If the switch SW, if the switch SW is changed from position A to position B, the values of the amplifier gain G before and after changing the switch respectively are, okay, fine. So in one case, the switch is connected to what? A. In the next case, the switch is connected to what? B. In both the cases, you need to find the gain. Gain means what? This output. Okay, this output is missing. This is the output. So gain, so this being what? An instrumentation amplifier, its output will be something like A times V2 minus V1. That is the form of the output. When you do the analysis, you'll get the output like that. Okay, V2 minus V1 times some gain A, and that gain you have to find in both the cases. Initially switch connected to what? A, what is the gain? And then switch connected to B, again what is the gain? Okay, so those two gain values you need to find, which is quite simple. Okay, so in this case, switch connected to what? A. The switch is connected to A will be like this. Then nothing is connected here, so this you can remove. Okay. Now this op amp is a negative feedback. This op amp is also a negative feedback. This is also a negative feedback. So the point, I mean, the way to do the analysis is what this. I mean, this is how we usually do in class as well. If this is the output, we assume the voltage at this node to be some V3, and the voltage at this point we assume it is some V4. So this circuit is what? The standard, difference amplifier, for which the inputs are V3 and V4, and it is ideal, okay, because this ratio of 500K by 50K is what? 10. Here also 500K by 50K is what? 10. Okay, so what is the gain of this difference amplifier? It is 10. So V0 can be written as 10 times the gain of this block times V3 minus V4. So 10 times V3 minus V4. That is how you can write down the gain. But the actual output must be, but the output must be in terms of the actual inputs V1 and V2. Okay. Now you have to do some analysis and find V3 minus V4 in terms of V2 and V1. Okay. When you apply V2 here also the voltage becomes V2. And here also the voltage becomes V1. Okay. Because this current is 0, this current and this current both will be equal. Because this current is 0, even this current and this current both will be equal. So what is the current flowing from V4 to V3? V4 minus V3 upon 100K plus 22.2K plus 100K. Okay. Or you can take current direction from V3 to V4. Okay. Because our output expression has V3 minus V4. I will take in the other direction. Okay. You can take any direction, by the way. So this current is equal to this current is equal to this current. So what is the current from V3 to V4? You should say it is V3 minus V4 upon this plus this plus this. So V3 minus V4 upon 100 plus 22 plus 100, which is 222.2 kilo ohms. And this current is also same as the current through 22.2K in the upward direction, which is V2 minus V1 by 22.2K. That's all. So from here, your V3 minus V4 can be written in terms of V2 minus V1. I think 222.2 by 22.2 is what? Roughly 10. Okay, so 10 times V2 minus V1. Okay. Okay, anyway, yeah, it is 10. So V0 will be, in place of V3 minus V4, we can write this 10 times 10 will become 100 times V2 minus V1. So what is the gain when the switch is connected to A? The answer is what? 100. What is the gain? It is 100. Same circuit, we need to find the gain when switch is connected to point B. So this time, the same switch is going to be connected to our point B. Like this. Now you can get rid of this one. Okay, rest of the analysis is what? Same as before. So even now, if you call the output voltage as V0, this block, it is what? The same difference amplifier. Let us call the voltage here as V3 and voltage here as what? V4. Okay, so this will be V1, this will be V2. First of all, V0 in terms of V3 and V4 is what? V3 minus V4 times 10. Okay. Once again, this current is equal to this current is equal to this current, because for the op amp, the two input currents are 0. So what is the current from V3 up to V4? V3 minus V4 upon 100 plus 10.53 plus 100. So V3 minus V4 by 210.53 kilo ohms is equal to, what is the current through 10.53 in the upward direction? V2 minus V1. V2 minus V1 by 10.53 K. So from here you can find V3 minus V4 in terms of V2 minus V1. Okay, which will be 210.53 divided by 10.53, which is 19.99, approximately 20. So 20 times V2 minus V1. Now you go back to the first expression. In place of V3 minus V4, you write this. You'll get 200 times V2 minus V1. So what is the gain? In this case, it is 200. So in the previous case, I think the gain was 100. When switch is connected to A, the gain is what? 100. When switch is connected to B, the gain becomes 200. Okay, 100, 200, which is option C. Moving on to the next question. A dual op amp, dual means what? Two op amps are there. A dual op amp instrumentation amplifier. So this, they are saying this is also what? Instrumentation amplifier. Instrumentation amplifier is what? Difference amplifier. Okay, two inputs will be applied. Your output will be proportional to difference between the two applied inputs. Okay, so what is the expression for the output of the amplifier in terms of the two inputs, that is V1 and V2? Okay, now what about feedback? What about feedback? If you start here, say for negative feedback, both the op amps should be part of a loop that has a negative loop gain. Okay, what is the gain from here to here? What is the gain from here to here? Positive, because you are going through resistors, the gain is what? Positive. What is the gain from here to here? It is negative, because you are going from negative input to output. What is the gain from here to here? Through resistors, always the gain is what? Positive. Let me write it properly. This is positive. Okay. And again, from here to here, you are going from negative input to output, the gain will be what? Negative. Now, what is the overall gain around the loop? Positive into negative into positive into negative. Positive. So the overall loop gain is what? Positive. That means the two op amps will be in positive feedback. But for the circuit to behave like an amplifier, any amplifier should have negative feedback. If at all there is feedback, that amplifier should be part of a circuit that has negative feedback, not positive feedback. Because in positive feedback, the overall circuit will be one second, just a second. I told you what in yeah. In positive feedback, the overall circuit becomes non-linear, but amplifier is supposed to be what? A linear circuit. Okay, so there has to be some modification in the circuit, otherwise the circuit will not function as an amplifier at all. So for that, the modification that you should do is what? You have to interchange the plus and minus for any one op amp. For example, you take this op amp, you make this thing plus, and then you make this thing minus. Then if you change this minus to plus, then from here to here the gain will be what? Positive. Positive, positive, negative, positive. Then the overall loop gain will be what? Negative. Then both op amps can be said to be in negative feedback. Then we can use what? Virtual short and so on. Okay. So the given circuit, there is a mistake. Okay. So you have to interchange the input terminals, the polarity of the input terminals, at least for one op amp. You can change it for this op amp or for this op amp, not for both the op amps. Okay, only for one op amp you need to change. So let us say for this op amp you have indeed changed. Okay. So now the overall loop gain is negative and so on. So now let's do the usual negative feedback analysis. This V2 will appear here. So what is the voltage here? V2. This current 0. This V1 will appear here. So what is the voltage here? V1. This current again 0. Okay. If you call this, actually not required. What is this current? Ohm's law, V1 minus 0 by R2, which is V1 by R2. What is this current? Same, V1 by R2. What is this drop? Current into resistance, which is V1 R1 by R2. This is V1, you go from minus to plus, add the drop. So what is the voltage at this point? It will be V1 plus this drop, correct? Which will be V1 times 1 plus R1 by R2. Okay. And then let us call this current as, sorry, I will take the opposite direction. I can take any direction, by the way. I will take this current to be I1. I will call this current as I2. At this point, I2 is entering, I1 is leaving. So I2 equal to I1. What is I2? Current through R2 in the downward direction. V0 minus V2 by R2. What is I1? V2 minus this upon R1. Okay. So V2 minus V1 times 1 plus R1 by R2 whole divided by R1. That's all. From this equation, we need to do some manipulation and find V0 in terms of V1 and V2. Since they are saying that it is what? Instrumentation amplifier, your output should be proportional to either V1 minus V2 or V2 minus V1. Okay. So in fact, your output must be proportional to V2 minus V1. Your output should be proportional to V2 minus V1. Let's see if we get that or not. Okay. So this R2, I will send it across to the other side. Then minus V2 will become plus V2. V2 plus V2 R2 by R1. V2 plus V2 R2 by R1. And then minus V1. And then minus V1. Sorry, minus V1 by R1. Oh no, wait. V2 R2 R1, this is correct. This is also correct. Minus V1 R2 by R1. And then you will have, see this, R2 R2 cancel out, R1 R1 cancel out, you'll have minus V1. This is correct. Okay. So V2 times 1 plus R2 by R1 minus V1 times again 1 plus R2 by R1. That's all. So V2 minus V1 times 1 plus R2 by R1. So as you can see, your output is proportional to the difference between the two applied inputs, that is V2 and V1. So it computes the difference, it is amplified by, the difference is amplified by a factor of 1 plus R2 by R1. So what is the gain of the instrumentation amplifier? 1 plus R2 by R1, okay? Which is option A. Let us move on to the next question. For the circuit shown in the following figure, okay, this circuit, the capacitor C 1 microfarad cap is initially uncharged. Fine. The initial voltage across the cap is 0. At t equal to 0, this switch is closed at t equal to 0. Okay. The voltage Vc across the capacitor at t equal to 1 millisecond is how much? Okay. Okay, fine. So what is Vc of 0? It is 0 because they are saying initially the cap is uncharged. Okay. So when you close the switch, what happens? When you close the switch, okay, let us say the switch is what closed. The moment you close the switch, immediately the op-amp will go into what? Negative feedback, because the output through the cap is connected to what? The negative input terminal. The op-amp goes into what? Negative feedback. Negative feedback will immediately lead to what? Virtual short. So V plus is 10 volts anyway. V minus will become 10 volts. Okay. And if you call the output voltage of the op-amp as V0, then your V0 will be what? This is 10. You go from minus to plus. at the drop, so 10 plus Vc. So V0 can be written as 10 plus Vc. Also, what is this current? It is 0 because ideal op amp. By the way, I'm analyzing circuit for t greater than 0. Okay. In the figure shown above, the op amp is supplied with, the power supply voltages are also mentioned, which are plus 15 and minus 15. Okay. So what is this current? 10 minus 0 by 1K, which is 10 milliamps. So this 10 milliamps will flow through what? The capacitor as well. Okay. So through the capacitor, as you can see, the current is flowing from plus to minus. That means the cap will get charged. Okay. Initial voltage across the cap 0. Also the current through the cap is what? Constant, because the input is constant, this current is constant, current through the cap is also constant. Whenever you have a constant current flowing through a cap, the voltage will change linearly. Yes or no? I is equal to C dV by dt. dV by dt is what? I by C. If I is constant, then the rate of change of voltage across the cap is also constant. Okay. In fact, the current is known 10 milliamps. Okay. So 10 milliamps divided by the capacitance is what? 1 microfarad. Okay. Which is 10 power minus 6. 10 milliamps is what? 10 into 10 power minus 3, which is 10 power minus 2. Okay. 10 power minus 2. So this is 10 power minus 2 divided by 10 power minus 6, which is 10 power 4 volts per second. What is it? 10 power 4 volts per second. Okay. You can also write this 10 power 4 volts per second as 10 volts per millisecond. So what is the rate of change of voltage across the cap due to this 10 milliamp current flowing through the cap? It is 10 volts per 1 millisecond. What it means is, in 1 millisecond, the voltage across the cap will increase by 10 volts. Okay, in a linear manner, because the current is constant. Okay. What is the equation? The voltage across the cap at t equal to 1 millisecond. Okay. You see the output is what? 10 plus Vc. And remember, the output can only increase up to what? See, as Vc increases, V0 also will increase, because V0 is what? 10 plus Vc, right? Yes. Now there is a possibility that V0 can become equal to what? 15, or V0 can increase and become what? 15. Once V0 reaches 15, the output gets saturated. In spite of the op amp being a negative feedback, from now onwards, virtual short will no longer be valid. So let's find out whether by this time instant, by t equal to 1 millisecond, if the output can get saturated or not. See, for the output to get saturated to what? Plus 15, the voltage across the cap should become 5 volts. Yes, on voltage across the cap should become 5 volts. Okay. For that initial voltage across the cap is what? 0. If the voltage across the cap becomes 5, what is the change in voltage? 5 volts. Now, what is the rate of change of voltage across the cap? 10 volts in 1 millisecond. Now, what is our required change in voltage for the cap? 5 volts. For 10 volt change, you require 1 millisecond. For 5 volt change, you'll obviously require half a millisecond. So t equal to 0.5 millisecond itself, the voltage across the cap will become 5. When voltage across the cap becomes 5, 10 plus 5, output of the op amp will become 15. Output gets saturated. Okay, so t equal to 0.5 milliseconds, voltage across the cap becomes 5, output voltage becomes 15. Your output becomes 15. Yes, so from here onwards, the output will stop increasing. Yes, output will no longer increase. Okay. But the question is what? To find voltage across the cap at t equal to 1 millisecond. 1 millisecond is what? 0.5 milliseconds after t equal to 0.5 milliseconds. Yes or no? From 0.5 milliseconds, after 0.5 milliseconds, you will get t equal to 1 milliseconds. So from zero point 0.5 up to 1, the duration is what? 0.5 milliseconds. So you need to understand what happens to the capacitor from t equal to 0.5 to t equal to 1 millisecond. Okay, that is the whole idea. Let's see it. So for t greater than 0.5 milliseconds, once your output gets saturated, virtual short is no longer valid. You can remove the op amp, yes, and you can draw only this RC circuit separately. Okay, see. So you have 1K, this end is connected to what? Ground, and then you have the capacitor of value 1 microfarad, across which the voltage is what? VC, and this end is connected to what? The output of the op amp, which is going to be fixed at plus 15 volts. Now for this simple RC circuit, the input is what? Plus 15 volts, which is a DC voltage. RC circuit driven by DC input, everything will change exponentially. Every node voltage, every branch voltage will simply start from initial value and reach its final value in an exponential manner. Okay, even VC will do the same. Okay, so what is VC initial? Remember, this circuit starts at t equal to 0.5 milliseconds. Okay, so initial voltage across the cap is what? 5 volts, because at t equal to 0.5 milliseconds, the cap will get charged to what? 5 volts. Then only output gets saturated, then only you'll get this RC circuit. Okay, if at all this RC circuit reaches steady state, it'll reach what? DC steady state. At DC steady state, the cap will act as an open circuit. When the cap is open, what is the voltage across the cap? 15 minus 0. When cap is open, no current flows through R. This 0 will appear here, 15 minus 0. So what is VC final? It is 15 volts. That's all. So what will VC try to do for t greater than 0? VC will try to go from 5 up to 15 in an exponential manner. What is the time constant? It is just R into C. R is 1K, which is 10 to the 3. C is 1 micro, which is 10 power minus 6. So it is what? 1 millisecond. That's all. Now you want to find the output at t equal to 1 millisecond. From 0.5 up to 1 millisecond, what is the interval? 0.5 milliseconds. Okay. So we can easily write what is the expression for VC as a function of time using that final initial formula. Okay. Final plus initial minus final times e power minus t by tau. Okay, here if you want, you can do that small modification, because this circuit is starting at t equal to 0.5 milliseconds, and we are trying to find what is the output at any instant for t greater than 0.5. So it is as if the circuit is delayed by 0.5. So replace t with t minus 0.5. Okay. T minus that 0.5 divided by RC, which is 1 millisecond. Okay. Now final value is what? 15. Initial is what? 5. So 15 plus 5 minus 15 is what? Minus 10. So 15 minus 10 e power minus of t minus 0.5 divided by 1 millisecond. Now you substitute t equal to 1 millisecond. So we see at t equal to 1 millisecond. So when you put t equal to 1 millisecond, 1 millisecond minus 0.5 millisecond is what? 0.5 millisecond. 0.5 by 1 is what? 0.5. So it'll be this 15 minus 10 e power minus 0.5. Let's find out what is the answer. Okay, 8.93. That is the voltage across the cap at t equal to 1 millisecond. Okay, so in our virtual short is not valid, which is when output is saturated. So this is how you do the analysis. Okay, so it is as if the op amp is not there in the circuit. It is there, and it will act as some sort of a comparator because output is saturated, right? Yes. So your V minus, I mean, this is V minus. Okay, by the way, after the capacitor, in between cap and resistor, whatever node you have, that is V minus. Okay, so your V minus will go from, so V minus initially is 10. Okay, because up to t equal to this 0.5 milliseconds, virtual short is valid. So V minus initially is 10, but finally it goes to 0, because finally when this RC circuit reaches DC steady state, cap becomes open, this ground will appear here. So V minus for t greater than 0.5 will always be some value that is less than 10, whereas V plus is always 10. V minus is always some value that is less than 10. So V plus is always more than V minus, which means the output will always be plus V sat. It makes sense, okay? Anyway. 8.93 volts. That is the answer. All right, guys, moving on to the next question. So again, there is this op amp. Along with the op amp, there is in the feedback path, a two-port network is connected, okay? And this side, the input is applied. The Z parameters of the two-port network, two-port feedback network. So in the feedback path, this two-port network is there, and its Z parameters are the following. Z11, Z22, both are 11 kilo ohms. Z12, Z21, both are 1 kilo ohm each. The gain of the amplifier, gain means what? V0 by Vi. Some gain means V0 by Vi. Okay, so let's do the analysis. Say, whenever the two-port network is given, it is always better to identify the four terminal variables for the two-port network. What are the four terminal variables of a two-port network? V1, I1 on the input side, V2, I2 on the output side. Okay, so immediately you place mark this input voltage or voltage across port 1 as V1 and this current as I1. This is V2 and this is I2. Okay. What is the voltage at this point? I'll just change the color. Yeah. What is the voltage at this point? 0. Why? Because V plus is 0. Due to virtual short, V minus is also 0. Now this point is connected to this terminal. Terminal 1 is at 0 potential. Terminal 1 prime is connected to ground, so 1 prime is also at 0 potential. So what is the difference between 1 and 1 prime? 0 minus 0, so V1 is what? 0. I hope you get it. Now you look at the other port between 2 and 2 prime terminals. 2 prime is connected to ground, so 2 prime will be at 0 potential. Terminal 2 is connected to what? V0. So here the voltage will be what? V0. So what is V2? Is actually V0. V2 is what? V0. V1 is 0. Also you can find this current Vi. We'll call this Vi, capital Vi. Vi minus 0 by 1K, which is Vi by 1K. Obviously, here the current is 0, so this current will flow like this. So what is this current? It is Vi by 1K. And this current is same as what? I1. Okay. Now for Z parameters, the first equation is what? V1 equal to Z11 I1 plus Z12 I2. What is Z11? 11K. 11K times I1 plus Z12, which is 1K. 1K times I2. But already we know I1 is same as what? Vi by 1K. And also V1 is what? 0. So in place of V1, I'll write 0. Okay, 11K times I1 is what? Vi by 1K. Vi by 1K. Plus 1K times I2. Here K and K will get cancelled out. I think you can write I2 in terms of Vi, and that will be minus 11 Vi by 1K. We'll use it a little later. Let us write the other equation for Z parameters. What is the other equation? V2 is equal to Z21 I1. Z21 is also what? 1K. So 1K times I1 plus Z22, which is 11K. 11K times 11K times I2. Now this V2 is same as what? V0. Yes or no? V2 is same as V0. So in place of V2, I just wrote V0. In place of I1, we can write Vi by 1K. When I write Vi by 1K, 1K will get cancelled. I just have Vi. Plus 11K into, in place of I2, I can write minus 11 Vi by 1K. K and K will get cancelled. Minus 11 into 11 is what? Minus 121. So Vi minus 121 Vi, which is minus 120 Vi. So what is the gain of this entire circuit? V0 by Vi. It is what? Minus 120. Okay, just have to carefully write the equations. Okay, the two defining equations for Z parameters in terms of the given Z parameters. Okay. Another way is what? Because it has symmetry. I mean, Z11 equal to Z22. It means what? It has symmetry. And Z12 and Z21 are both equal. That means it can be drawn as a purely resistive network. So using the Z parameters, you can draw one simple T-shaped network. You can draw one simple T-shaped network. Okay, the T-shaped network will be like this. Okay. So T-shaped network can be something like this. 10K, 1K, again 10K. So in place of this two-port network, if you want, you can draw this resistive network. So for this network, Z11 will definitely be 11K, Z22 also 11K, Z12 and Z21 both will be 1K. Okay. So you can replace this and do the analysis, but it's okay. I mean, not required. Okay. Look at the next question. So let me read the equation. This is op amp. For the op amp circuit, V0 is approximately equal to. So here they have used the word approximately. It means you can make any reasonable approximation that is required. Okay. See, this is the input source voltage. which is 10 volts. Okay, this op amp is clearly in negative feedback, so virtual short has to be used. Okay. Okay. See, please make the observation. At this point, okay, if I call this point as A, okay, between A and ground, I have this 95 ohm resistor, but also between A and ground, I got 100K and 1 mega ohm both in series. Okay, 100K and 1 mega ohm both in series. This is one thing. Okay, so from A to ground, you have 95 ohm and also 100K plus 1 mega ohm, which is 1.1 mega ohm. Okay, so it is something like this. If I call this point as A, some current will flow like this, 10 minus this voltage divided by 105. After that, some of that current will flow like this, the remaining current will flow like this. Okay, but what is the resistance of this path? From A to ground, one path resistance is what? 95 ohms. The other path resistance is what? 1.1 mega ohms, which is the part that has a much lower resistance, 95 ohms. So what is the approximation that you can make? You can neglect this current. You can assume if this current is I, then all that current, you can assume it flows entirely through what? 95 ohms, because this path has got a much higher resistance. So negligible current will flow here. That is the point. Okay, that is the approximation you have been asked to make. Okay, once you neglect this current, analysis becomes easy. Why? Then these two currents are equal, which means the 105 and 95 both are in series. We can apply voltage division. So what is voltage at point A? VA can be written as 10 into 95 upon 105 plus 95. Correct? Which will be 105 plus 95 is what? I think 200. 10 by 200 is what? 1 by 20. 95 by 20. Okay? 95 by 20 volts. And you can find the value 9.5 by 2 like that. Okay? I hope this is clear. Okay, so here we can assume 105 and 95 both are in series. Another thing is this. If I call this point as B, okay, some current will definitely flow here through 95, 10 minus B by 10 minus the voltage at B divided by 95. If I call this current as I, now at this point, this current can flow in two directions. Okay, this current has two paths, one like this, another like this. Okay, now this path has a resistance of 100 kilo ohms. This path has a resistance of just 105 ohms. Again, you can neglect this current. You can assume this current will entirely flow only through what? 105 ohms. In other words, you can assume 95 and 105 are both connected in series. That is the assumption that you can make. Then what is the voltage at point B? If you assume or if you neglect this current, because this is a high resistance path, so voltage at point B will be what? 10 into 105 upon 95 plus 105. Okay, I mean volts. Again, 105 volts by 20. Okay. Now if you observe, okay, this voltage we have called it VB. This voltage we have called it VA. Now please look at this part of the circuit. Okay, for this yellow color block, the two input voltages are what? VA and VB. Does it not resemble the difference amplifier? So this is 1 mega ohm, this is 100k, this is 1 mega ohm, again 100k. Is it ideal difference amplifier? Definitely yes. What is the condition for difference amplifier to be ideal? Ratio of these two must be equal to ratio of these two. 1 mega by 100k is what? 10. 1 mega by 100k again is what? 10. So what is the gain of this difference amplifier? 10. 1 mega by 100k is what? 10. So what is the output in terms of the two inputs VA and VB? 10 times VA minus VB, because VA is applied on the plus side, VB is applied on the minus side. So this yellow color block is what? An ideal difference amplifier. Okay. So V naught is equal to 10 times VA minus VB. Correct? 10 times VA minus VB. So earlier, by doing the two approximations, we found VA and VB. VA is 95 by 20, VB is 105 by 20. So 10 times 95 by 20 minus 105 by 20. 95 minus 105 is what? Minus 10. So 10 into minus 10 divided by 20, which is minus 5 volts. So what is the answer? It is minus 5 volts, which is option B. Okay. All right, look at the next question. The input resistance of the circuit shown in the figure. Input resistance means what? This is the input source. When you look in this direction, whatever you see, that is the input resistance. Okay. So how do you find the input resistance? Across the input port, you have to connect a test voltage source VT and call this current as what? IT. You have to find VT by IT. That's all. So what is the voltage at this point? It is VT. Yes, on the voltage at this point will be what? VT. What is the voltage at this point? Due to virtual short, V plus 0, V minus also 0. So what is this current? It will be Vt minus 0 by R, which is Vt by R. Now because this current is 0, even this current will be what? Vt by R. And then Vt by R flowing through 3R, the resulting drop will be what? 3 Vt. This is 0, you go from plus to minus, subtract the drop. So this will be minus 3 Vt. Again, Ohm's law, what is this current? Vt minus 3 Vt, which is 4 Vt divided by 2R, which is 4 Vt divided by 2R is what? I think 2 Vt by R. Now at this point, you can write KCL. From the left, IT is entering. On the right side, two currents are leaving. So IT is equal to Vt by R plus 2 Vt by R, which is 3 Vt by R. So the input resistance means what? Obviously Vt divided by IT, which is R by 3. So what is the input resistance? It is R by 3. Okay. That's correct. Option A. A differential amplifier is constructed using an ideal op amp as shown in the figure. The values of R1 and R2. R1 is 47K and R2 is 470K. The input impedance is seen looking into the terminals V1 and V2. Okay. So you are separately so there are two input terminals, right? You are not looking into the input port. You are separately looking into each input terminal. So when you look like this, how much input resistance do you see? Or how much equivalent resistance do you see? And when you look like this, into this first input terminal, again how much equivalent resistance you are going to see. Okay. So input resistance in by voltage source V1. So at V1 location you connect Vt, call this current as It, make this V2 0. When you make V2 0, this current, everything will be 0. Even this voltage will be 0. Due to virtual short, this voltage 0. Voltage at this point will anyway be Vt. So what is this current? Ohm's law, Vt minus 0 by R1, which is Vt by R1. So It is equal to Vt by R1. So what is the input resistance in this case? It is Vt by It, which is R1. And R1 is what? 47 kilo ohms. So one input impedance is what? 47 kilo ohms. Now you have to find out what is the input impedance looking into this input terminal. Okay. For which we need to connect the same voltage source at the second input terminal. Again, call this VT-IT. I mean, this is straightforward. Okay. You just have the series combination of R1 and R2. So this current will anyway be 0. So what is Vt by It? It is R1 plus R2. So what is the input resistance this time? It is R1 plus R2, which is 47 plus 470, which is 517 kilo ohms. So what are the two input resistances at the two input terminals? 47 and 517, which is option C. Okay. In the circuit shown below, the op amp is ideal. Okay, I mean, there are two op amps, both op amps are ideal. What is the output voltage? This op amp output negative terminal, negative feedback. This op amp also output connected negative terminal. So both op amps are clearly in negative feedback. Okay. Let's do the analysis by using virtual short. What is this current? 0. What is this? Drop 0. So what is the voltage here? 1. Virtual short, this is also 1. What is this current? 0. What is this current? 1 minus minus 2, 3 by 1K is what? 3 milliamps. So what is this current? 3 milliamps. Resulting drop is what? 3 volts. This is 1, you go from minus to plus. So what is the voltage here? It will be 4 volts. And again, this current is 0. So this 1K and this 1K both are in series. So what is the voltage at this point? V0 by 2. Now, if you apply virtual short, this 4 and V0 by 2 have to be equal. So V0 by 2 equal to 4. So V0 equal to 8 volts. So what is the answer? It is 8 volts. And that is option C. Assuming that the output in the circuit, I mean, not the output, op amp. Assuming that the op amp in the circuit shown below is ideal, the output voltage V0 will be. See here, it looks like the output is connected to what? The negative input terminal, but that is not really the case. Because irrespective of what the output is, V minus is always going to be 0. And it is what? Fixed. Yes or no? Because the minus input terminal is connected to ground. So V minus will always be 0. So if at all you do that loop gain test where you apply Vt here and try to find V minus will still be 0. Okay, so none of the output reaches the negative input terminal. So this op amp does not have any feedback at all. In fact, this 12 kilo ohm, this 12, sorry, not 12, 2 kilo ohm is connected between what? This point, but this point is what? Ground. I can also redraw the circuit like this. We have the op amp itself at the plus input terminal, a 1 volt voltage of 1 volt is applied. At the minus input terminal, it is simply connected to ground. Now this 2K, you can connect it at the output itself between output and ground. So between output and ground, you have 2K. This is V0. This is what a comparator, which will simply compare V plus and V minus. So 1 volt greater than 0, V plus more than V minus. So output will be what? Plus V sat, which is 12 volts. So this op amp does not have any feedback. That is the point. Okay. Moving on to the next question. In the circuit shown in this circuit, assume that the op amp is ideal. The bridge output voltage V0. Okay, this is the bridge they are talking about. You have to find this output voltage V0 in millivolts for the delta value equal to 0.05. Okay, fine. This is the op amp negative feedback, 100%. Output connected to what? Negative input terminal. Op amp in negative feedback. Immediately you can use what? Virtual short. What is V plus? 1. So due to virtual short, V minus is also at 1. This current is always 0. So what is this current? 1 minus 0 by 50 ohms. 1 volt by 50 ohms. Okay, 1 volt. Okay, 1 by 50 amps. Okay. So this is 1 by 50 amps. And this current, I will call it I. What is the value of I? It is 1 by 50 amps. Now, because this current is 0, even this current will be what? I. Okay. Now, this I, some of it will flow in this branch. The remaining current, the remaining part of I will flow in this branch. Okay. Now, if you look at this branch, what is the total resistance of this branch? 250 into 1 plus delta plus 250 into 1 minus delta. Okay. What is the resistance of this branch? 250 into 1 minus delta plus. So the point is this. The resistance of this path is the same as the resistance of this path. In such a case, this current will get equally divided between the two paths. Okay. So what will this current be? It will be I by 2. What will this current be? This will also be I by 2. That's all. Okay. So this current is I. This current is I by 2. This current is also I by 2. Due to I by 2 flowing through this, there will be some drop with this polarity. Due to the same I by 2 flowing through this, there will be some drop with this polarity. Now what? We can write KVL around this loop. You can start anywhere. Okay. Let's say I start here. Okay. If I start here and write KVL around this loop, minus 250 times 1 minus delta times I by 2. I by 2, okay. And then you go like this, minus V0, you go like this, plus 250 times 1 plus delta times, again I by 2 equal to 0. Okay. That's all. So from here, you can just simplify and get the value of V0. Okay. So V0 equal to say 250 I by 2 and minus 250 I by 2 will get cancelled. I'll only write the delta terms. Okay. So 250 times delta times I by 2 plus minus into minus will become plus 250 into delta into I by 2. So, I mean, both are identical. So, this will be 250 into delta into I. 250 times delta times I. Now, you plug the values into this expression. I think in the question, delta is given 0.05. 0.05 is what? I think 5 by 100. And previously, we found I as what? 1 by 50. That's all. Okay, so 50 goes into 250 as what? 5. 5 times 5, 25. 25 by 100, 0.25 volts. So what is the answer? It is 0.25 volts. I think the options are not given. Are they given? No. Moving on to the next question. A PIN photodiode of responsivity. So for this photodiode, the responsivity is what? 0.8 amperes per watt. What is responsivity? You know, it is IL divided by P in optical. IL is what? The resulting photocurrent due to the incident light. P in optical is what? The optical power that is incident on the photodiode, which will produce that IL. Okay, is connected to the inverting input of an ideal op amp. Okay, there is the inverting input. Okay, the supply voltage are given. Load resistance RL is 10 kilo ohms. If 10 microwatts of power is incident. Okay, so from this, what is the photocurrent? R into P in optical. R is what? 0.8. And they are saying 10 microwatts is the incident optical power. So 10 into 10 power minus 6. So this is 8 microamps. This is what? 8 microamps. Then the value of the photocurrent in microamps through the load, which is the load. I mean, there is nothing that is mentioned as RL, but if you look at 10 kilo ohm, it is connected between output and ground. So definitely this 10 kilo ohm resistor should be treated as what? Load. So they are asking what is the current through this load? What is the current through the load? Okay. And by the way, is the photodiode forward or reverse biased? It will be reverse biased. Why? Because of negative feedback, the voltage at this point will be what? 0. Now for the photodiode, this is P side, this is N side. P side connected to what? 0, but N side connected to what? Plus VCC, which is far greater than 0 or P side. So this photodiode, it is what? Reverse biased. Okay. So when photodiode is reverse biased, so you know ID is equal to what? IS times e power Vd by Vt minus 1 and then minus IL. When I say diode is what? Reverse biased, Vd will be what? Some negative value. When Vd is negative, the value of the exponential will be far less than 1. Then you can neglect the exponential in comparison to 1. Then IS into minus 1 is what? Minus IS and then minus IL. Usually the photocurrent IL will be far greater than reverse saturation current, many orders of magnitude bigger than IS. So ID is equal to what? Minus IL. If ID is minus IL, then the reverse current will be what? Plus IL. Okay, reverse current will be what? Plus IL. Reverse current will flow in the reverse direction, that is from N side to P side, and this current is what? The photo current, which is 8 microamps. So what is this current? It is 8 microamps. What is this current? It is 0 input current. So this 8 microamps will simply flow through what? 1 mega ohm, resulting in a drop of 8 micro into 1 mega. Micro mega will cancel out 8 volts. By the way, the voltage at this point is same as V plus, which is 0. This is 0, go from plus to minus. So the voltage at the output will be what? Minus 8. Once you know, okay, this is RL for us. This is the load current. This is the load current. So what is the load current? Minus 8 minus 0 by 10K. So minus 8 volts by 10K, which is minus 0.8 amps. Okay, minus 0.8 milliamps. But I think we have been asked to find the current through the load in microamps. 1 milli is what? 1000 micro multiplied with 1000. 0.8 into 1000 is what? 800 minus 800 microamps. Okay, so they should have asked about the magnitude of the current through the load, then there will be no confusion. The answer would be 800. Okay, or at least they should have indicated the current direction. Okay, so in the downward direction, the current through the load is what? Minus 800 microamps. Okay. All right, look at the next question. An ideal op amp has voltage sources V1, V3, V5 up to Vn minus 1 connected to the non-inverting input. I mean, all these voltages, input voltages are connected to the plus input terminal. Okay. And also we have a bunch of other input voltages which are even numbered. Okay, V2, V4 up to Vn, they're all connected on the inverting input terminal side. And the supply voltage for the op amp are plus 15 and minus 15. The voltages V1, V2, V3, V4 up to Vn are such that they are 1 minus half. Okay, all the odd numbered input voltages are positive valued, and all the even numbered input voltages, okay, V2, V4, V6, V8, etc., they are all negative valued. Okay, and the question is, as n approaches infinity, so if you have infinite number of these, you know, input voltages connected to the circuit, then what is the output voltage in volts? That is the question. Okay, so we'll do the analysis and find what is the output. So first of all, the output of the op amp is connected to what? The negative input terminal. So definitely you have to use what? Virtual short. What is our virtual short? This point and this point both are at same potential. Okay, so let us use virtual short in order to find the output in terms of all the various inputs. Okay, please follow carefully. Let me call the voltage at this node as some V. Okay, if that is V, then this is also V, correct? And then I'm going to write KCL here and also here. What is this current? V minus V2 by 10K. What is this current? V minus V4 by 10K. And up to Vn, what is this current? V minus Vn by 10K. What is this current? V minus V0 by 10K. I'll write KCL at this point. Remember, this input current is what? 0. Now, all four currents are leaving this node. So, I mean, all currents are leaving this node. Add up all the currents equal to 0. Okay. So, V minus V2 by 10K plus V minus V4 by 10K up to V minus Vn by 10K plus not equal to this plus. V minus V0 by 10K equal to 0. What is the LCM? Clearly the LCM is what? 10K. LCM is what? 10K. So when you take LCM and how many such V terms will be there? N by 2. Yes or no? 2, 4, 6, 8, like that up to N, there will be N by 2. N by 2 number of V's. So V times N by 2 is equal to V2 plus V4 plus V6 plus, like this up to Vn plus V0. Okay. So V will be 2 by N times, I'm sorry, this bracket will be here. Okay, so 2 by N times V2 plus V4 plus V6 up to Vn plus V0. Okay. In the same way, let us write KCL at this node. Remember, we have called this as V, so this is also going to be the same V. You can take any direction for the current. I will take the current to be away from the node. This current anyway is what, 0. Again, all currents are leaving the node. Add up all the currents equal to what, 0. So what is this current? V minus V1 by 1K plus V minus V3 by 1K and so on up to V minus Vn minus 1 by 1K plus V by 1K equal to 0. Okay. Again, LCM is what? 1K. And like this, you'll have n by 2 number of V terms. N by 2 times V is equal to it's not n by 2. Okay. You also have this extra V by 1K term. Okay. Plus V is equal to V1 plus V3 up to Vn minus 1. Okay. Here again, if you try to write an expression for V, that would be what is 1 plus n by 2 plus 1 is what? N plus 2 by 2, which is 2 by 2 plus n times V1 plus V3 up to Vn minus 1. So previously I got this. Now I'm getting this. Okay. Did I make a mistake anywhere? Oh, I made a mistake. Like here, also there will be how many number of V terms? N by 2 plus 1. Okay, so here I should have written V times N by 2 plus 1. Okay. So V times N by 2 plus 1. Now this V can be written as 2 divided by N plus 2. So look at the two equations that we obtained. Okay. V is equal to 2 by N plus 2 times this thing. That is one thing. The same V is also equal to 2 by N plus 2. 2 plus N, N plus 2 both are same. This thing. Okay. So here, in place of this V, I'll write this thing. In place of this V, I'll write this thing. Then I'll get 2 by N plus 2 times V2 plus V4 up to Vn plus V0 is equal to 2 by 2 plus n times this factor, which is V1 plus V3 up to Vn minus 1. Okay. Now what? This 2 by n plus 2 and 2 by n plus 2 will get cancelled out. Only this V0 will keep it on the left side. All this V2 up to Vn will send it to the other side. Then we'll get V0 is equal to V1. This V2, when it goes to the other side, it becomes minus V2. And then I'll write V3. Again, V4 on the other side will become minus V4. Like this, you'll get up to n. Okay. So all the even terms have a negative, have a multiplying factor of minus 1. odd number terms will appear as it is. Okay, that is the thing. So like this, up to Vn minus 1 and then minus Vn. Okay. Now what is given in the equation? V1, V2, V3 are what like this. Okay. 1 by 1 minus 1 by 2, 1 by 3 minus 1 by 4 like that. Okay. So in place of V1, you can just write 1. V2 is what? Minus half. Yes or no? V2 is what? Minus half. So minus V2 will be what? Plus half. Again, V3 odd number, it is what? Positive, and it is equal to what? 1 by 3. V4 even number, negative. V4 is what? Minus 1 by 4. Minus V4 is what? Minus half minus 1 by 4, which is plus 1 by 4. That's all. Like this, you have up to n. But the question is what? What is the output as n approaches infinity? As n approaches infinity. So sorry. Like this, you have infinite terms. Okay, 1 by 5, 1 by 6, 1 by 7, 1 by 8, up to 1 by infinity. 1 by infinity is anyway 0. But what is the sum of this infinite number of terms? Okay, that is the output voltage value. Okay. So I'll just write that summation 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 plus 1 by 9 plus 1 by 10. Like this, I'm not going to write all the terms. I cannot do that. Like this, you have infinite terms. Now the question is, what is the sum of this? What is the value of the summation? What is the value of the summation? Okay, already 1 is there. Okay, I'll tell you one thing. Please understand carefully. Look at these two terms. 1 by 3 plus 1 by 4. 1 by 3 plus 1 by 4, will it not be greater than 1 by 4 plus 1 by 4? Think about it. Here also 1 by 4, here also 1 by 4. But 1 by 3 is definitely greater than 1 by 4. I hope all of you agree with this. Now what is 1 by 4 plus 1 by 4? Half. That means the value of the sum of these two terms is definitely greater than half. Yes, I'm not saying it is equal to half. It is some value greater than half. Okay? Fine. Now you look at 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. These four terms, okay, together. 1 by 5, say among these four terms, which is the smallest value? 1 by 8. Yes or no? 1 by 5 up to 1 by 8. Smallest is what? 1 by 8. Okay. So 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. Can I say it is greater than 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8? Definitely, right? Because 1 by 5 is greater than 1 by 8. 1 by 6 is greater than 1 by 8. 1 by 7 is greater than 1 by 8. 1 by 8 and 1 by 8 both are equal. So clearly left hand side is greater than right hand side. Okay. But what is the value of the right hand side? For 1 by 8 terms is what? 1 by 2. That means this is what? 1 by 2. So this sum of these four terms again is some fraction which is greater than half. So the sum of these four terms is also going to be some value which is greater than half. Like this, how many groups can we form, and the sum of each group will be greater than half? You can form infinite groups. Yes or no? Starting from 1 by 9, you can make a group up to 1 by 16. 1 by 9, 1 by 10, 1 by 11, up to 1 by 16. 1 by 9 to 1 by 16, how many terms you have? 8 terms. Now, each one of these terms from 1 by 9 up to 1 by 16 will be greater than 1 by 16. So it is like having 8 into 1 by 16. 8 into 1 by 16 is what? Half. So again, we can have a group whose sum is what? Greater than half. Then again from 1 by 17 up to 1 by 32. 16 terms. 1 by 17 up to 1 by 32. 16 terms. Every term will be greater than 1 by 32. 16 into 1 by 32 is what? 1 by 2. Again, that group also will have a sum which is greater than half. Like that, we can form infinite such groups. What is infinity into 1 by 2? Infinity. So the value of this infinite summation is what? Infinity. It won't converge to some finite value. Please understand that. Okay. So like this, I can form infinite number of groups, and for each group, the value of the sum will be greater than half. Infinity into greater than half is also what? Infinity. So this output tends to infinity. But the output voltage cannot be infinite. Output will get saturated to plus Vsat. Output gets saturated to plus Vsat. Okay. So what is plus VCC? It is 15. So the output voltage V0 will be what? Plus 15 volts. Okay. Moving on to the next question. The two input voltage multiplier. This is the voltage multiplier. So for the voltage multiplier, as you can see from the arrow marks, these are the two inputs that will get multiplied and the product will appear here. Okay. So already this is V2, this is V0. So what is the product that will appear at the output of the multiplier? V0 times V2. V0 times V2. And has a scaling factor of 1. K times the product of these two, and that scaling factor is what? 1. Okay, so don't worry. Produces output voltage. Voltage output, if V1 is 15, V is actually V1. Okay, this is 15. V2 is 3. Okay, that means this is what? 3V0. This is 3V0. The value of V0. That's all. I mean, this current is what? 0. Voltage at this point will be 0 due to virtual short. Then you can equate these two currents, right? 15 minus 0 by R. 15 by R is equal to 0 minus 3V0, which is minus 3V0 divided by R. R will get cancelled. V0 is what? Minus 5 volts. Okay, so V0 is what? Minus 5 volts. Moving on to the next question. For the circuit shown below, assume the op amp is ideal. Which one of the following is true? Okay, you have to find relation between V0 and Vs. Negative feedback, so let us just use virtual short. This is 0. If you assume the voltage at this point to be some VA, yes, if you assume the voltage at this point to be some VA, and by the way, what is this current? 0. That means, if for example, if the current through this 2R is like this current has to flow like this, which means what? 2R and 2R both are in series between 0 and Vs. So directly I can tell the voltage at this point will be what? Vs by 2. This is Vs by 2. If V plus is Vs by 2, then from virtual short, V minus is also what? Vs by 2. Okay. And then, you can find this current 0 minus Vs by 2 upon R. Okay. And you can also write this current. And at this point, if you write KCL, these two currents will be equal. Okay. That way, you'll get VA in terms of Vs. I think it will be 0. I think it is 0. Let's find out. At least whatever I did so far, I hope is correct. This Vs by 2, this Vs by 2. Okay. So what is this current? 0 minus Vs by 2 upon R. Minus Vs by 2 upon R. What is this current? Vs by 2 minus Va. Vs by 2 minus Va divided by R. So this R and this R will get cancelled. So what is Va? I'm getting Va as Vs. I'm sorry, Va is not 0. Va is Vs. Okay, so this Va, it is what? Vs. Okay. And then you can write KCL at this point. Okay, now you can write KCL at this point. What is this current? Vs minus 0 by R, which is Vs by R. Okay. What is this current? Vs minus V0 by R. What is this current? Vs minus Vs by 2, which is Vs by 2 divided by R, which is Vs by 2R. Now if you observe, outgoing, 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 all three currents are leaving. Add the three currents equal to 0. So Vs by R plus Vs by 2R plus Vs minus V0 by R equal to 0. That's all. You take LCM, you'll get V0 in terms of Vs. So what is LCM? It is 2R. So 2 Vs plus Vs plus 2 Vs minus 2 V0 equal to 0. So 2 V0 equal to 5 Vs. So what is V0 by Vs? I'm getting 2.5. Okay, that is option C. So V0 is what? 2.5 Vs. Moving on to the next question. An op-amp based circuit is implemented as shown below. I mean, this circuit is what? Inverting amplifier, right? 1 volt is like the input. This is like R1, this is like R2, and this is the output. Okay, in the above circuit, assume the op-amp to be ideal. The voltage in volts correct to 1 decimal place at node A. Okay, node A is what? The negative input terminal connected to the negative. Yeah. So you have to find VA. VA is actually what? V minus. VA is actually what? V minus. So what is the voltage here? It is 1. So initially we'll assume virtual short is valid and so on. So this is R2 and this is R1. So your output will be what? Minus R2 by R1 times Vi, which is minus 31K by 1K, which is minus 31 volts. Okay. So definitely minus 31 volts is outside the range between minus Vsat and plus Vsat. Output will get saturated to minus 15. So what is your output? It is minus 15. So whenever output gets saturated, your V plus and V minus will not be equal. Had the output not been saturated, then you can say V minus is equal to what? 0. But because the output is saturated, V minus is not 0. Okay, so what is the output saturated to? Minus 15. Okay, so what is the voltage here? It is minus 15. So here also it is minus 15. Here it is what? 1 volt. Whether output is saturated or not, the input current will always be 0. And always 1K and 31K should be in, will have the same current. They'll be in series between 1 and minus 15. So what is the voltage at this point? 1 into 31 and then minus 15 into 1. Okay. So V minus is 1 into 31 plus minus 15 into 1 divided by 1 plus 31. 31 minus 15 is what? 16. 16 by 32 is what? 0.5. So V minus is 0.5. So V minus is 0.5. V plus connected to ground will always be at zero potential. So which is bigger? V minus is more than V plus. Whenever V minus is more than V plus, Vd is negative, output will be what? Minus V sat. Already for us, output is what? Minus V sat or minus 15. Okay. Moving on to the next question. The circuit given uses two ideal op amps. The current I, okay, you have to find this current I drawn from the source. So here we have an input source, okay. So here between this point and ground, you have the input source Vi, whose value is what? 1 volt. Whose value is what? 1 volt. I think there is a power fluctuation continuously. So here, if you try to check the type of feedback, while checking the type of feedback, this input you have to make it 0. It becomes short circuit. When it becomes short, now for this op amp, output is only connected to what? Negative input, negative feedback. Now even for this op amp, you can only go like this, not like this, because if you try to go like this, here you'll have ground, because this point is shorted to ground. You should not be going like this. For each op amp, you have to go like this and like this. In both cases, both op amps are in negative feedback. So we can use what? Virtual short. Okay. So let us use virtual short and find what is the value of I. If this is 1 volt, this thing is what? An inverting amplifier. Input R1, R2, output plus terminal. What is the gain of this inverting amplifier? Minus R2 by R1, minus 20K by 10K. So what is the voltage here? It is minus 2 volts. From here to here also, you can assume, you can imagine there is, you can think that we have what? Inverting amplifier. Which will be, so this will be plus 2 volts. Okay. What is the voltage here? It is 0. What is this current? Remember, this is 1 volt. 1 minus 0 by 10K. 1 by 10K is what? 0.1 milliamps. What is this current? Remember, this point is what? 1. And this point is what? 2. So what is this current? 1 minus 2 minus 1 by 10.1 K. Minus 1 volt by 10.1 K. This is 1 volt by 10K. Now, if you write KCL at this point, I is equal to 0.1 milliamps minus what is 1 volt? So here you have to be careful with the numbers. So that is the value of I that I am getting. Microamps, right? Your answer has to be in microamps. And this is the answer in microamps. No, one second. Milli to micro, I just have to multiply it with 1000, right? I think this is incorrect. Point 0.1 minus 0.099 into 1000. Maybe this is 1 microamp or something. Okay, just be careful with the calculation. We still have a few more problems left. We'll take a 5 minute break. Okay, I'll be back. So this is zero point 0.1 milliamps. That is correct. This is okay. It is just a calculation exercise. Let's continue. Assuming ideal op amp. So this op amp, they're saying it is what it is ideal. RMS voltage in millivolts in the output V naught only due to the 230 volt 50 hertz interference up to 1 decimal. So this is some uh, source of interference. Okay, some AC source which is interfering with this circuit. So what is the actual intended input for this circuit? It is here. Okay, so between this point and ground, you have a DC input of value 1 volt. Okay, so ideally your output should be only due to what? This but because this is interfering with this circuit, you'll also get some extra component at the output. So the question is, what RMS voltage in the output due to what is this 230 volts? This is AC source. 230 volts itself is what RMS value, and the frequency is what 50 hertz. Okay. Uh, so if you are asked to find output only due to this interference source, this VDC source, you can make it 0. When you make it 0, this becomes shorted to ground. Yes or no? So this becomes shorted to ground. So the only source that is going to be present is what? The interference source, which is like a AC voltage source. Okay. And they're asking what is the RMS value of the output due to this interference. Okay. So as I told you, this point you can simply short it to ground. What is the voltage at this point going to be 0 because of virtual short. Okay. Now if you look at 10K, it is between 0 and 0, no current flows, you can remove this. You can remove this. Okay. And you can call this as what? The input source Vn. Let us do the analysis in the phasor domain. In the phasor domain, this input source just becomes what? Capital Vn. Also this current is what? 0. Now in the phasor domain, the capacitor should be treated as what? An impedance. Let's call it impedance Z1. Even this resistor can be treated as another impedance Z2. What is this current? What is this current? Ohm's law. Here the voltage will be what? Vn. Okay. Vn minus 0 by Z1. Correct? Vn minus 0 by Z1. What is this current? Again Ohm's law. 0 minus V0 by Z2, which is minus V0 by Z2. Now at this point we can write KCL. At this point Vn by Z1 is what? Entering. Minus V0 by Z2 is what? Leaving. So Vn by Z1 is equal to minus V0 by Z2. So what is V0 by Vn? It is minus Z2 by Z1. Okay. So the question is what? To find the RMS value of the output voltage. Okay. So anyway, Z2 is what? 50 kilo ohms, which is 5 into 10 to the 4. Z1 is what? Impedance of this 3 picofarad capacitance at a frequency of 50 hertz. Okay, so Z1, remember, I'll write it at the bottom. So Z1 is what? 1 by j omega c. Okay, which is 1 by j times omega is what? 2 pi times 50. 2 pi times 50, and c is what? 3 picofarad, which is 3 into 10 raised to minus 12. Okay. So in place of Z1, when you write 1 by j omega c, that j omega c will actually go to what? Numerator. Okay. Now if you simply take magnitudes on both the sides, okay, this minus and also j will disappear when you take magnitudes. Okay. See, for a phasor, the magnitude is same as what? RMS. Okay. Yes, no, for a phasor, the magnitude is same as RMS. Already the RMS value of input is 230. So VO RMS divided by V in RMS, which is given as 230. It's all about finding the value of this. 5 into 10 to the 4 into omega is what? 2 pi into 50. 2 pi into 50, I'll write it as 100 pi. And then the C, 3 picofarad, I'll write it as 3 into 10 to the minus 12. Okay. That's all. And also your answer has to be in what units? Millivolts. Okay. That means something times 10 power minus 3. So VO RMS is equal to 230 into 5 into 100 into 3.14 into 3. Okay, and then 10 power 4 into 10 power minus 12 is 10 power minus 8. Mm. 10.83 into 10 power minus 3, which is 10.83 millivolts. Okay. All right, moving on to the next question. I think we are almost about to finish off the questions. Maybe 2-3 questions more are left. 54, 55, 56, 57, 57, 50. Okay, around 5 questions to go. If the op amps in the circuit shown are ideal, there are two op amps, Vx, okay, 0.5 millivolts, the steady state value of V0. So this Vx is 0.5 millivolts. It is what? DC. And they are asking steady state. At the input source is DC, circuit will reach what steady state? It will reach DC steady state. Yes or no? Input source is DC, circuit will reach DC steady state. At DC steady state, this cap will act as what? An open circuit. Yes or no? Cap will act as an open circuit. So some of you might be wondering, when the cap becomes open, then the output for this op amp is not connected to negative, which is correct. But still, it is part of a loop. Okay. See, you can go from here to here, positive gain through resistor. While finding loop gain, voltage source, it becomes 0. So this thing is actually gain of 1. Then from here to here, positive gain. From here to here, also positive gain. And then negative gain. So positive into 1 into positive into negative. Overall loop gain is what? Negative. And also the loop contains what? Both the op amps. So definitely both op amps will be in negative feedback. Both op amps will be in negative feedback. Now let's find out the output voltage V0. Steady state, okay? At steady state, what steady state? DC steady state. This cap will become open. This Vx is given, fine. Will any current flow here? No. So what is the current through this resistor? 0. What is the drop across this? 0. This ground will appear here. So what is the voltage here? 0. V minus 0 due to virtual short. V plus is also 0. This is 0. You go from minus to plus. Add the drop. So what is the voltage here? Vx. Also input current 0. So this current 0. Because this current is 0, these two resistors will be in series. Between V0 and ground, so what is the voltage here? V0 into 100 divided by 99.9, 100 plus 99.100 is what? Like 0.1 kilo. Okay. So the voltage here will be V0 into 0.1 K divided by 100 K, which is V0 by 1000. So what is the voltage here? It is V0 by 1000, but it is same as what? Vx, which is 0.5 millivolts. So V0 by 1000 is what? 0.5 milli, which is 0.5 times 10 power minus 3. So what is V0? It is 0.5 volts. So what is V0? It is 0.5 volts. Okay. Moving on to the next question, the current gain. Current gain I out by In. This is the input current, this is the output current. The circuit with an ideal current amplifier. Okay, this is quite simple. negative feedback. So what is this current? Because this current is 0, this is not IM, this is I in, okay? This current is also I in. What is resulting drop across this? If I call this as Z1, okay? Impedance of CF is Z1, then this drop will be I in times Z1. Because of negative feedback and resulting virtual short, even V minus will be 0 because V plus is 0. This is 0, you go from minus to plus, add the drop. What is the current, what is the voltage at this point? I in times Z1. Now, I out is what? Current through this capacitor in this direction, Ohm's law. So, I out will be equal to I in times Z1 divided by the impedance of the first capacitor 1 by SC. So, what is, what is I out by I in? Z1 is what? 1 by SCF, and this is 1 by SCC. This will get cancelled. You'll get CC by CF, which is correct, right? Directions, everything is fine. It is correct. Okay, CC by CF. That is the current gain. Moving on to the next question, the V out by V in. This is the output voltage V out. This is the input voltage V in. Okay, V out by V in. The diagram is not that clear. Okay. There are 3 op amps. First op amp output connected to negative. Second op amp also output connected to negative. Third op amp also output connected to negative. So all 3 op amps are clearly in negative feedback. You can just use a virtual short. Okay. You see, if you look at this part of the circuit, input R1, R2, output plus 10. So this is what? An inverting amplifier. Whose output will be what? V in times minus R2 by R1. Okay, minus R2 by R1 times V in. Now the same V in is also applied at this point. If you look at this part of the circuit, input applied at plus input terminal, then you have R2 and R1. This is what? The non-inverting amplifier. This is the non-inverting amplifier. So what is the voltage here? V in times 1 plus R2 by R1. Okay, so V in times 1 plus R2 by R1. Okay. And then this part of the circuit of this block, it is what? A weighted summer, for which directly we can write what are the 2 inputs for the weighted summer? Minus R2 by R1 V in and V in times 1 plus R2 by R1. Okay. So what is V out going to be? This input multiplied with minus R4 by R3. Yes or no? Minus R2 by R1 times minus R4 by R3 times V in. Okay. And then this input also gets multiplied with minus R4 by R3. Minus R4 by R3 times 1 plus R2 by R1 times V in. I think a few terms will get cancelled out. Okay. This will be positive. R2, R4 by R1, R3 times V in. And this will get cancelled out. I guess you'll get minus R4 by R3 times V in. So what is V out by V in? Minus R4 by R3, which is option A. Okay. Look at the next question. The op amps in the circuit are ideal. The op amps in the circuit are ideal. The input signals are, there are 3 op amps. In fact, okay, the input signals are Vs1 applied here, which is 3 plus that sine thing, and Vs2 applied here, which is minus 2 plus another sinusoidal voltage. The average value of the output, voltage V0 is dash. Okay. So this op amp negative feedback, this op amp also negative feedback. So what is the voltage here? It is Vs1. What is the voltage here? It will be Vs2. Yes. What is this current? 0. What is this current? Also 0. Even this current and this current both are 0. So here you can write Vs1. Here you can write Vs2. Okay. Let me call the voltage at this point. See. So what is the drop across this? Vs1 minus Vs2. Correct or not? Vs1 minus Vs2. So this Vs1 minus Vs2, I'll call it VA. I'll call it VA. That voltage drop or the voltage difference between Vs1 and Vs2, I'll call it VA. Let's compute the value of Vs1 minus Vs2. Vs1 3. 3 minus 2 is what? 5. 0.1 minus 0.11. 0.1 minus 0.11 is minus 0.01 sine of 300t. Okay. Okay, this is the potential difference across this R, which is VA. Now, because this current is 0, this current and this current both are equal. Even this current will be same as this current. If this current is some I, then the drop across this is what? IR. Drop across this is also what? IR. So I can say drop across this is also what? VA. Drop across this is also what? VA. Okay. Okay. And so what is the drop across this branch? VA. So I can say the drop across this entire branch is what? 3VA. Okay. So again, this R and this R both are in series. They're identical. They have same voltage drop as well. So this will be half of 3VA. Okay. Half of 3VA is what? 1.5 VA. Even this will be what? Like 1.5 VA. Okay. Now let's say we start at this point. Be careful. This is Vs1. You go from minus to plus. Okay. So what is the voltage at this point? Vs1 plus VA. Correct? Vs1 plus VA. And then from this point, you go up to this point. You are going from plus to minus. You are going from plus to minus. And the voltage at this node, you can call it V0. So V0 will be Vs1 plus VA minus whatever is the drop in between. Okay. So Vs1 plus VA minus 1.5 VA, which is same as Vs1 minus 0.5 VA. Now we know what is VA. We also know what is Vs1. Let's put the values. Then maybe we'll get the answer. Okay. So Vs1 is what? 3 plus 0.1 sine 300t. Okay. Three plus, so that is what? Vs1 minus 0.5 VA. Already there is VA, so minus 2.5, and then plus 0.005 times sine of 300t. What is the equation? Average value. Question is what to find average value. Average value of any sinusoidal term is what? 0. For this term, the average value is 0. Even for this term, the average value is what? 0. Then the only DC, then the only terms that remain when computing average is what? The DC values. Okay. 3 minus 2.5, which is 0.5 volts. That is the output average. This is not the output. This is VO average. This is the complete output expression. Okay, I think you can also combine these two. 3 minus 2.5 also, you can write it as 0.5. Okay. Yeah, 0.5, that is correct. All right, look at the next question. In the circuit shown, the input voltage Vin, this is the input voltage. They are saying it is 100 millivolts. The switch and the op-amp, this switch, which is being moved between 1 and 2, it is ideal. Even the op-amp is not ideal. At time t equal to 0, that is initially, the initial charge stored in the 10 nanofarad capacitor. This is the 10 nanofarad capacitor. They are saying the initial charge stored in this cap is what? 1 nanocoulomb. Okay, so 10 nanofarad cap, the initial charge is what? 1 nanocoulomb. Okay, so if you know the charge, if you know the capacitance, can't we find what is the initial voltage across this capacitor? So V, Q equal to CV, C is what? Q by V. 1 nanocoulomb divided by 10 nanofarad. 1 by 10 is what? 0.1 volts. With the polarity as indicated in the figure. So the initial voltage across this 10 nanofarad cap is what? 0.1 volts with this polarity. Minus on the left, plus on the right. Okay. What else is given? The switch S, this switch is controlled using a 1 kilohertz square wave voltage signal as shown. This is the square wave at a frequency of 1 kilohertz that is controlling this switch. Whenever Vs is high, so when the square wave value is high, the switch is in position 1. Vs is high, switch is in position 1. That means the switch is connected to what? Vin. Okay. And when Vs is low, the same switch is connected to what? Position 2, which is this connection. And then they are asking at t equal to 20 milliseconds. T equal to 20 milliseconds, the magnitude of the voltage V0. Okay, the magnitude of the voltage V0 in millivolts is how much? Let's understand what is going to happen in this circuit. Let's understand what happens in one cycle. Okay, each cycle, this is one cycle. Initially, the value of Vs is high, during which the switch is connected to position 1. And during the next interval, in the first cycle, in each cycle, when Vs is low, the same switch will be connected to point 2. Okay. You see that control input for the switch, which is this Vs, I have drawn one cycle of it. Okay, one time period, I have drawn that control signal, which is controlling the switch. Okay. So let's say during the initial part of the cycle, the control signal is what? High, in which case the switch is connected to what? Position 1. When switch is connected to position 1, whatever input voltage you have, 100 millivolts, will it not directly appear across the 1 nanofarad capacitor? Yes. So during the first half cycle, okay, during TH, I'll say during TH, okay, during TH, this cap will get charged to 100 millivolts, okay. Now you have TL interval where your Vs becomes low. When Vs becomes low, please understand this. When Vs becomes low, switch is going to be connected to position 2. Okay. So during TH, during TH, your 1 nanofarad capacitor will get charged to 100 millivolts. Okay. Now let's understand what happens during TL. During TL, the switch will be connected to what? Position 2, like this. Okay. When switch is connected to position 2, what is the voltage at this point? Due to virtual short, V plus 0, V minus also 0, then this is 0, this is ground. Immediately the voltage across 1 nanofarad capacitor becomes 0. But previously it was charged to what? 100 millivolts. So the moment the switches moved from 1 to 2, immediately this cap is getting discharged. Yes or no? So if you take 1 nanofarad capacitor, and if I call the voltage across it as some Vc, it is going from 100 millivolts to 0, which means the cap is getting fully discharged. Okay, so whatever charge is stored in the capacitor, the charge is going away from the capacitor. Okay, so how will they? So what happens when this cap gets discharged? Cap is getting discharged. It means what? It is losing charge. So charge is being removed from the capacitor. So where is the charge going? Okay. Can it go into the op amp? No. So the only way the charge can flow out of this capacitor, this cap is getting discharged, it means what? Current flows into or out of plus. Whenever cap gets discharged, current flows out of plus. Okay. And that current will actually flow like this. So don't you have a current flowing through the other capacitor? And this happens in every cycle. Okay. Anyway, we'll fully understand what is going to happen during this interval TL. Okay. So this current which is discharging this capacitor will also charge the other capacitor. So this current will do what? It will take out charge from this capacitor, and all of that charge will be transferred to the 10 nanofarad capacitor. This current, you can call it some I. This current will take out charge from this capacitor, and all the charge will be transferred to the other capacitor. Remember, already the 10 nanofarad capacitor is charged. But in addition to the existing charge, some extra charge is being added. Say if you have a capacitor across which the voltage is V, so what is the charge stored in the cap? You would say Q equal to CV. If I add some extra charge of delta Q to the capacitor, what is the change in voltage across the cap? Delta Q can be written as C times delta V. So what is delta V? The extra charge delta Q divided by the capacitance. What is the extra charge that is being added to this capacitor? Whatever charge is initially stored in this capacitor. Yes or no? Yes. Now due to this current flowing through the capacitor, some extra voltage will appear across this. That extra voltage is what? Delta V. So what is the polarity of delta V? Since the current that is transferring the charge from this cap to this cap is flowing from left to right, this will be plus, this will be minus. This is the polarity of delta V. Forget about the initial voltage. It is always there. Okay. On top of the existing initial voltage, some extra voltage will appear. For that extra voltage, the polarity is what? This. I hope this is clear. Based on the current direction, you have to decide that polarity. Okay. Now, what is the value of that extra voltage. Extra voltage or change in voltage is what? Delta Q. What is a delta Q? What is the initial charge stored in this capacitor? Okay. So 1 nanofarad capacitor, what is the charge? 1 nanofarad capacitor, what is the charge? Just multiply 1 nanofarad C into the voltage, which is 100 millivolts. Okay. This is the charge that is going to be stored in this capacitor when the switch is connected to Vin. Okay. But after that, the switch is moved to position 2. When that happens, this whatever charge is stored in this cap, that charge will be transferred to the other cap, which will lead to a change in voltage across the other cap. Okay. So initial charge stored in this cap is what? This much, and that charge will be completely transferred to the other cap because the same current flows throughout this. Whatever charge is removed from here, the same charge gets added to the other capacitor. Okay. 1 nanofarad into 100 millivolts. Okay. Sorry. Yeah. So what is delta V, delta Q, which is 1 nanofarad into 100 millivolts divided by this capacitance. Okay, for which cap the voltage is changing, it is this. So we write the value of that capacitance 10 nanofarad. Nanofarad cancel out. 100 by 10 is what? 10 millivolts. That is the incremental voltage or extra voltage across the capacitor in one cycle. This will happen in one cycle. After that, second cycle again, initially this control signal will be high. Again, the switch will be connected to 1. Again, this cap will get charged to what? 100 millivolts. Again, the switch will move to position 2. Again, that cap will get fully discharged and that charge gets transferred to the other cap. So in every cycle, this will happen. So every cycle, this will get charged and that charge will be transferred to this. Due to this transfer of charge from this to this, there will be some change in voltage, and the polarity of change in voltage is what? Always this, because every time the current flows from left to right, and the value of the change in voltage across this cap is what? 10 millivolts. Every cycle, the voltage across this cap increases by 10 millivolts with this polarity. Now what is our question? At t equal to 20 milliseconds, okay, 20 milliseconds is how many cycles? What is the frequency of this control signal? 1 kilohertz. 1 kilohertz, it means what is the time period? 1 millisecond. Yes or no? 1 kilohertz. Frequency is 1 kilohertz. Time period is what? 1 by frequency. 1 by 1 kilo is what? 1 milli. So the time period of one cycle, time period means what? Duration of one cycle. So time period is what? 1 millisecond. So t equal to 20 milliseconds, it means what? At the end of 20 cycles. At the end of 20 cycles. At the end of 20 cycles, what is the value of V0? That is what you need to find. Okay. In each cycle, what is the extra voltage that is added to this extra voltage across this capacitor? 10 millivolts. 20 cycles. 20 cycles. Delta V will be what? 20 into 10 millivolts, which is 200 millivolts. Okay. Now, what is the initial voltage across the cap, across this 0.1 millivolts, which is 100 millivolts. Polarity is what? Minus plus. But for the extra voltage, the polarity is what? Plus minus. Okay. So now if you draw this capacitor, okay, 10 nanofarad capacitor, initial voltage is what? 100 millivolts. And in every cycle, some extra voltage will appear across the cap, which has this polarity. So after every cycle, that extra voltage keeps getting added up. Okay. And we understood that after 20 cycles, the net extra voltage with this polarity plus minus is what? 200 millivolts. This is 200 millivolts. So what is the net voltage across the cap? The initial voltage and the delta extra voltage have opposite polarity, so you should not add them. Okay, this minus plus, this plus minus. This is bigger than this, so the final net voltage across the cap will have this polarity, but the value will be 200 minus 100, which is 100 millivolts. Okay, that's all. So what is the voltage at this point? Due to virtual short, it is 0. And just now we understood that at the end of 20 cycles, the net voltage across this cap will be 100 millivolts with this polarity. So 100 millivolts. This is 0, you go from plus to minus, subtract the drop. What is V naught? It is minus 100 millivolts. Okay. What is the question? V naught, the magnitude of the voltage V naught will be dash millivolts. It is, I mean, actual value of V naught is what? Minus 100. So V naught is what? Minus 100 millivolts. So mod V naught will be 100 millivolts. I hope it is clear. All right, guys, moving on to the next question. In the circuit shown, assume the op amp is ideal. Okay. In fact, what circuit is this? It is an integrator. Input RC, output plus terminal connected to ground. It is what? The integrator. Okay. Initial charge on the capacitor is 0. Better. What is the voltage here? It is 0. Initial voltage across the cap, 0. This is 0. This is 0. What is the initial value of V naught? Also 0. Okay. And the input is what? This rectangular waveform. Okay, with a height of 5 volts. Okay, the output voltage at t equal to 2 milliseconds. Okay, I mean, you just have to go by the output expression for the output voltage as a function of time. Okay, in terms of the input voltage. So we know very well V naught of t is equal to minus 1 by RC times 0 to t integration of Vi from 0 to t. Yes or no? Minus 1 by RC times integration of the input from 0 to t. Yes, this can be used when the initial value of V naught is what? 0. Okay? Or the initial voltage across the cap is 0. So what is the value of RC? R is 1 kilo ohm, C is 2 microfarad. RC will be what? 1K into 2. 2 milliseconds. So minus 1 by 2 milliseconds. And by the way, the question is what? To find the output at t equal to 2 milliseconds. So in place of this t, you should write 2 milliseconds. Integration of the input from 0 to 2 means what? Finding area under the input waveform from 0 to 2. Look at the input waveform from 0 to 2. 1 to 2, anyway, input is 0 out. Even area will be 0. 0 to 1, you just have to find this area. What is the area of this box? Height into width. 5 volts into 1 millisecond. That is the value of the integral of the input from 0 to 2 milliseconds. So minus 1 by 2 milliseconds times 5 volts into 1 milliseconds. So milli and milli will get cancelled. So the answer is what? Minus 2.5 volts. So you just have to go by the output expression for the integrator. Okay. The op amps in the following circuit are ideal. There are two op amps, both are ideal. The voltage gain of the circuit. Voltage gain means what? V out by V in. Okay. V out by V in. See, what is this V in? It is the potential difference between it is the potential difference between this point and this point. Let me call the voltage at this point as V1. Let me call the voltage here as V2. And V in is what? V1 minus V2. So if you have V2 here, then due to virtual short, there is also V2. What is this current? 0. What is this current? It is, I mean, not required. Okay. So this is like a non-inverting amplifier, right? Input V2 applied at plus input terminal R2 and R1. So the output of non-inverting amplifier can be directly written as 1 plus R2 by R1, which is 1 plus 1, 2 times V2. So the output voltage of the first op amp is what? 2V2. So this 2V2, this V1 will definitely appear here as well. So what is this current? 0. That's all. Now you just have to write KCL at this point. So what is this current? 2V2 minus V1 by 10K and V1 minus V0 by 10K. Both currents are equal. So 2V2 minus V1 by 10K is equal to V1 minus V0 by 10K. So 10K and 10K will get cancelled out. So you're going to get V0 is equal to 2V1 minus 2V2, which is 2 times V1 minus V2. And this Vn is not V1 minus V2. It is V1 minus V2. Yes, Vn is what? V1 minus V2. So in place of V1 minus V2, we can just write Vn. So V0 equal to 2Vn. So what is V0 by Vn? It is 2. That is the voltage gain of this circuit. Okay. So we have completed all questions. Okay, all PYQs which are based on ideal op amp in negative feedback from all 3 streams. Okay, electrical, EC, and IM. So every good question has been discussed in this session. So I hope that it is going to be useful for you guys in the upcoming GATE exam. Okay. So I'll see you in the next session where we'll solve problems with respect to the remaining topics, which are comparator, the Schmidt trigger, the different types of oscillator circuits you can make using Schmidt trigger, and also active filters, and also the non-ideal or real op amp. Okay, so we'll do remaining things in the next session, which will be 2 to 3 days from now. Okay. So, all right, guys. Thank you for being a part of this session. Good night. I'll see you in the next session. Okay.